The Origin of Species by means of natural selection, or the Preservation of Favoured Races in the Struggle of Life, 6th London edition, by Charles Darwin. Chapter number 5. Laws of Variation. Contents of this chapter include effects of changed conditions, use and disuse combined with natural selection, organs of light and of vision, acclimatization, correlated variation, compensation and economy of growth, false correlations, multiple, rudimentary and lowly organized structures variable. Parts developed in an unusual manner are highly variable, specific characters more variable than generic, secondary sexual characters variable. Species of the same genus vary in an analogous manner. Reversions to long-lost characters. Summary. I have hitherto sometimes spoken as if the variations, so common and multiform with organic beings under domestication, and in a lesser degree with those under nature, were due to chance. This, of course, is a wholly incorrect expression, but it serves to acknowledge plainly our ignorance of the cause of each particular variation. Some authors believe it to be as much the function of the reproductive system to produce individual differences or slight deviations of structure as to make the child like its parents. But the fact of variations and monstrosities occurring much more frequently under domestication than under nature, and the greater variability of species having wide ranges than of those with restricted ranges, lead to the conclusion that variability is generally related to the conditions of life to which each species has been exposed during several successive generations. In the first chapter I attempted to show that changed conditions act in two ways: directly, on the whole organization or on certain parts alone, and indirectly, through the reproductive system. In all cases there are two factors: the nature of the organism, which is much the most important of the two, and the nature of the conditions. The direct action of changed conditions leads to definite or indefinite results. In the latter case, the organization seems to become plastic, and we have much fluctuating variability. In the former case, the nature of the organism is such that it yields readily, when subjected to certain conditions, and all, or nearly all, the individuals become modified in the same way. It is very difficult to decide how far changed conditions, such as of climate, food, etc., have acted in a definite manner. There is reason to believe that in the course of time the effects have been greater than can be proved by clear evidence. But we may safely conclude that the innumerable complex co-adaptations of structure, which we see throughout nature between various organic beings, cannot be attributed simply to such action. In the following cases the conditions seem to have produced some slight definite effect. E. Forbes asserts that shells at their southern limit, and when living in shallow water, are more brightly coloured than those of the same species of further north, or from a greater depth. But this certainly does not always hold good. Mr. Gould believes that birds of the same species are more brightly coloured under a clear atmosphere than when living near the coast or on islands, and Wollaston is convinced that residence near the sea affects the colours of insects. Moquin-Tandon gives a list of plants which, when growing near the seashore, have their leaves in some degree fleshy, though not elsewhere fleshy. These slightly varying organisms are interesting in as far as they present characters analogous to those possessed by the species which are confined to similar conditions. When a variation is of the slightest use to any being, we cannot tell how much to attribute to the accumulative action of natural selection, and how much to the definite action of the conditions of life. Thus, it is well known to furriers that animals of the same species have thicker and better fur the further north they live. But who can tell how much of this difference may be due to the warmest clad individuals having been favoured and preserved during many generations, and how much to the action of the severe climate? For it would appear that climate has some direct action on the hair of our domestic quadrupeds. Instances could be given of similar varieties being produced from the same species under external conditions of life, as different as can well be conceived, and, on the other hand, of dissimilar varieties being produced under apparently the same external conditions. Again, innumerable instances are known to every naturalist of species keeping true, or not varying at all, although living under the most opposite climates. Such considerations as these incline me to lay less weight on the direct action of the surrounding conditions than on a tendency to vary, due to causes of which we are quite ignorant. In one sense, the conditions of life may be said not only to cause variability, either directly or indirectly, but likewise to include natural selection, for the conditions determine whether this or that variety shall survive. But when man is the selecting agent, we clearly see that the two elements of change are distinct. Variability is in some manner excited, but it is the will of man which accumulates the variations in certain direction, and it is this latter agency which answers to the survival of the fittest under nature. Subchapter: Effects of the increased use and disuse of parts, as controlled by natural selection. From the facts alluded to in the first chapter, I think there can be no doubt that use in our domestic animals has strengthened and enlarged certain parts, and disused diminished them, and that such modifications are inherited. Under free nature, we have no standard of comparison by which to judge of the effects of long continued use or disuse, for we know not the parent forms. But many animals possess structures which can be best explained by the effects of disuse. As Professor Owen has remarked, there is no greater anomaly in nature than a bird that cannot fly. Yet there are several in this state. The logger-headed duck in South America can only flap along the surface of the water, and has its wings in nearly the same condition as a domestic Aylesbury duck. It is a remarkable fact that the younger birds, according to Mr. Cunningham, can fly, while the adults have lost this power. As the larger, ground-feeding birds seldom take flight except to escape danger, it is probable that the nearly wingless condition of several birds now inhabiting, or which lately inhabited several oceanic islands, tenanted by no beasts of prey, has been caused by disuse. The ostrich indeed inhabits continents, and is exposed to danger from which it cannot escape by flight, but it can defend itself by kicking its enemies as efficiently as many quadrupeds. We may believe that the progenitor of the ostrich genus had habits like those of the bustard, and that as the size and weight of its body were increased during successive generations, its legs were used more and its wings less, until they became incapable of flight. Kirby has remarked, and I have observed the same fact, that the anterior tarsi, or feet, of many male dung-feeding beetles are often broken off. He examined 70 specimens in his own collection, and not one had even a relic left. In the Onites apelles, the tarsi are so habitually lost that the insect has been described as not having them. In some other genera they are present, but in a rudimentary condition. in the Antiochus or sacred beetle of the Egyptians, they are totally deficient. The evidence that accidental mutilations can be inherited is at present not decisive, but the remarkable cases observed by Brown-Séquard in Guinea pigs of the inherited effects of operations should make us cautious in denying this tendency. Hence it will perhaps be safest to look at the entire absence of the anterior tarsi in Antiochus, and their rudimentary condition in some other genera, not as cases of inherited mutilations, but as due to the effects of long-continued disuse. For as many dung-feeding beetles are generally found with their tarsi lost, this must happen early in life. Therefore the tarsi cannot be of much importance or be much used by these insects. In some cases we might easily put down to disuse modifications of structure which are wholly or mainly due to natural selection. Mr. Wollaston has discovered the remarkable fact that 200 beetles out of the 550 species, but more are not known, inhabiting Madeira are so far deficient in wings that they cannot fly, and that of the 29 endemic genera, no less than 23 have all their species in this condition. Several facts, namely, that beetles in many parts of the world are very frequently blown to sea and perish, that the beetles in Madeira, as observed by Mr. Wollaston, lie much concealed until the wind lulls and the sun shines, that the proportion of wingless beetles is larger on the exposed deserters than in Madeira itself, and especially the extraordinary fact, so strongly insisted on by Mr. Wollaston, that certain large groups of beetles, elsewhere excessively numerous, which absolutely require the use of their wings, are here almost entirely absent. These several considerations make me believe that the wingless condition of so many Madeira beetles is mainly due to the action of natural selection, combined probably with disuse. For during many successive generations, each individual beetle which flew least, either from its wings having been ever so little less perfectly developed, or from indolent habit, will have had the best chance of surviving from not being blown out to sea, and, on the other hand, those beetles which most readily took to flight would oftenest have been blown to sea, and thus destroyed. The insects in Madeira, which are not ground feeders, and which, as certain flower-feeding Coleoptera and Lepidoptera, must habitually use their wings to gain their subsistence, have, as Mr. Wollaston suspects, their wings not at all reduced, but even enlarged. This is quite compatible with the action of natural selection, for when a new insect first arrives on the island, the tendency of natural selection to enlarge or to reduce the wings would depend on whether a greater number of individuals were saved by successfully battling with the winds, or by giving up the attempt and rarely or never flying. As with mariners shipwrecked near a coast, it would have been better for the good swimmers if they had been able to swim still further, whereas it would have been better for the bad swimmers if they had not been able to swim at all and had stuck to the wreck. The eyes of moles in some burrowing rodents are rudimentary in size, and in some cases are quite covered by skin and fur. This state of the eyes is probably due to gradual reduction from disuse, but aided perhaps by natural selection. In South America, a burrowing rodent, the tucutucu or stenomys, is even more subterranean in its habits than the mole, and I was assured by a Spaniard, who had often caught them, that they were frequently blind. One which I kept alive was certainly in this condition, the cause, as appeared on dissection, having been inflammation of the nictitating membrane. As frequent inflammation of the eyes must be injurious to any animal, and as eyes are certainly not necessary to animals having subterranean habits, a reduction in their size, with the adhesion of the eyelids and growth of fur over them, might, in such case, be an advantage, and if so, natural selection would aid the effects of disuse. It is well known that several animals, belonging to the most different classes, which inhabit the caves of Carniola and Kentucky, are blind. In some of the crabs, the footstalk for the eye remains, though the eye is gone. The stand for the telescope is there, though the telescope with its glasses has been lost. As it is difficult to imagine that eyes, though useless, could be in any way injurious to animals living in darkness, their loss may be attributed to disuse. In one of the blind animals, namely the cave rat, Neotoma, two of which were captured by Professor Silliman at above half a mile distance from the mouth of the cave, and therefore not in the profoundest depth, the eyes were lustrous and of large size, and these animals, as I am informed by Professor Silliman, having been exposed for about a month to graduated light, acquired a dim perception of objects. It is difficult to imagine conditions of life more similar than deep limestone caverns under a nearly similar climate, though that, in accordance with the old view of the blind animals having been separately created for the American and European caverns, very close similarity in their organization and affinities might have been expected. This is certainly not the case if we look at the two whole faunas. With respect to the insects alone, Schiott has remarked, "We are accordingly prevented from considering the entire phenomenon in any other light than something purely local, and the similarity which is exhibited in a few forms between the Mammoth Cave in Kentucky and the caverns in Carniola, otherwise than as a very plain expression of that analogy which subsists generally between the fauna of Europe and North America." On my view, we must suppose that American animals, having in most cases ordinary powers of vision, slowly migrated by successive generations from the outer world into the deeper and deeper recesses of the Kentucky caves, as did European animals into the caves of Europe. We have some evidence of this gradation of habit, for, as Schiott remarks, we accordingly look upon the subterranean faunas as small ramifications which have penetrated into the earth from the geographically limited faunas of the adjacent tracts, and which, as they extended themselves into darkness, have been accommodated to surrounding circumstances. Animals not far remote from ordinary forms prepare the transition from light to darkness. Next follow those that are constructed for twilight, and, last of all, those destined for total darkness, and whose formation is quite peculiar. These remarks of Schiott's, it should be understood, apply not to the same, but to distinct species. By the time that an animal had reached, after numberless generations, the deepest recesses, disuse will on this view have more or less perfectly obliterated its eyes, and natural selection will often have effected other changes, such as an increase in the length of the antennae or palpi, as a compensation for blindness. Notwithstanding such modifications, we might expect still to see in the cave animals of America affinities to the other inhabitants of that continent, and in those of Europe to the inhabitants of the European continent. And this is the case with some of the American cave animals, as I hear from Professor Dana. And some of the European cave insects are very closely allied to those of the surrounding country. It would be difficult to give any rational explanation of the affinities of the blind cave animals to the other inhabitants of the two continents on the ordinary view of their independent creation. That several of the inhabitants of the caves of the Old and the New Worlds should be closely related, we might expect from the well-known relationship of most of their other productions. As a blind species of Bathyscia is found in abundance on shady rocks far from caves, the loss of vision in the cave species of this one genus has probably had no relation to its dark habitation, for it is natural that an insect already deprived of vision should readily become adapted to dark caverns. Another blind genus, Anophthalmus, offers this remarkable peculiarity, that the species, as Mr. Murray observes, have not as yet been found anywhere except in caves. Yet those which inhabit the several caves of Europe and America are distinct. But it is possible that the progenitors of these several species, while they were furnished with eyes, may formerly have ranged over both continents, and then have become extinct, excepting in their present secluded abodes. Far from feeling surprise that some of the cave animals should be very anomalous, as Agassiz has remarked in regard to the blind fish, the Amblyopsis, and as it is the case with the blind Proteus, with reference to the reptiles of Europe, I am only surprised that more wrecks of ancient life have not been preserved, owing to the less severe competition to which the scanty inhabitants of these dark abodes will have been exposed. Subchapter Acclimatization. Habit is hereditary with plants, as in the period of flowering, in the time of sleep, and the amount of rain requisite for seeds to germinate, etc. And this leads me to say a few words on acclimatization, as it is extremely common for distinct species belonging to the same genus to inhabit hot and cold countries. If it be true that all the species of the same genus are descended from a single parent form, acclimatization must be readily effected during a long course of descent. It is notorious that each species is adapted to the climate of its own home. Species from an Arctic or even from a temperate region cannot endure a tropical climate, or conversely. So again, many succulent plants cannot endure a damp climate. But the degree of adaptation of species to the climates under which they live is often overrated. We may infer this from our frequently inability to predict whether or not an imported plant will endure our climate, and from the number of plants and animals brought from different countries which are here perfectly healthy. We have reason to believe that species in a state of nature are closely limited in their ranges by the competition of other organic beings quite as much as, or more than, by adaptation to the particular climates. But whether or not this adaptation is in most cases very close, we have evidence with some few plants of their becoming, to a certain extent, naturally habituated to different temperatures, that is, they become acclimatized. Thus the pines and rhododendrons, raised from seed collected by Dr. Hooker from the same species growing at different heights on the Himalayas, were found to possess in this country different constitutional powers of resisting cold. Mr. Thwaites informs me that he has observed similar facts in Ceylon. Analogous observations have been made by Mr. H. C. Watson on European species of plants brought from the Azores to England, and I could give other cases. In regard to animals, several authentic instances could be adduced of species having largely extended within historical times their range from warmer to colder latitudes, and conversely. But we do not positively know that these animals were strictly adapted to their native climate, though in all ordinary cases we assume such to be the case. nor do we know that they have subsequently become specially acclimatized to their new homes, so as to be better fitted for them than they were at first. As we may infer that our domestic animals were originally chosen by uncivilized man because they were useful, and because they bred readily under confinement, and not because they were subsequently found capable of far extended transportation, the common and extraordinary capacity in our domestic animals of not only withstanding the most different climates, but of being perfectly fertile, a far severer test, under them, may be used as an argument that large proportion of other animals now in a state of nature could easily be brought to bear widely different climates. We must not, however, push the foregoing argument too far, on account of the probable origin of some of our domestic animals from several wild stocks. The blood, for instance, of a tropical and arctic wolf may perhaps be mingled in our domestic breeds. The rat and mouse cannot be considered as domestic animals, but they have been transported by man to many parts of the world, and now have a far wider range than any other rodent. For they live under the cold climate of Faroe in the north and the Falklands in the south, and on many an island in the torrid zones. Hence, adaptation to any special climate may be looked at as a quality readily grafted on an innate wide flexibility of constitution, common to most animals. On this view, the capacity of enduring the most different climates by man himself and by his domestic animals, and the fact of the extinct elephant and rhinoceros having formerly endured a glacial climate, whereas the living species are now all tropical or subtropical in their habits, ought not to be looked at as anomalies, but as examples of a very common flexibility of constitution, brought under peculiar circumstances into action. How much of the acclimatization of species to any peculiar climate is due to mere habit, and how much to the natural selection of varieties having different innate constitutions, and how much to both means combined, is an obscure question. That habit or custom has some influence, I must believe, both from analogy and from the incessant advice given in agricultural works, even in the ancient encyclopedias of China, to be very cautious in transporting animals from one district to another, as it is not likely that man should have succeeded in selecting so many breeds and sub-breeds with constitutions specially fitted for their own districts. The result must, I think, to be due to habit. On the other hand, natural selection would inevitably tend to preserve those individuals which were born with constitutions best adapted to any country which they inhabited. In treatises on many kinds of cultivated plants, certain varieties are said to withstand certain climates better than others. This is strikingly shown in works on fruit trees published in the United States, in which certain varieties are habitually recommended for the northern and others for the southern states. And as most of these varieties are of recent origin, they cannot owe their constitutional differences to habit. The case of the Jerusalem artichoke, which is never propagated in England by seed, and of which, consequently, new varieties have not been produced, has even been advanced as proving that acclimatization cannot be effected, for it is now as tender as ever it was. The case also of the kidney bean has been often cited for a similar purpose, and with much greater weight. But until some one will sow during a score of generations, his kidney beans so early that a very large proportion are destroyed by frost, and then collect seed from the few survivors, with care to prevent accidental crosses, and then again get seed from these seedlings, with the same precautions, the experiment cannot be said to have been tried. Nor let it be supposed that differences in the constitution of seedling kidney beans never appear, for an account has been published how much more hardy some seedlings are than others, and of this fact I have myself observed striking instances. On the whole, we may conclude that habit, or use and disuse, have, in some cases, played a considerable part in the modification of the constitution and structure, but that the effects have often been largely combined with, and sometimes overmastered by, the natural selection of innate variations. Subchapter Correlated Variation. I mean by this expression that the whole organization is so tied together during its growth and development that, when slight variations in any one part occur and are accumulated through natural selection, other parts become modified. This is a very important subject, most imperfectly understood, and no doubt wholly different classes of facts may be here easily confounded together. We shall presently see that simple inheritance often gives the false appearance of correlation. One of the most obvious real cases is that variations of structure arising in the young or larvae naturally tend to affect the structure of the mature animal. The several parts which are homologous and which, at an early embryonic period, are identical in structure, and which are necessarily exposed to similar conditions, seem eminently liable to vary in a like manner. We see this in the right and the left sides of the body varying in the same manner, in the front and the hind legs, and even in the jaws and limbs, varying together, for the lower jaw is believed by some anatomists to be homologous with the limbs. These tendencies, I do not doubt, may be mastered more or less completely by natural selection. Thus, a family of stags once existed with an antler only on one side, and if this had been of any great use to the breed, it might probably have been rendered permanent by natural selection. Homologous parts, as has been remarked by some authors, tend to cohere. This is often seen in monstrous plants, and nothing is more common than the union of homologous parts in normal structures, as in the union of the petals into a tube. Hard parts seem to affect the form of the adjoining soft parts. It is believed by some authors that with birds the diversity in the shape of the pelvis causes the remarkable diversity in the shape of the kidneys. Others believe that the shade of the pelvis in the human mother influences by pressure the shape of the head of the child. In snakes, according to Schlegel, the shape of the body and the manner of swallowing determine the position and form of several of the most important viscera. The nature of the bond is frequently quite obscure. Amice Geoffroy St. Hilaire has forcibly remarked that certain malconformations frequently, and that others rarely, coexist, without our being able to assign any reason. What can be more singular than the relation in cats between complete whiteness and blue eyes with deafness, or between the tortoise shell color and the female sex, or in pigeons between the feathered feet and skin betwixt the outer toes, or between the presence of more or less down on the young pigeon when first hatched, with the future color of its plumage, or again the relation between the hair and the teeth in the naked Turkish dog, though here, no doubt, homology comes into play. With respect to this latter case of correlation, I think it can hardly be accidental that the two orders of mammals, which are most abnormal in their dermal covering, viz. Cetacea, whales, and Edentata, armadillos, scaly anteaters, etc., are likewise on the whole the most abnormal in their teeth, but there are so many exceptions to this rule, as Mr. Mirwart has remarked, that it has little value. I know of no case better adapted to show the importance of the laws of correlation and variation, independently of utility, and therefore of natural selection, than that of the difference between the outer and inner flows in some compositous and ambivalorous plants. Everybody is familiar with the difference between the ray and central florets of, for instance, the daisy, and this difference is often accompanied with a partial or complete abortion of the reproductive organs. But in some of these plants, the seeds also differ in shape and sculpture. These differences have sometimes been attributed to the pressure of the involucra on the florets, or to the mutio pressure, and the shape of the seeds in the ray florets of some compositae countenances this idea. But with the umbelliferæ it is by no means, as Dr. Hooker informs me, the species with the densest heads which most frequently differ in their inner and outer flowers. It might have been thought that the development of the ray petals by drawing nourishment from the reproductive organs causes their abortion. But this can hardly be the sole case, for in some compositae the seeds of the outer and inner florets differ, without any difference in the corolla. Possibly these several differences may be connected with the different flow of nutriment towards the central and external flowers. We know, at least, that with irregular flowers those nearest to the axis are most subject to peloria, that is, to become abnormally symmetrical. I may add, as an instance of this fact, and as a striking case of correlation, that in many pelargoniums the two upper petals and the central flower of the truss often lose their patches of darker colour, and when this occurs, the adherent nectary is quite aborted, the central flower thus becoming peloric or regular. When the colour is absent from only one of the two upper petals, the nectary is not quite aborted, but is much shortened. With respect to the development of the corolla, Sprengel's idea that the ray florets serve to attract insects, whose agency is highly advantageous, or necessary for the fertilization of these plants, is highly probable, and if so, natural selection may have come into play. But, with respect to the seeds, it seems impossible that their differences in shape, which are not always correlated with any difference in the corolla, can be in any way beneficial. Yet, in the umbelliferæ these differences are of such apparent importance, the seeds being sometimes orthospermous in the exterior flowers and coleospermous in the central flowers, that the elder de Candolle founded his main divisions in the order on such characters. Hence, modification of structure, viewed by systematists as of high value, may be wholly due to the laws of variation and correlation, without being, as far as we can judge, of the slightest service to the species. We may often falsely attribute to the correlated variation structures which are common to whole groups of species, and which, in truth, are simply due to inheritance. For an ancient progenitor may have acquired, through natural selection, some one modification in structure, and, after thousands of generations, some other and independent modification, and these two modifications, having been transmitted to a whole group of descendants with diverse habits, would naturally be thought to be, in some necessary manner, correlated. Some other correlations are apparently due to the manner in which natural selection can alone act. For instance, Alf de Candolle has remarked that winged seeds are never found in fruits which do not open. I should explain this rule by the impossibility of seeds gradually becoming winged through natural selection, unless the capsules were open. For in this case alone could the seeds, which were a little better adapted to be wafted by the wind, gain an advantage over others less well fitted for wide dispersal. Subchapter: Compensation and Economy of Growth. The elder Geoffroy and Goethe propounded, at about the same time, their law of compensation or balancement of growth, or, as Goethe expressed it, in order to spend on one side, nature is forced to economize on the other side. I think this holds true to a certain extent with our domestic productions. If nourishment flows to one part or organ in excess, it rarely flows, at least in excess, to another part. Thus it is difficult to get a cow to give much milk and to fatten readily. The same varieties of the cabbage do not yield abundant and nutritious foliage and copious supply of oil-bearing seeds. When the seeds in our fruits become atrophied, gains largely in size and quality. In our poultry, a large tuft of feathers on the head is generally accompanied by a diminished comb, and a large beard by diminished battles. With species in a state of nature, it can hardly be maintained that the law is of a universal application. But many good observers, more especially botanists, believe in this truth. I will not, however, here give any instances, for I see hardly any way of distinguishing between the effects on the one hand of a part being largely developed through natural selection, and another and adjoining part being reduced by the same process or by disuse, and, on the other hand, the actual withdrawal of nutriment from one part owing to the excess of growth in another and adjoining part. I suspect also that some of the cases of compensation which have been advanced, and likewise some other facts, may be merged under a more general principle, namely, that natural selection is continually trying to economize in every part of the organization. If, under changed conditions of life, a structure, before useful, becomes less useful, its diminution will be favored, for it will profit the individual not to have its nutriment wasted in building up a useless structure. I can thus only understand the fact with which I was much struck when examining Cirripedes, and of which many other instances could be given, namely, that when a Cirripede is parasitic within another Cirripede, and is thus protected, it loses more or less completely its own shell or carapace. This is the case with the male Ebla, and in a truly extraordinary manner with the Proteopolis, for the carapace in all other Cirripedes consists of the three highly important anterior segments of the head, enormously developed, and furnished with great nerves and muscles. But in the parasitic and protected Proteopolis, the whole anterior part of the head is reduced to the merest rudiment attached to the basis of the prehensile antennae. Now, the saving of a large and complex structure, when rendered superfluous, would be a decided advantage to each successive individual of the species. For, in the struggle of life to which every animal is exposed, each would have a better chance of supporting itself, by less nutriment being wasted. Thus, as I believe, natural selection will tend in the long run to reduce any part of the organization as soon as it becomes, through changed habits, superfluous, without by any means causing some other part to be largely developed in a corresponding degree, and conversely, that natural selection may perfectly well succeed in largely developing an organ without requiring as a necessary compensation the reduction of some adjoining part. Subchapter: Multiple, rudimentary, and lowly organized structures are variable. It seems to be a rule, as remarked by Is. Geoffroy St. Hilaire, both with varieties and species, that when any part or organ is repeated many times in the same individual, as the vertebrae in snakes and the stamens in polyandrous flowers, the number is variable, whereas the number of the same part or organ, when it occurs in lesser numbers, is constant. The same author, as well as some botanists, have further remarked that multiple parts are extremely liable to vary in structure, as vegetative repetition, to use Professor Owen's expression, is a sign of low organization. The foregoing statements accord with the common opinion of naturalists that beings which stand low in the scale of nature are more variable than those which are higher. I presume that lowness here means that the several parts of the organization have been but little specialized for particular functions, and as long as the same part has to perform diversified work, we can perhaps see why it should remain variable, that is, why natural selection would not have preserved or rejected each little deviation to form so carefully as when the part has to serve for some one special purpose. In the same way as a knife, which has to cut all sorts of things, may be of almost any shape, whilst a tool for some particular purpose must be of some particular shape. Natural selection, it should never be forgotten, can act solely through and for the advantage of each being. Rudimentary parts, as is generally admitted, are apt to be highly variable. We shall have to recur to the subject, and I will here only add that their variability seems to result from their uselessness, and consequently from natural selection having had no power to check deviations in their structure. Subchapter: A part developed in any species in an extraordinary degree or manner, in comparison with the same part in an allied species, tends to be highly variable. Several years ago I was much struck by a remark to the above effect made by Mr. Waterhouse. Professor Owen, also, seems to have come to a nearly similar conclusion. It is hopeless to attempt to convince any one of the truth of the above proposition without giving the long array of facts which I have collected, and which cannot possibly be here introduced. I can only state my conviction that it is a rule of high generality. I am aware of several causes of error, but I hope that I have made due allowances for them. I should be understood that the rule by no means applies to any part, however unusually developed, unless it be unusually developed in one species or in a few species, in comparison with the same part in many closely allied species. Thus the wing of the bat is a most abnormal structure in the class of mammals. But the rule would not apply here, because the whole group of bats possesses wings. It could apply only if some one species had wings developed in a remarkable manner in comparison with the other species of the same genus. The rule applies very strongly in the case of secondary sexual characters, when displayed in any unusual manner. The term secondary sexual characters, used by Hunter, relates to characters which are attached to one sex, but are not directly connected with the act of reproduction. The rule applies to males and females, but more rarely to females, as they seldom offer remarkable secondary sexual characters. The rule being so plainly applicable in the case of secondary sexual characters may be due to the great variability of these characters, whether or not displayed in any unusual manner, of which fact I think there can be little doubt. But that our rule is not confined to secondary sexual characters is clearly shown in the case of hermaphrodite Cirripedes. I particularly attended to Mr. Waterhouse's remark, whilst investigating this order, and I am fully convinced that the rule almost always holds good. I shall, in a future work, give a list of all the more remarkable cases. I will here give only one, as it illustrates the rule in its largest application. The opercular valves of the seal Cirripedes, rock barnacles, are, in every sense of the word, very important structures, and they differ extremely little even in a distinct genera. But in the several species of one genus, Pyrogoma, these valves present a marvellous amount of diversification, the homologous valves in the different species being sometimes wholly unlike in shape, and the amount of variation in the individuals of the same species is so great that it is no exaggeration to state that the varieties of the same species differ more from each other in the characters derived from these important organs than do the species belonging to other distinct genera. As with the birds, the individuals of the same species, inhabiting the same country, vary extremely little. I have particularly attended to them, and the rule certainly seems to hold good in this class. I cannot make out that it applies to plants, and this would have seriously shaken my belief in its truth, had not the great variability in plants made it particularly difficult to compare their relative degree of variability. When we see any part or organ developed in a remarkable degree or manner in a species, the fair presumption is that it is of high importance to that species. Nevertheless, it is in this case eminently liable to variation. Why should this be so? On the view that each species has been independently created, with all its parts as we now see them, I can see no explanation. But on the view that groups of species are descended from some other species and have been modified through natural selection, I think we can obtain some light. First, let me make some preliminary remarks. If, in our domestic animals, any part of the whole animal be neglected, and no selection be applied, that part, for instance, the comb in the Dorking fowl, or the whole breed, will cease to have a uniform character, and the breed may be said to be degenerating. In the rudimentary organs, and in those which have been but little specialized for any particular purpose, and perhaps in polymorphic groups, we can see a nearly parallel case. For in such cases, natural selection either has not or cannot come into full play, and thus the organization is left in a fluctuating condition. But what here more particularly concerns us is that those points in our domestic animals which at the present time are undergoing rapid change by continued selection, are also eminently liable to variation. Look at the individuals on the same breed of the pigeon, and see what a prodigious amount of difference there is in the beak of tumblers, in the beak and wattle of carriers, in the carriage and tail of fantails, etc., these being the points now mainly attended to by English fanciers. Even in the same sub-breed, as in that of the short-faced tumbler, it is notoriously difficult to breed nearly perfect birds, many departing widely from the standard. There may truly be said to be a constant struggle going on between, on the one hand, the tendency to reversion to a less perfect state, as well as an innate tendency to new variations, and, on the other hand, the power of steady selection to keep the breed true. In the long run, selection gains the day, and we do not expect to fail so completely as to breed a bird as coarse as a common tumbler pigeon from a good short-faced strain. But as long as selection is rapidly going on, much variability in the parts undergoing modification may always be expected. Now let us turn to nature. When a part has been developed in an extraordinary manner in any one species, compared with the other species of the same genus, we may conclude that this part has undergone an extraordinary amount of modification since the period when several species branched off from the common progenitor of the genus. This period will seldom be remote in any extreme degree, as species rarely endure for more than one geological period. An extraordinary amount of modification implies an unusually large and long-continued amount of variability, which has continually been accumulated by natural selection for the benefit of the species. But, as the variability of the extraordinary developed part or organ has been so great and long continued, with a period not excessively remote, we might, as a general rule, still expect to find more variability in such parts than in other parts of the organization which have remained for a much longer period nearly constant. And this, I am convinced, is the case, that the struggle between natural selection on the one hand and the tendency to reversion and variability on the other hand will in the course of time cease, and that the most abnormally developed organs may be made constant, I see no reason to doubt. Hence, when an organ, however abnormal it may be, has been transmitted in approximately the same condition to many modified descendants, as in the case of the wing of the bat, it must have existed, according to our theory, for an immense period in nearly the same state, and thus it has come not to be more variable than any other structure. It is only in those cases in which the modification has been comparatively recent and extraordinarily great that we ought to find that generative variability, as it may be called, still present in a high degree. For in this case the variability will seldom as yet have been fixed by the continued selection of the individuals varying in the required manner and degree, and by the continued rejection of those tending to revert to a former and less modified condition. Subchapter: Specific characters more variable than generic characters. The principle discussed under the last heading may be applied to our present subject. It is notorious that specific characters are more variable than generic. To explain by a simple example what is meant: if, in a large genus of plants, some species had blue flowers and some had red, the color would be only a specific character, and no one would be surprised at any one of the blue species varying into red, or conversely. But if all the species had blue flowers, the colour would become a generic character, and its variation would be a more unusual circumstance. I have chosen this example because the explanation which most naturalists would advance is not here applicable, namely, that specific characters are more variable than generic, because they are taken from parts of less physiological importance than those commonly used for classic genera. I believe this explanation is partly, yet not indirectly, true. I shall, however, have to return to this point in the chapter on classification. It would be almost superfluous to adduce evidence in support of the statement that ordinary specific characters are more variable than generic. But with respect to important characters, I have repeatedly noticed in works on natural history that when an author remarks with surprise that some important organ or part, which is generally very constant throughout a large group of species, differs considerably in closely allied species, it is often variable in the individuals of the same species. And this fact shows that a character, which is generally of generic value, when it sinks in value and becomes only of specific value, often becomes variable, though its physiological importance may remain the same. Something of the same kind applies to monstrosities. At least East Geoffroy Saint-Hilaire apparently entertains no doubt that the more an organ normally differs in the different species of the same group, the more subject it is to anomalies in the individuals. On the ordinary view of each species having been independently created, why should that part of the structure which differs from the same part in other independently created species of the same genus be more variable than those parts which are closely alike in the several species? I do not see that any explanation can be given, but on the view that species are only strongly marked and fixed varieties, we might expect often to find them still continuing to vary in those parts of their structure which have varied within a moderately recent period, and which have thus come to differ. Or to state the case in another manner, the points in which all the species of a genus resemble each other, and in which they differ from allied genera, we called generic characters, and these characters have been attributed to inheritance from a common progenitor, for it can rarely have happened that natural selection will have modified several distinct species, fitted to more or less widely different habits, in exactly the same manner. And as these so-called generic characters have been inherited from before the period when the several species first branched off from the common progenitor, and subsequently have not varied or come to differ in any degree, or only in a slight degree, it is not probable that they should vary at the present day. On the other hand, the points in which species differ from other species of the same genus are called specific characters, and that these specific characters have varied and come to differ since the period when the species branched off from a common progenitor, it is probable that they should still often be in some degree variable, at least more variable than those parts of the organization which have for a very long period remained constant. Subchapter: Secondary sexual characters variable. I think it will be admitted by naturalists, without my entering on details, that secondary sexual characters are highly variable. It will also be admitted that species of the same group differ from each other more widely in their secondary sexual characters than other parts of their organization. Compare, for instance, the amount of difference between the males of gallinaceous birds, in which secondary sexual characters are strongly displayed, with the amount of difference between the females. The cause of the original variability of these characters is not manifest, but we can see why they should not have been rendered as constant and uniform as others, for they are accumulated by sexual selection, which is less rigid in its action than ordinary selection, as it does not entail death, but only gives fewer offspring to the less favoured males. Whatever the cause may be of the variability of secondary sexual characters, as they are highly variable, sexual selection will have had a wide scope for action, and may thus have succeeded in giving to the species of the same group a greater amount of difference in these than in other respects. It is a remarkable fact that the secondary differences between the two sexes of the same species are generally displayed in the very same parts of the organization in which the species of the same genus differ from each other. Of this fact I will give, in illustration, the first two instances which happen to stand on my list. And as the differences in these cases are of a very unusual nature, the relation can hardly be accidental. The same number of joints in the tarsi is a character common to very large groups of beetles, but in the Engidae, as Westwood has remarked, the number varies greatly, and the number likewise differs in the two sexes of the same species. Again, in the fossorial Hymenoptera, the neuration of the wings is a character of the highest importance, because common to large groups. But in certain genera the neuration differs in the different species, and likewise in the two sexes of the same species. Sir J. Lubbock has recently remarked that several minute crustaceans offer excellent illustration of this law. In Pontella, for instance, the sexual characters are afforded mainly by the anterior antennae and by the fifth pair of legs. The specific differences also are principally given by these organs. This relation has a clear meaning on my view. I look at all the species of the same genus as having as certainly descended from the same progenitor as have the two sexes of any one species. Consequently, whatever part of the structure of the common progenitor or of its early descendants became variable, variations of this part would, it is highly probable, be taken advantage of by natural and sexual selection, in order to fit the several places in the economy of nature, and likewise to fit the two sexes of the same species to each other, or to fit the males to struggle with other males for the possession of the females. Finally, then, I conclude that the greater variability of specific characters, or those which distinguish species from species, than of generic characters, or those which are possessed by all the species; that the frequent extreme variability of any part which is developed in a species in an extraordinary manner in comparison with the same part in its congeners, and the slight degree of variability in a part, however extraordinarily it may be developed, if it be common to a whole group of species; that the great variability of secondary sexual characters, and their great difference in closely allied species; that secondary sexual and ordinary specific differences are generally displayed in the same parts of the organization, are all principles closely connected together, all being mainly due to the species of the same group being the descendants of a common progenitor, from whom they have inherited much in common, to parts which have recently and largely varied, being more likely still to go on varying than parts which have long been inherited and have not varied, to natural selection having more or less completely, according to the lapse of time, overmastered the tendency to reversion and to further variability, to sexual selection being less rigid than ordinary selection, and to variations in the same parts having been accumulated by natural and sexual selection, and thus having been adapted for secondary sexual and for ordinary purposes. Subchapter: Distinct species present analogous variations, so that a variety of one species often assumes a character proper to an allied species, or reverts to some of the characters of an early progenitor. These propositions will be most readily understood by looking to our domestic races. The most distinct breeds of the pigeon, in countries widely apart, present subvarieties with reversed feathers on the head, and with feathers on their feet, characters not possessed by the aboriginal rock pigeon. These, then, are analogous variations in two or more distinct races. The frequent presence of 14 or even 16 tail feathers in the pouter may be considered as a variation representing the normal structure of another race, the fantail. I presume that no one will doubt that all such analogous variations are due to the several races of the pigeon having inherited from a common parent the same constitution and tendency to variation, when acted on by similar unknown influences. In the vegetable kingdom we have a case of analogous variation, in the enlarged stems, or as commonly called roots, of the Swedish turnip and rutabaga, plants which several botanists rank as varieties produced by cultivation from a common parent. If this be not so, the case will then be one of analogous variation in two so-called distinct species, and to these a third may be added, namely, the common turnip. According to the ordinary view of each species having been independently created, we should have to attribute this similarity in the enlarged stems of these three plants not to the vera causa of community of descent and a consequent tendency to vary in a like manner, but to three separate yet closely related acts of creation. Many similar cases of analogous variation have been observed by Norden in the great gourd family, and by various authors in our cereals. Similar cases occurring with insects under natural conditions have lately been discussed with much ability by Mr. Walsh, who has grouped them under his law of equable variability. With pigeons, however, we have another case, namely, the occasional appearance in all the breeds of slaty blue birds with two black bars on the wings, white loins, a bar at the end of the tail, with the outer feathers externally edged near the bases with white. As all these marks are characteristic of the parent rock pigeon, I presume that no one will doubt that this is a case of reversion, and not of a new yet analogous variation appearing in the several breeds. We may, I think, confidently come to this conclusion, because, as we have seen, these coloured marks are eminently liable to appear in the crossed offspring of two distinct and differently coloured breeds. And in this case there is nothing in the external conditions of life to cause the reappearance of the slaty blue with the several marks, beyond the influence of the mere act of crossing on the laws of inheritance. No doubt, it is a very surprising fact that characters should reappear after having been lost for many, probably for hundreds of generations. But when a breed has been crossed only once by some other breed, the offspring occasionally show for many generations a tendency to revert in character to the foreign breed. Some say for a dozen or even a score of generations. After 12 generations, the proportion of blood, to use a common expression, from one ancestor is only 1 in 2048. And yet, as we see, it is generally believed that a tendency to reversion is retained by this remnant of foreign blood. In a breed which has not been crossed, but in which both parents have lost some character, which their progenitor possessed, the tendency, whether strong or weak, to reproduce the lost character might, as was formerly remarked, for all that we can see, to the contrary, be transmitted for almost any number of generations. When a character which has been lost in a breed reappears after a great number of generations, the most probable hypothesis is not that one individual suddenly takes after an ancestor removed by some 100 generations, but that in each successive generation the character in question has been lying latent, and at last, under unknown favourable conditions, is developed. With the bar pigeon, for instance, which very rarely produces a blue bird, it is probable that there is a latent tendency in each generation to produce blue plumage. The abstract improbability of such a tendency being transmitted through a vast number of generations is not greater than that of quite useless or rudimentary organs being similarly transmitted. A mere tendency to produce a rudiment is indeed sometimes thus inherited. As all the species of the same genus are supposed to be descended from a common progenitor, it might be expected that they would occasionally vary in an analogous manner, so that the varieties of two or more species would resemble each other, or that a variety of one species would resemble in certain characters an other and distinct species, this other species being, according to our view, only a well-marked and permanent variety. But characters exclusively due to analogous variation would probably be of an unimportant nature. For the preservation of all functionally important characters will have been determined through natural selection, in accordance with the different habits of the species. It might further be expected that the species of the same genus would occasionally exhibit reversions to long-lost characters. As, however, we do not know the common ancestor of any natural group, we cannot distinguish between reversionary and analogous characters. If, for instance, we did not know that the parent rock pigeon was not feather-footed or tern-crowned, we could not have told whether such characters in our domestic breeds were reversions or only analogous variations. But we might have inferred that the blue colour was a case of reversion from the number of the markings, which are correlated with this tint, and which would not probably have all appeared together from simple variation. More especially, we might have inferred this from the blue colour and the several marks so often appearing when differently coloured breeds are crossed. Hence, although under nature it must generally be left doubtful what cases are reversions to formerly existing characters, and what are new but analogous variations, yet we ought, in our theory, sometimes to find the varying offspring of a species assuming characters which are already present in other members of the same group. And this undoubtedly is the case. The difficulty in distinguishing variable species is largely due to the varieties mocking, as it were, other species of the same genus. A considerable catalogue also could be given in forms of intermediate between two other forms, which themselves can only doubtfully be ranked as species. And this shows, unless all these closely allied forms be considered as independently created species, that they have in varying assumed some of the characters of the others. But the best evidence of analogous variations is afforded by parts or organs which are generally constant in character, but which occasionally vary so as to resemble, in some degree, the same part or organ in an allied species. I have collected a long list of such cases, but here, as before, I lie under the great disadvantage of not being able to give them. I can only repeat that such cases certainly occur, and seem to me very remarkable. I will, however, give one curious and complex case, not indeed as affecting any important character, but from occurring in several species of the same genus, partly under domestication and partly under nature. It is a case almost certainly of reversion. The ass sometimes has very distinct transverse bars on its legs, like those of the legs of a zebra. It has been asserted that these are plainest in the foal, and from inquiries which I have made, I believe this to be true. The stripe on the shoulder is sometimes double, and is very variable in length and outline. A white ass, but not an albino, has been described without either spinal or shoulder stripe, and these stripes are sometimes very obscure, or actually quite lost in dark-coloured asses. The colline of Pallas is said to have been seen with a double shoulder stripe. Mr. Blight has seen a specimen of the Hemionus with a distinct shoulder stripe, though it properly has none, and I have been informed by Colonel Poole that foals of this species are generally striped on the legs and faintly on the shoulder. The quagga, though plainly barred like a zebra over the body, is without bars on the legs. But Dr. Gray has figured one specimen with very distinct zebra-like bars on the hooks. With respect to the horse, I have collected cases in England of the spinal stripe in horses of the most distinct breeds, and of all colours. Transverse bars on the legs are not rare in duns, mouse duns, and in one instance in a chestnut. A faint shoulder stripe may sometimes be seen in duns, and I have seen a trace in a bay horse. My son made a careful examination and sketch for me of a dun Belgian cart horse, with a double stripe on each shoulder and with leg stripes. I have myself seen a dun Devonshire pony, and a small dun Welsh pony has been carefully described to me, both with 3 parallel stripes on each shoulder. In the northwest part of India, the Kathiawar breed of horses is so generally striped that, as I hear from Colonel Poole, who examined these breeds for the Indian government, a horse without stripes is not considered as purely bred. The spine is always striped, the legs are generally barred, and the shoulder stripe, which is sometimes double and sometimes treble, is common. The side of the face, moreover, is sometimes striped. The stripes are often plainest in the foal, and sometimes quite disappear in old horses. Colonel Poole has seen both grey and bay Kathiawar horses striped when first foaled. I have also reason to suspect, from information given me by Mr. W. W. Edwards, that with the English race horse the spinal stripe is much commoner in the foal than in the full-grown animal. I have myself recently bred a foal from a bay mare, offspring of a Turkoman horse and a Flemish mare, by a bay English racehorse. This foal, when a week old, was marked on its hinder quarters and on its forehead with numerous very narrow, dark, zebra-like bars, and its legs were feebly striped. All the stripes soon disappeared completely. Without here entering on further details, I may state that I have collected cases of leg and shoulder stripes in horses of very different breeds in various countries, from Britain to eastern China, and from Norway in the north to the Malay archipelago in the south. In all parts of the world these stripes occur, far oftenest in duns and mouse duns. By the term dun a large range of colour is included, from one between brown and black to a close approach to cream colour. I am aware that Colonel Hamilton Smith, who has written on this subject, believes that the several breeds of the horse are descended from several aboriginal species, one of which, the dun, was striped, and that the above described appearances are all due to ancient crosses with the dun stock. But this view may be safely rejected, for it is highly improbable that the heavy Belgian cart horse, Welsh ponies, Norwegian cobs, the lanky Catawar race, etc., inhabiting the most distant parts of the world, should all have been crossed with one supposed aboriginal stock. Now let us turn to the effects of crossing the several species of the horse genus. Rowland asserts that the common mule from the ass and horse is particularly apt to have bars on its legs. According to Mr. Goss, in certain parts of the United States, about 9 out of 10 mules have striped legs. I once saw a mule with its legs so much striped that anyone might have thought it was a hybrid zebra. And Mr. W. C. Martin, in his excellent treatise on the horse, has given a figure of a similar mule. In 4 coloured drawings, which I have seen, of hybrids between the ass and zebra, the legs were much more plainly barred than the rest of the body, and in one of them there was a double shoulder stripe. In Lord Morton's famous hybrid from a chestnut mare and male quagga, the hybrid and even the pure offspring subsequently produced from the same mare by a black Arabian sire, were much more plainly barred across the legs than is even the pure quagga. Lastly, and this is another most remarkable case, a hybrid has been figured by Dr. Gray, and he informs me that he knows of a second case, from the ass and the Miscellaneous. And this hybrid, though the ass only occasionally has stripes on his legs, and the Miscellaneous has none, and has not even a shoulder stripe, nevertheless had all 4 legs barred, and had 3 short shoulder stripes, like those on the dun Devonshire and Welsh ponies, and even had some zebra-like stripes on the side of its face. With respect to this last fact, I was so convinced that not even a stripe of colour appears from what is commonly called chance, that I was led solely from the occurrence of the face stripes on this hybrid, from the ass and Miscellaneous, to ask Colonel Poole whether such face stripes ever occurred in the eminently striped Catawar breed of horses, and was, as we have seen, answered in the affirmative. What now are we to say to these several facts? We see several distinct species of the horse genus becoming, by simple variation, striped on the legs like a zebra, or striped on the shoulders like an ass. In the horse we see this tendency strong whenever a dun tint appears, a tint which approaches to that of the general colouring of the other species of the genus. The appearance of the stripes is not accompanied by any change of form or by any other new character. We see this tendency to become striped most strongly displayed in hybrids from between several of the most distinct species. Now observe the case of the several breeds of pigeons. They are descended from a pigeon, including 2 or 3 subspecies or geographical races, of a bluish color with certain bars and other marks, and when any breed assumes by simple variation a bluish tint, these bars and other marks invariably reappear, but without any other change of form or character. When the oldest and truest breeds of various colors are crossed, we see a strong tendency for the blue tint and bars and marks to reappear in the mongrels. I have stated that the most probable hypothesis to account for the reappearance of very ancient characters is that there is a tendency in the young of each successive generation to produce the long-lost character, and that this tendency, from unknown causes, sometimes prevails. And we have just seen that in several species of the horse genus the stripes are either plainer or appear more commonly in the young than in the old. Call the breeds of pigeons, some of which have bred true for centuries, species. And how exactly parallel is the case with that of the species of the horse genus? For myself, I venture confidently to look back thousands on thousands of generations, and I see an animal striped like a zebra, but perhaps otherwise very differently constructed, the common parent of our domestic horse, whether or not it be descended from one or more wild stocks, of the ass, the Miscellaneous, quagga, and zebra. He who believes that each equine species was independently created will, I presume, assert that each species has been created with the tendency to vary, both under nature and under domestication, in this particular manner, so as often to become striped like the other species of the genus, and that each has been created with a strong tendency, when crossed with species inhabiting distant quarters of the world, to produce hybrids resembling their stripes, not their own parents, but other species of the genus. To admit this view is, as it seems to me, to reject a real for an unreal, or at least for an unknown cause. It makes the works of God a mere mockery and deception. I would almost as soon believe with the old and ignorant cosmogonics that fossil shells had never lived, but had been created in stone so as to mock the shells now living on the seashore. Subchapter Summary. Our ignorance of the laws of variation is profound. Not in one case out of 100 can we pretend to assign any reason why this or that part has varied. But whenever we have the means of instituting a comparison, the same laws appear to have acted in producing the lesser differences between varieties of the same species, and the greater differences between species of the same genus. Changed conditions generally induce mere fluctuating variability, but sometimes they cause direct and definite effects, and these may become strongly marked in the course of time, though we have not sufficient evidence on this head. Habit in producing constitutional peculiarities, and use in strengthening, and disuse in weakening and diminishing organs, appear in many cases to have been potent in their effects. Homologous parts tend to vary in the same manner, and homologous parts tend to cohere. Modification in hard parts and in external parts sometimes affect softer and internal parts. When one part is largely developed, perhaps it tends to draw nourishment from the adjoining parts, and every part of the structure which can be saved without detriment will be saved. Changes of structure at an early age may affect parts subsequently developed, and many cases of correlated variation, the nature of which we are unable to understand, undoubtedly occur. Multiple parts are variable in number and in structure, perhaps arising from such parts not having been closely specialized for any particular function, so that their modifications have not been closely checked by natural selection. It follows probably from this same cause that organic beings low in the scale are more variable than those standing higher in the scale, and which have their whole organization more specialized. Rudimentary organs, from being useless, are not regulated by natural selection, and hence are variable. Specific characters, that is, the characters which have come to differ since the several species of the same genus branched off from a common parent, are more variable than generic characters, or those which have long been inherited and have not differed within the same period. In these remarks we have referred to special parts or organs being still variable, because they have recently varied and thus come to differ. But we have also seen in the second chapter that the same principle applies to the whole individual. For in a district where many species of a genus are found, that is, where there has been much former variation and differentiation, or where the manufactory of new specific forms has been actively at work, in that district and among these species, we now find, on an average, most varieties. Secondary sexual characters are highly variable, and such characters differ much in the species of the same group. Variability in the same part of the organization has generally been taken advantage of in giving secondary sexual differences to the two sexes of the same species, and specific differences to the several species of the same genus. Any part or organ developed in an extraordinary size or in an extraordinary manner in comparison with the same part or organ in the allied species must have gone through an extraordinary amount of modification since the genus arose. And thus we can understand why it should often still be variable in a much higher degree than other parts. For variation is a long continued and slow process, and natural selection will in such cases not as yet have had time to overcome the tendency to further variability and to reversion to a less modified state. But when a species with an extraordinarily developed organ has become the parent of many modified descendants, which, on our view, must be a very slow process, requiring a long lapse of time, in this case, natural selection has succeeded in giving a fixed character to the organ, in however extraordinary a manner it may have been developed. Species inheriting nearly the same constitution from a common parent and exposed to similar influences naturally tend to present analogous variations, or these same species may occasionally revert to some of the characters of their ancient progenitors. Although new and important modifications may not arise from reversion and analogous variation, such modifications will add to the beautiful and harmonious diversity of nature. Whatever the cause may be of each slight difference between the offspring and their parents, and a cause for each must exist, we have reason to believe that it is the steady accumulation of beneficial differences which has given rise to all the more important modifications of structure in relation to the habits of each species. End of Chapter 5. Laws of Variation.
The Origin of Species by Means of Natural Selection, or the Preservation of Favoured Races in the Struggle for Life. 6th London edition, by Charles Darwin. Chapter number 6.
Part 1.
Difficulties of the Theory. Chapter contents include difficulties of the theory of descent with modification, absence or rarity of transitional varieties, transitions in habits of life, diversified habits in the same species, species with habits widely different from those of their allies, organs of extreme perfection, modes of transition, cases of difficulty, natura non fecit saltum, organs of small importance, organs not in all cases absolutely perfect, the law of unity of type, and of the conditions of existence embraced by the theory of natural selection. Long before the reader has arrived at this part of my work, a crowd of difficulties will have occurred to him. Some of them are so serious that to this day I can hardly reflect on them without being in some degree staggered. But, to the best of my judgment, the greater number are only apparent, and those that are real are not, I think, fatal to the theory. These difficulties and objections may be classed under the following heads. First, why, if species have descended from other species by fine gradations, do we not everywhere see innumerable transitional forms? Why is not all nature in confusion, instead of the species being, as we see them, well defined? Secondly, is it possible that an animal having, for instance, the structure and habits of a bat could have been formed by the modification of some other animal with widely different habits and structure? Can we believe that natural selection could produce, on the one hand, an organ of trifling importance, such as the tail of a giraffe, which serves as a fly flapper, and, on the other hand, an organ so wonderful as the eye? Thirdly, can instincts be acquired and modified through natural selection? What shall we say to the instinct which leads the bee to make cells, and which has practically anticipated the discoveries of profound mathematicians? Fourthly, how can we account for species, when crossed, being sterile and producing sterile offspring, whereas, when varieties are crossed, their fertility is unimpaired? The first two heads will be here discussed. Some miscellaneous objections in the following chapter, instinct and hybridism in the two succeeding chapters. On the absence or rarity of transitional varieties. As natural selection acts solely by the preservation of profitable modifications, each new form will tend in a fully stocked country to take the place of, and finally to exterminate, its own less improved parent form and other less favoured forms with which it comes into competition. Thus extinction and natural selection go hand in hand. Hence, if we look at each species as descended from some unknown form, both the parent and all the transitional varieties will generally have been exterminated by the very process of the formation and perfection of the new form. But, as by this theory innumerable transitional forms must have existed, why do we not find them embedded in countless numbers in the crust of the earth? It will be more convenient to discuss this question in the chapter on the imperfection of the geological record, and I will here only state that I believe the answer mainly lies in the record being incomparably less perfect than is generally supposed. The crust of the earth is a vast museum, but the natural collections have been imperfectly made, and only at long intervals of time. But it may be urged that when several closely allied species inhabit the same territory, we surely ought to find at the present time many transitional forms. Let us take a simple case. In traveling from north to south over a continent, we generally meet at successive intervals with closely allied or representative species, evidently filling nearly the same place in the natural economy of the land. These representative species often meet and interlock. And as the one becomes rarer and rarer, the other becomes more and more frequent, till the one replaces the other. But if we compare these species where they intermingle, they are generally as absolutely distinct from each other in every detail of structure as are specimens taken from the metropolis inhabited by each. By my theory, these allied species are descended from a common parent, and during the process of modification, each has become adapted to the conditions of life of its own region, and has supplanted and exterminated its original parent form and all the transitional varieties between its past and present states. Hence, we ought not to expect at the present time to meet with numerous transitional varieties in each region, though they must have existed there, and may be embedded there in a fossil condition. But in the intermediate region, having intermediate conditions of life, why do we not now find closely linking intermediate varieties? This difficulty for a long time quite confounded me, but I think it can be in the large part explained. In the first place, we should be extremely cautious in inferring, because an area is now continuous, that it has been continuous during a long period. Geology would lead us to believe that most continents have been broken up into islands even during the later tertiary periods, and in such islands distinct species might have been separately formed without the possibility of intermediate varieties existing in the intermediate zones. By changes in the form of the land and of the climate, marine areas now continuous must often have existed within recent times in a far less continuous and uniform condition than at present. But I will pass over this way of escaping from the difficulty, for I believe that many perfectly defined species have been formed on strictly continuous areas, though I do not doubt that the formerly broken condition of areas now continuous has played an important part in the formation of new species, more especially with freely crossing and wandering animals. In looking at species as they are now distributed over a wide area, we generally find them tolerably numerous over a large territory, then becoming somewhat abruptly rarer and rarer on the confines, and finally disappearing. Hence the neutral territory between two representative species is generally narrow in comparison with the territory proper to each. We see the same fact in ascending mountains, and sometimes it is quite remarkable how abruptly, as Alpha de Candolle has observed, a common alpine species disappears. The same fact has been noted by E. Forbes in sounding the depths of the sea with the dredge. To those who look at climate and the physical conditions of life as the all-important elements of distribution, these facts ought to cause surprise, as climate and height or depth graduate away insensibly. But when we bear in mind that almost every species, even in its metropolis, would increase immensely in numbers were it not for other competing species, that nearly all either prey on or serve as prey for others, in short, that each organic being is either directly or indirectly related in the most important manner to other organic beings, we see that the range of the inhabitants of any country by no means exclusively depends on insensibly changing physical conditions, but in large part on the presence of other species on which it lives, or by which it is destroyed, or with which it comes into competition. And as these species are already defined objects, not blending one into another by insensible gradations, the range of any one species, depending as it does on the range of others, will tend to be sharply defined. Moreover, each species on the confines of its range, where it exists in lessened numbers, will, during fluctuations in the number of its enemies or of its prey, or in the nature of the seasons, be extremely liable to utter extermination, and thus its geographical range will come to be still more sharply defined. As allied or representative species, when inhabiting a continuous area, are generally distributed in such a manner that each has a wide range, with a comparatively narrow neutral territory between them, in which they become rather suddenly rarer and rarer. As varieties do not essentially differ from species, the same rule will probably apply to both. And if we take a varying species inhabiting a very large area, we shall have to adapt two varieties to two large areas, and a third variety to a narrow intermediate zone. The intermediate variety, consequently, will exist in lesser numbers from inhabiting a narrow and lesser area, and practically, as far as I can make out, this rule holds good with varieties in a state of nature, I have met with striking instances of the rule in the case of varieties intermediate between well-marked varieties in the genus Balanus. And it would appear from information given me by Mr. Watson, Dr. Asa Gray, and Mr. Wollaston, that generally, when varieties intermediate between two other forms occur, they are much rarer numerically than the forms which they connect. Now, if we may trust these facts and inferences, and conclude that varieties linking two other varieties together generally have existed in lesser numbers than the forms which they connect, then we can understand why intermediate varieties should not endure for very long periods, why, as a general rule, they should be exterminated and disappear sooner than the forms which they originally linked together. For any form existing in lesser numbers would, as already remarked, run a greater chance of being exterminated than one existing in large numbers, and in this particular case, the intermediate form would be eminently liable to the inroads of closely allied forms existing on both sides of it. But it is a far more important consideration that, during the process of further modification, by which two varieties are supposed to be converted and perfected into two distinct species, the two which exist in larger numbers, from inhabiting larger areas, will have a great advantage over the intermediate variety, which exists in smaller numbers in a narrow and intermediate zone. For forms existing in larger numbers will have a better chance, within any given period, of presenting further favorable variations for natural selection to seize on, than will the rarer forms which exist in lesser numbers. Hence, the more common forms, in the race for life, will tend to beat and supplant the less common forms, for these will be more slowly modified and improved. It is the same principle which, as I believe, accounts for the common species in each country, as shown in the second chapter, presenting on an average a greater number of well-marked varieties than do the rarer species. I may illustrate what I mean by supposing 3 varieties of sheep to be kept, one adapted to an extensive mountainous region, a second to a comparatively narrow hilly tract, and a third to the wide plains of the base, and that the inhabitants are all trying with equal steadiness and skill to improve their stocks by selection. The chances in this case will be strongly in favor of the great holders on the mountains or on the plains improving their breeds more quickly than the small holders on the intermediate narrow, hilly tract. And consequently the improved mountain or plain breed will soon take the place of the less improved hill breed, and thus the two breeds, which originally existed in greater numbers, will come into close contact with each other, without the interposition of the supplanted intermediate hill variety. To sum up, I believe that species come to be tolerably well-defined objects, and do not at any one period present an inextricable chaos of varying intermediate links. First, because new varieties are very slowly formed, for variation is a slow process and natural selection can do nothing until favorable individual differences or variations occur, and until a place in the natural polity of a country can be better fitted by some modification of some one or more of its inhabitants. And such new places will depend on slow changes of climate, or on the occasional immigration of new inhabitants, and probably, in a still more important degree, on some of the old inhabitants becoming slowly modified, with the new forms thus produced and the old ones acting and reacting on each other. So that, in any one region and at any one time, we ought to see only a few species presenting slight modifications of structure in some degree permanent, and this, assuredly, we do see. Secondly, areas now continuous must often have existed within the recent period as isolated portions, in which many forms, more especially among the classes which unite for each birth and wander much, may have separately been rendered sufficiently distinct to rank as a representative species. In this case, intermediate varieties between the several representative species and their common parent must formerly have existed within each isolated portion of the land, but these links during the process of natural selection will have been supplanted and exterminated, so that they will no longer be found in a living state. Thirdly, when 2 or more varieties have been formed in different portions of a strictly continuous area, intermediate varieties will, it is probable, at first have been formed in the intermediate zones, but they will generally have had a short duration. For these intermediate varieties will, from reasons already assigned, namely from what we know of the actual distribution of closely allied or representative species, and likewise of acknowledged varieties, exist in the intermediate zones in lesser numbers than the varieties which they tend to connect. From this cause alone the intermediate varieties will be liable to accidental extermination, and during the process of further modification through natural selection, they will almost certainly be beaten and supplanted by the forms which they connect, for these, from existing in greater numbers, will, in the aggregate, present more varieties and thus be further improved through natural selection and gain further advantages. Lastly, looking not to any one time, but at all time, if my theory be true, numberless intermediate varieties, linking closely together all the species of the same group, must assuredly have existed. But the very process of natural selection constantly tends, as has been so often remarked, to exterminate the parent forms in the intermediate links. Consequently, evidence of their former existence could be found only among fossil remains, which are preserved, as we shall attempt to show in a future chapter, in an extremely imperfect and intermittent record. On the origin and transition of organic beings with peculiar habits and structure. It has been asked by the opponents of such views as I hold, how, for instance, could a land carnivorous animal have been converted into one with aquatic habits? For how could the animal in its transitional state have subsisted? It would be easy to show that there now exist carnivorous animals presenting close intermediate grades from strictly terrestrial to aquatic habits, and, as each exists by a struggle for life, it is clear that each must be well adapted to its place in nature. Look at the Mustela vison of North America, which has webbed feet, and which resembles an otter in its fur, short legs, and form of tail. During summer this animal dives for and preys on fish, but during the long winter it leaves the frozen waters and preys, like other polecats, on mice and land animals. If a different case had been taken, and it had been asked how an insectivorous quadruped could possibly have converted into a flying bat, the question would have been far more difficult to answer. Yet I think such difficulties have little weight. Here, as on other occasions, I lie under a heavy disadvantage, for out of the many striking cases which I have collected, I can only give one or two instances of transitional habits and structures in allied species, and of diversified habits, either consonant or occasional, in the same species, and it seems to me that nothing less than a long list of such cases is sufficient to lessen the difficulty in any particular case like that of the bat. Look at the family of squirrels. Here we have the finest gradation from animals with their tails only slightly flattened, and from others, as Sir Richardson has remarked, with the posterior part of their bodies rather wide and with the skin on their flanks rather full, to the so-called flying squirrels. And flying squirrels have their limbs and even the base of the tail united by a broad expanse of skin, which serves as a parachute and allows them to glide through the air to an astonishing distance from tree to tree. We cannot doubt that each structure is of use to each kind of squirrel in its own country, by enabling it to escape birds or beasts of prey, or to collect food more quickly, or, as there is reason to believe, to lessen the danger from occasional falls. But it does not follow from this fact that the structure of each squirrel is the best that it is possible to conceive under all possible conditions. Let the climate and vegetation change, let other competing rodents or new beasts of prey immigrate, or old ones become modified, and all analogy would lead us to believe that some, at least, of the squirrels would decrease in numbers or become exterminated, unless they also become modified and improved in structure in a corresponding manner. Therefore, I can see no difficulty, more especially under changing conditions of life, in the continued preservation of individuals with fuller and fuller flank membranes, each modification being useful, each being propagated, until by the accumulated effects of this process of natural selection, a perfect so-called flying squirrel was produced. Now look at the Galeopithecus, or the so-called flying lemur, which was formerly ranked among bats, but is now believed to belong to the Insectivoria. An extremely wide flank membrane stretches from the corner of the jaw to the tail, and includes the limbs with elongated fingers. This flank membrane is furnished with an extensor muscle. Although no graduated links of structure, fitted for gliding through the air, now collect the Galeopithecus with other insectivora, yet there is no difficulty in supposing that such links formerly existed, and that each was developed in the same manner as with the less perfectly gliding squirrels, each grade of structure having been useful to its possessor. Nor can I see any insuperable difficulty in further believing it possible that the membrane-connected fingers and forearm of the Galeopithecus might have been greatly lengthened by natural selection, and this, as far as the organs of flight are concerned, would have converted the animal into a bat. In certain bats, in which the wing membrane extends from the top of the shoulder to the tail and includes the hind legs, we perhaps see traces of an apparatus originally fitted for gliding through the air rather than for flight. If about a dozen genera of birds were to become extinct, who would have ventured to surmise that birds might have existed which used their wings solely as flappers, like the logger-headed duck, Micropterus of Eyton, as fins in the water and as front legs on the land, like the penguin, as sails, like the ostrich, and functionally for no purpose, like the apterus? Yet the structure of each of these birds is good for it, under the conditions of life to which it is exposed, for each has to live by a struggle, but it is not necessarily the best possible under all possible conditions. It must not be inferred from these remarks that any of the grades of wing structure here alluded to, which perhaps may all be the result of disuse, indicate the steps by which birds actually acquire their perfect power of flight, but they serve to show what diversified means of transition are at least possible. Seeing a few members of such water-breeding classes as the Crustacea and Mollusca are adapted to live on the land, and seeing that we have flying birds and mammals, flying insects of the most diversified types, and formerly had flying reptiles, it is conceivable that flying fish, which now glide far through the air, slightly rising and turning by the aid of their fluttering fins, might have been modified into perfectly winged animals. If this had been effected, who would have ever imagined that in an early transitional state they had been inhabitants of the open ocean, and had used their incipient organs of flight exclusively, so far as we know, to escape being devoured by other fish? When we see any structure highly perfected for any particular habit, as the wings of a bird for flight, we should bear in mind that animals displaying early transitional grades of the structure will seldom have survived to the present day, for they will have been supplanted by their successors, which were gradually rendered more perfect through natural selection. Furthermore, we may conclude that transitional states between structures fitted for very different habits of life will rarely have been developed at an early period in great numbers and under many subordinate forms. Thus, to return to our imaginary illustration of the flying fish, it does not seem probable that fishes capable of true flight would have been developed under many subordinate forms, for taking prey of many kinds in many ways, on the land and in the water, until their organs of flight had come to a high stage of perfection, so as to have given them a decided advantage over other animals in the battle for life. Hence the chance of discovering species with transitional grades of structure in a fossil condition will always be less, from their having existed in lesser numbers, than in the case of species with fully developed structures. I will now give 2 or 3 instances, both of diversified and of changed habits, in the individuals of the same species. In either case it would be easy for natural selection to adapt the structure of the animal to its changed habits, or exclusively to one of its several habits. It is, however, difficult to decide and immaterial for us whether habits generally change first and structure afterwards, or whether slight modifications of structure lead to changed habits, both probably often occurring almost simultaneously. Of cases of changed habits, it will suffice merely to allude to that of the many British insects which now feed on exotic plants, or exclusively on artificial substances. Of diversified habits innumerable instances could be given. I have often watched a tyrant flycatcher, Saurophagus sulphuratus, in South America, hovering over one spot and then proceeding to another, like a kestrel, and at other times standing stationary on the margin of water, and then dashing into it like a kingfisher at a fish. In our own country the larger titmouse, Parus major, may be seen climbing branches, almost like a creeper. It sometimes, like a shrike, kills small birds by blows on the head, and I have many times seen and heard it hammering the seeds of the yew on a branch, and thus breaking them like a nuthatch. In North America the black bear was seen by herds swimming for hours with widely open mouth, thus catching, almost like a whale, insects in the water. As we sometimes see individuals following habits different from those proper to their species and to the other species of the same genus, we might expect that such individuals would occasionally give rise to new species, having anomalous habits, and with their structure either slightly or considerably modified from that of their type. And such instances occur in nature. Can a more striking instance of adaptation be given than that of a woodpecker for climbing trees and seizing insects in the chinks of the bark? Yet in North America there are woodpeckers which feed largely on fruit, and others with elongated wings which chase insects on the wing. On the plains of La Plata, where hardly a tree grows, There is a woodpecker, Colaptes campestris, which has 2 toes before and 2 behind, a long pointed tongue, pointed tail feathers, sufficiently stiff to support the bird in a vertical position on a post, but not so stiff as in the typical woodpeckers, and a straight, strong beak. The beak, however, is not so straight or so strong as in the typical woodpeckers, but is strong enough to bore into wood. Hence this Colaptes, in all the essential parts of its structure, is a woodpecker. Even in such trifling characters as the colouring, the harsh tone of the voice, and undulatory flight, its close blood relationship to our common woodpecker is plainly declared. Yet, as I can assert, not only from my own observations, but from those of the accurate Azara, in certain large districts it does not climb trees, and it makes its nest in holes and banks. In certain other districts, however, this same woodpecker, as Mr. Hudson states, frequents trees, and bores holes in the trunk for its nest. I may mention as another illustration of the varied habits of this genus, that a Mexican Colaptes has been described by de Saussure as boring holes into hard wood in order to lay up a store of acorns. Petrels are the most aerial and oceanic of birds, but, in the quiet sounds of Tierra del Fuego, the Puffonuria berardi, in its general habits, in its astonishing power of diving, in its manner of swimming and flying when made to take flight, would be mistaken by anyone for an auk or a grebe. Nevertheless, it is essentially a petrel, but with many parts of its organization profoundly modified in relation to its new habits of life. Whereas the woodpecker of La Plata has had its structure only slightly modified. In the case of the water ouzel, the acutest observer, by examining its dead body, would never have suspected its subaquatic habits, yet this bird, which is allied to the thrush family, subsists by diving, using its wings under water and grasping stones with its feet. All the members of the great order of Hymenopterous insects are terrestrial, excepting the genus Proctotrupes, which Sir John Lubbock has discovered to be aquatic in its habits. It often enters the water and dives about by the use not of its legs but of its wings, and remains as long as 4 hours beneath the surface, yet it exhibits no modification in structure in accordance with its abnormal habits. He who believes that each being has been created as we now see it, must occasionally have felt surprise when he has met with an animal having habits and structure not in agreement. What can be plainer than that the webbed feet of ducks and geese are formed for swimming? Yet there are upland geese with webbed feet which rarely go near the water, and no one except Audubon has seen the frigate bird, which has all its 4 toes webbed, alight on the surface of the ocean. On the other hand, grebes and coots are eminently aquatic, although their toes are only bordered by membrane. What seems plainer than that the long toes, not furnished with membrane, of the grallatorers, are formed for walking over swamps and floating plants? The water-hen and landrail are members of this order, yet the first is nearly as aquatic as the coot, and the second is nearly as terrestrial as the quail or partridge. In such cases, and many others could be given, habits have changed without a corresponding change of structure. The webbed feet of the upland goose may be said to have become almost rudimentary in function, though not in structure. In the frigate bird, the deeply scooped membrane between the toes shows that structure has begun to change. He who believes in separate and innumerable acts of creation may say that, in these cases, it has pleased the Creator to cause a being of one type to take the place of one belonging to another type. But this seems to me only restating the fact in dignified language. He who believes in the struggle for existence and in the principle of natural selection will acknowledge that every organic being is constantly endeavouring to increase its numbers, and that if any one being varies ever so little, either in habits or structure, and thus gains an advantage over some other inhabitant of the same country, it will seize on the place of that inhabitant, however different that may be from its own place. Hence it will cause them no surprise if there should be geese and frigate birds with webbed feet, living on the dry land and rarely alighting on the water, that there should be long-toed corncrakes, living in meadows instead of in swamps, that there should be woodpeckers where hardly a tree grows, that there should be diving thrushes and diving hymenoptera, and petrels with the habits of auks. Organs of extreme perfection and complication. To suppose that the eye, with all its inimitable contrivances for adjusting the focus to different distances, for admitting different amounts of light, and for the correction of spherical and chromatic aberration, could have been formed by natural selection, seems, I freely confess, absurd in the highest degree. When it was first said that the sun stood still and the world turned round, the common sense of mankind declared the doctrine false. But the old saying of vox populi, vox Dei, as every philosopher knows, cannot be trusted in science. Reason tells me that if numerous gradations from a simple and imperfect eye to one complex and perfect can be shown to exist, each grade being useful to its possessor, as is certainly the case, if further the eye ever varies and the variations be inherited, as is likewise certainly the case, and if such variations should be useful to any animal under changing conditions of life, then the difficulty of believing that a perfect and complex eye could be formed by natural selection, though insuperable by our imagination, should not be considered as subversive of the theory. How a nerve comes to be sensitive to light hardly concerns us more than how life itself originated. But I may remark that, as some of the lowest organisms in which nerves cannot be detected are capable of perceiving light, it does not seem impossible that certain sensitive elements in their sarcode should become aggregated and developed into nerves, endowed with this special sensibility. In searching for the gradations through which an organ in any species has been perfected, we ought to look exclusively to its lineal progenitors, but this is scarcely ever possible, and we are forced to look to other species and genera of the same group, that is to the collateral descendants from the same parent form, in order to see what gradations are possible, and for the chance of some gradations having been transmitted in an unaltered or little altered condition. But the state of the same organ in distinct classes may incidentally throw light on the steps by which it has been perfected. The simplest organ which can be called an eye consists of an optic nerve, surrounded by pigment cells and covered by translucent skin, but without any lens or other refractive body. We may, however, according to M. Jourdain, descend even a step lower and find aggregates of pigment cells, apparently serving as organs of vision, without any nerves and resting merely on sarcodic tissue. Eyes of the above simple nature are not capable of distinct vision, and serve only to distinguish light from darkness. In certain starfishes, small depressions in the layer of pigment which surrounds the nerve are filled, as described by the author just quoted, with transparent gelatinous matter, projecting with a convex surface, like the cornea in the higher animals. He suggests that this serves not to form an image, but only to concentrate the luminous rays and render their perception more easy. In this concentration of the rays we gain the first and by far the most important step towards the formation of a true, picture-forming eye, for we have only to place the naked extremity of the optic nerve, which in some of the lower animals lies deeply buried in the body, and in some near the surface, at the right distance from the concentrating apparatus, and an image will be formed on it. In the great class of the articulata, we may start from an optic nerve simply coated with pigment, the latter sometimes forming a sort of pupil, but destitute of lens or other optical contrivance. With insects it is now known that the numerous facets on the cornea of their great compound eyes form true lenses, and that the cones include curiously modified nervous filaments. But these organs in the articulata are so much diversified that Muller formerly made 3 main classes with 7 subdivisions, besides a 4th main class of aggregated simple eyes. When we reflect on these facts, here given much too briefly, with respect to the wide, diversified, and graduated range of structure in the eyes of the lower animals, and when we bear in mind how small the number of all living forms must be in comparison with those which have become extinct, the difficulty ceases to be very great in believing that natural selection may have converted the simple apparatus of an optic nerve, coated with pigment and invested by transparent membrane, into an optical instrument as perfect as is possessed by any member of the articulata class. He who will go thus far ought not to hesitate to go one step further, if he finds on finishing this volume that large bodies of facts, otherwise inexplicable, can be explained by the theory of modification through natural selection. He ought to admit that a structure even as perfect as an eagle's eye might thus be formed, although in this case he does not know of the transitional states. It has been objected that in order to modify the eye and still preserve it as a perfect instrument, many changes would have to be effected simultaneously, which, it is assumed, could not be done through natural selection. But as I have attempted to show in my work on the variation of domestic animals, it is not necessary to suppose that the modifications were all simultaneous, if they were extremely slight and gradual. Different kinds of modification would, also, serve for the same general purpose. As Mr. Wallace has remarked, if a lens has too short or too long a focus, it may be amended either by alteration of curvature or an alteration of density. If the curvature be irregular, and the rays do not converge to a point, then any increased regularity of curvature will be an improvement. So the contraction of the iris and the muscular movements of the eye are neither of them essential to vision, but only improvements which might have been added and perfected at any stage of the construction of the instrument. Within the highest division of the animal kingdom, namely the vertebrata, we can start from an eye so simple that it consists, as in the lancelet, of a little sac of transparent skin, furnished with a nerve and lined with pigment, but destitute of any other apparatus. In fishes and reptiles, as Owen has remarked, the range of gradation from dioptric structures is very great. It is a significant fact that even in man, according to the high authority of Virchow, the beautiful crystalline lens is formed in the embryo by an accumulation of epidermic cells lying in a sac-like fold of the skin, and the vitreous body is formed from embryonic subcutaneous tissue. To arrive, however, at a just conclusion regarding the formation of the eye, with all its marvellous yet not absolutely perfect characters, it is indispensable that the reason should conquer the imagination. But I have felt the difficulty far too keenly to be surprised at others hesitating to extend the principle of natural selection to so startling a length. It is scarcely possible to avoid comparing the eye with a telescope. We know that this instrument has been perfected by the long-continued efforts of the highest human intellects, and we naturally infer that the eye has been formed by a somewhat analogous process. But may not this interference be presumptuous? Have we any right to assume that the Creator works by intellectual powers like those of man? If we must compare the eye to an optical instrument, we ought in imagination to take a thick layer of transparent tissue, with spaces filled with fluid, and with a nerve sensitive to light beneath, and then suppose every part of this layer to be continually changing slowly in density, so as to separate into layers of different densities and thickness, placed different distances from each other, and with the surfaces of each layer slowly changing in form. Further, we must suppose that there is a power, represented by natural selection or the survival of the fittest, always intently watching each slight alteration in the transparent layers, and carefully preserving each which, under varied circumstances, in any way or degree, tends to produce a distincter image. We must suppose each new state of the instrument to be multiplied by the million, each to be preserved until a better is produced, and then the old ones to be all destroyed. In living bodies, variation will cause the slight alteration, generation will multiply them almost infinitely, and natural selection will pick out with unerring skill each improvement. Let this process go on for millions of years, enduring each year on millions of individuals of many kinds, and may we not believe that a living optical instrument might thus be formed as superior to one of glass, as the works of the Creator are to those of man?
Modes of transition. If it could be demonstrated that any complex organ existed which could not possibly have been formed by numerous successive slight modifications, my theory would absolutely break down. But I can find out no such case. No doubt many organs exist of which we do not know the transitional grades, more especially if we look to much isolated species, around which, according to the theory, there has been much extinction. Or again, if we take an organ common to all the members of a class, for in this latter case, the organ must have been originally formed at a remote period, since which all the many members of the class have been developed, and in order to discover the early transitional grades through which the organ has passed, we should have to look to very ancient ancestral forms, long since become extinct. We should be extremely cautious in concluding that an organ could not have been formed by transitional gradations of some kind. Numerous cases could be given among the lower animals of the same organ performing at the same time wholly distinct functions. Thus, in the larva of the dragonfly and in the fish cobites, the alimentary canal respires, digests, and excretes. In the hydra, the animal may be turned inside out, and the exterior surface will then digest, and the stomach respire. In such cases, natural selection might specialize, if any advantage were thus gained, the whole or part of an organ, which had previously performed two functions, for one function alone, and thus by insensible steps greatly change its nature. Many plants are known which regularly produce at the same time differently constructed flowers, and if such plants were to produce one kind alone, a great change would be effected with comparative suddenness in the character of the species. It is, however, probable that the two sorts of flowers borne by the same plant were originally differentiated by finely graduated steps, which may still be followed in some few cases. Again, two distinct organs, or the same organ under two very different forms, may simultaneously perform in the same individual the same function, and this is an extremely important means of transition. To give one instance, there are fish with gills or branchiae that breathe the air dissolved in the water, at the same time that they breathe free air in their swim bladders, this latter organ being divided by highly vascular partitions and having a ductus pneumaticus for the supply of air. To give another instance from the vegetable kingdom, plants climb by three distinct means: by spirally twining, by clasping a support with their sensitive tendrils, and by the emission of aerial rootlets. These three means are usually found in distinct groups, but some few species exhibit two of the means, or even all three, combined in the same individual. In all such cases, one of the two organs might readily be modified and perfected so as to perform all the work, being aided during the process of modification by the other organ, and then this other organ might be modified for some other and quite distinct purpose, or be wholly obliterated. The illustration of the swim bladder in fishes is a good one, because it shows us clearly the highly important fact that an organ originally constructed for one purpose, namely flotation, may be converted into one for a widely different purpose, namely respiration. The swim bladder has, also, been worked in as an accessory to the auditory organs of certain fishes. All physiologists admit that the swim bladder is homologous, or ideally similar, in position and structure with the lungs of the higher vertebrate animals. Hence there is no reason to doubt that the swim bladder has actually been converted into lungs, or an organ used exclusively for respiration. According to this view, it may be inferred that all vertebrate animals with true lungs are descended by ordinary generation from an ancient and unknown prototype which was furnished with a floating apparatus or swim bladder. We can thus, as I infer from Professor Owen's interesting description of these parts, understand the strange fact that every particle of food and drink which we swallow has to pass over the orifice of the trachea, with some risk of falling into the lungs, notwithstanding the beautiful contrivance by which the glottis is closed. In the higher vertebrata, the branchiae have wholly disappeared, but in the embryo the slits on the side of the neck and the loop-like course of the arteries still mark their former position. But it is conceivable that the now utterly lost branchiae might have been gradually worked in by natural selection for some distinct purpose. For instance, Landois has shown that the wings of insects are developed from the trachea. It is therefore highly probable that in this great class, organs which once served for respiration have been actually converted into organs for flight. In considering transitions of organs, it is so important to bear in mind the probability of conversion from one function to another that I will give another instance. Pedunculated cirripedes have two minute folds of skin, called by me ovigerous frena, which serve, through a means of sticky secretion, to retain the eggs until they are hatched within the sac. These cirripedes have no branchiae, the whole surface of the body and of the sac, together with the small frena, serving for respiration. The balandae, or sessile cirripedes, on the other hand, have no ovigerous frena, the eggs lying loose at the bottom of the sac, within the well-enclosed shell, but they have, in the same relative position with the frena, large, much-folded membranes, which freely communicate with the circulatory lacunae of the sac and body, and which have been considered by all naturalists to act as branchiae. Now I think no one will dispute that the ovigerous frena in the one family are strictly homologous with the other branchiae of the other family. Indeed, they graduate into each other. Therefore, it need not be doubted that the two little folds of skin, which originally served as ovigerous frena, but which likewise very slightly aided in the act of respiration, have been gradually converted by natural selection into branchiae, simply through an increase in their size and the obliteration of their adhesive glands. If all pedunculated cirripedes had become extinct, and they have suffered far more extinction than have sessile cirripedes, who could ever have imagined that the branchiae in this latter family had originally existed as organs for preventing the ova from being washed out of the sac? There is another possible mode of transition, namely through the acceleration or retardation of the period of reproduction. This has lately been insisted on by Professor Cope and others in the United States. It is now known that some animals are capable of reproduction at a very early age, before they have acquired their perfect characters, and if this power became thoroughly well developed in a species, it seems probable that the adult stage of development would sooner or later be lost, and in this case, especially if the larva differed much from the mature form, the character of the species would be greatly changed and degraded. Again, not a few animals, after arriving at maturity, go on changing in character during nearly their whole lives. With mammals, for instance, the form of the skull is often much altered with age, of which Dr. Murray has given some striking instances with seals.
End of chapter
6.
part 1.
The Origin of Species by Means of Natural Selection, or the Preservation of Favoured Races in the Struggle for Life. 6th London edition, by Charles Darwin. Chapter number 6.
Part 2.
Difficulties of the Theory.
Everyone knows how the horns of stags become more and more branched, and the plumes of some birds become more finely developed as they grow older. Professor Cope states that the teeth of certain lizards change much in shape with the advancing years. With crustaceans, not only many trivial, but some important parts assume a new character, as recorded by Fritz Müller after maturity. In all such cases, and many could be given, if the age for reproduction were retarded, the character of the species, at least in its adult state, would be modified. Nor is it improbable that the previous and earlier stages of development would in some cases be hurried through and finally lost. Whether species have often or ever been modified through this comparatively sudden mode of transition, I can form no opinion, but if this has occurred, it is probable that the differences between the young and the mature, and between the mature and the old, were primordially acquired by graduated steps. Special difficulties of the theory of natural selection. Although we must be extremely cautious in concluding that any organ could not have been produced by successive, small, transitional gradations, yet undoubtedly serious cases of difficulty occur. One of the most serious is that of neuter insects, which are often differently constructed from either the males or fertile females, but this case will be treated of in the next chapter. The electric organs of fishes offer another case of special difficulty, for it is impossible to conceive by what steps these wondrous organs have been produced. But this is not surprising, for we do not even know of what use they are. In the gymnotus and torpedo, they no doubt serve as powerful means of defense, and perhaps for securing prey. Yet in the ray, as observed by Metucci, an analogous organ in the tail manifests but little electricity, even when the animal is greatly irritated, so that it can hardly be of any use for the above purposes. Moreover, in the ray, besides the organ just referred to, there is, as Dr. R. MacDonald has shown, another organ near the head, not known to be electrical, but which appears to be the real homologue of the electric battery in the torpedo. It is generally admitted that there exists between these organs and ordinary muscle a close analogy, an intimate structure, in the distribution of the nerves, and in the manner in which they are acted on by various reagents. It should also be especially observed that muscular contraction is accompanied by an electrical discharge, and, as Dr. Radcliffe insists, in the electrical apparatus of the torpedo during rest, there would seem to be a charge in every respect like that which is met with in muscle and nerve during the rest, and the discharge of the torpedo, instead of being peculiar, may be only another form of the discharge which tends upon the action of muscle and motor nerve. Beyond this, we cannot at present go in the way of explanation, but as we know so little about the uses of these organs, and as we know nothing about the habits and structure of the progenitors of the existing electric fishes, it would be extremely bold to maintain that no serviceable transitions are possible by which these organs might have been gradually developed. These organs appear at first to offer another and far more serious difficulty, for they occur in about a dozen kinds of fish, of which several are widely remote in their affinities. When the same organ is found in several members of the same class, especially if in members having very different habits of life, we may generally attribute its presence to inheritance from a common ancestor, and its absence in some of the members to loss through disuse or natural selection. So that, if the electric organs had been inherited from some one ancient progenitor, we might have expected that all electric fishes would have been specially related to each other, but this is far from the case. Nor does geology at all lead to the belief that most fishes formerly possessed electric organs, which their modified descendants have now lost. But when we look at the subject more closely, we find in the several fishes provided with electric organs that they are situated in different parts of the body, that they differ in construction, as in the arrangement of plates, and, according to Piscini, in the process or means by which the electricity is excited, and lastly, in being supplied with nerves proceeding from different sources, and this is perhaps the most important of all the differences. Hence, in the several fishes furnished with electric organs, these cannot be considered as homologous, but only as analogous in function. Consequently, there is no reason to suppose that they have been inherited from a common progenitor, for had this been the case, they would have closely resembled each other in all respects. Thus the difficulty of an organ, apparently the same, arising in several remotely allied species, disappears, leaving only the lesser, yet still great difficulty, namely, by which graduated steps these organs have been developed in each separate groups of fishes. The luminous organs which occur in a few insects, belonging to widely different families, and which are situated in different parts of the body, offer, under our present state of ignorance, a difficulty almost exactly parallel with that of electric organs. Other similar cases could be given. For instance, in plants, the very curious contrivance of a mass of pollen grains, borne on a footstalk with an adhesive gland, is apparently the same in Orchis and Asclepias, genera almost as remote as is possible among flowering plants. But here again the parts are not homologous. In all cases of beings, far removed from each other in the scale of organization, which are furnished with similar and peculiar organs, it will be found that although the general appearance and function of the organs may be the same, yet fundamental differences between them can always be detected. For instance, the eyes of cephalopods, or cuttlefish, and of vertebrate animals appear wonderfully alike, and in such widely sundered groups no part of this resemblance can be due to inheritance from a common progenitor. Mr. Mivart has advanced this case as one of special difficulty, but I am unable to see the force of his argument. An organ for vision must be formed of transparent tissue, and must include some sort of lens for throwing an image at the back of a darkened chamber. Beyond this superficial resemblance, there is hardly any real similarity between the eyes of cuttlefish and vertebrates, as may be seen by consulting Henson's admirable memoir on these organs in the Cephalopoda. It is impossible for me to enter here on details, but I may specify a few of the points of difference. The crystalline lens in the higher cuttlefish consists of two parts, placed one behind the other like two lenses, both having a very different structure and disposition to what occurs in the vertebrata. The retina is wholly different, with an actual inversion of the elemental parts, and with a large nervous ganglion included within the membranes of the eye. The relations of the muscles are as different as it is possible to conceive, and so in other points. Hence it is not a little difficult to decide how far even the same terms ought to be employed in describing the eyes of the Cephalopoda and the vertebrata. It is, of course, open to anyone to deny that the eye in either case could have been developed through the natural selection of successive slight variations. But if this be admitted in the one case, it is clearly possible in the other, and fundamental differences of structure in the visual organs of two groups might have been anticipated in accordance with this view of their manner of formation. As two men have sometimes independently hit on the same invention, so in the several foregoing cases it appears that natural selection, working for the good of each being, and taking advantage of all favorable variations, has produced similar organs, as far as function is concerned, in distinct organic beings, which owe none of their structure in common to inheritance from a common progenitor. Fritz Müller, in order to test the conclusions arrived at in this volume, has followed out with much care a nearly similar line of argument. Several families of crustaceans include a few species possessing an air-breathing apparatus and fitted to live out of the water. In two of these families, which are more especially examined by Müller, and which are nearly related to each other, the species agree most closely in all important characters, namely in their sense organs, circulating systems, in the position of the tufts of hair within their complex stomachs, and lastly, in the whole structure of the water-breathing branchiae, even to the microscopical hooks by which they are cleansed. Hence it might have been expected that in the few species belonging to both families which live on the land, the equally important air-breathing apparatus would have been the same, for why should this one apparatus, given for the same purpose, have been made to differ, while all the other important organs were closely similar, or rather identical? Fritz Müller argues that this close similarity in so many points of structure must, in accordance with the views advanced by me, be accounted for by inheritance from a common progenitor. But as the vast majority of the species in the above two families, as well as with most other crustaceans, are aquatic in their habits, it is improbable in the highest degree that their common progenitor should have been adapted for breathing air. Müller has thus led carefully to examine the apparatus in the air-breathing species, and he found it to differ in several important points, as in the position of the orifices, in the manner in which they are open and closed, and in some accessory details. Now such differences are intelligible, and might even have been expected, on the supposition that species belonging to distinct families had slowly become adapted to live more and more out of water, and to breathe the air. For these species, from belonging to distinct families, would have differed to a certain extent, and in accordance with the principle that the nature of each variation depends on two factors, viz., the nature of the organism and that of the surrounding conditions, their variability assuredly would not have been exactly the same. Consequently, natural selection would have had different materials or variations to work on in order to arrive at the same functional result, and the structures thus acquired would almost necessarily have differed. On the hypothesis of several acts of creation, the whole case remains unintelligible. This line of argument seems to have had great weight in leading Fritz Muller to accept the views maintained by me in this volume. Another distinguished zoologist, the late Professor Clapauder, has argued in the same manner and has arrived at the same result. He shows that there are parasitic mites, Acardinae, belonging to distinct subfamilies and families which are furnished with hair claspers. These organs must have been independently developed, as they could not have been inherited from a common progenitor, and, in the several groups they are formed by the modification of the forelegs, of the hind legs, of the maxillae or lips, and of appendages on the underside of the hind part of the body. In the foregoing cases, we see the same end gained and the same function performed in beings not at all or only remotely allied, by organs in appearance, though not in development, closely similar. On the other hand, it is a common rule throughout nature that the same end should be gained, even sometimes in the case of closely related beings, by the most diversified means. How differently constructed is the feathered wing of a bird and the membrane-covered wing of a bat, and still more so the 4 wings of a butterfly, the 2 wings of a fly, and the 2 wings with the elytra of the beetle. Bivalve shells are made to open and shut, but on what a number of patterns is the hinge constructed, from the long row of neatly interlocking teeth in a nucula to the simple ligament of a muscle. Seeds are disseminated by their minuteness, by their capsule being converted into a light balloon-like envelope, by being embedded in pulp or flesh, formed of thy most diverse parts, and rendered nutritious as well as conspicuously colored, so as to attract and be devoured by birds, by having hooks and grapples of many kinds and serrated awns, so as to adhere to the fur of quadrupeds, and by being furnished with wings and plumes, as different in shape as they are elegant in structure, so as to be wafted by every breeze. I will give one other instance. For this subject of the same end being gained by the most diversified means well deserves attention. Some authors maintain that organic beings have been formed in many ways for the sake of mere variety, almost like toys in a shop, but such a view of nature is incredible. With plants having separated sexes, and with those in which, though hermaphrodites, the pollen does not spontaneously fall on the stigma, some aid is necessary for their fertilization. With several kinds this is effected by the pollen grains, which are light and incoherent, being blown by the wind through mere chance onto the stigma, and this is the simplest plan which can well be conceived. An almost equally simple, though very different plan occurs in many plants in which a symmetrical flower secretes a few drops of nectar, and is consequently visited by insects, and these carry the pollen from the anthers to the stigma. From this simple stage we may pass through an inexhaustible number of contrivances, all for the same purpose and effected in essentially the same manner, but entailing changes in every part of the flower. The nectar may be stored in variously shaped receptacles, with the stamens and pistils modified in many ways, sometimes forming trap-like contrivances, and sometimes capable of neatly adapted movements through irritability or elasticity. From such structures we may advance till we come to such a case of extraordinary adaptation as that lately described by Dr. Kruger in the Coryanthes. This orchid has part of its labellum or lower lip hollowed into a great bucket, into which drops of almost pure water continually fall from 2 secreting horns which stand above it, and when the bucket is half full, the water overflows by a spout on one side. The basal part of the labellum stands over the bucket, and is itself hollowed out into a sort of chamber with 2 lateral entrances. Within this chamber there are curious fleshy ridges. The most ingenious man, if he had not witnessed what takes place, could never have imagined what purpose all these parts serve. Dr. Kruger saw crowds of large humblebees visiting the gigantic flowers of this orchard, not in order to suck nectar, but to gnaw off the ridges within the chamber above the bucket. In doing this they frequently pushed each other into the bucket, and their wings being thus wetted they could not fly away, but were compelled to crawl out through the passage formed by the spout or overflow. Dr. Kruger thus saw a continual procession of bees crawling out of their involuntary bath. The passage is narrow, and is roofed over by the column, so that a bee, in forcing its way out, first rubs its back against the viscid stigma and then against the viscid glands of the pollen masses. The pollen masses are thus glued to the back of the bee, which first happens to crawl out through the passage of a lately expanded flower, and are thus carried away. Dr. Kruger sent me a flower in spirits of wine, with a bee which he had killed before it had quite crawled out, with a pollen mass still fastened to its back. When the bee, thus provided, flies to another flower, or to the same flower a second time, and is pushed by its comrades into the bucket, and then crawls out by the passage, the pollen mass necessarily comes first into contact with the viscid stigma, and adheres to it, and the flower is fertilized. Now at last we see the full use of every part of the flower, of the water-secreting horns of the bucket half full of water, which prevents the bees from flying away, and forces them to crawl out through the spout, and rub against the properly placed viscid pollen masses and the viscid stigma. The construction of the flower in another closely allied orchid, namely the cataseum, is widely different, though serving the same end, and is equally curious. Bees visit these flowers, like those of the coryanthes, in order to gnaw the labellum. In doing this, they inevitably touch a long, tapering, sensitive projection, or, as I have called it, the antenna. This antenna, when touched, transmits a sensation or vibration to a certain membrane which is instantly ruptured. This sets free a spring by which the pollen mass is shot forth, like an arrow, in the right direction, and adheres by its viscid extremity to the back of the bee. The pollen mass of the male plant, for the sexes are separate in this orchid, is thus carried to the flower of the female plant, where it is brought into contact with the stigma, which is viscid enough to break certain elastic threads and retain the pollen, thus effecting fertilization. How, it may be asked, in the foregoing and in innumerable other instances, can we understand the graduated scale of complexity and the multifarious means for gaining the same end? The answer, no doubt, is, as already remarked, that when two forms vary, which already differ from each other in some slight degree, the variability will not be of the same exact nature, and consequently the results obtained through natural selection for the same general purpose will not be the same. We should also bear in mind that every highly developed organism has passed through many changes, and that each modified structure tends to be inherited, so that each modification will not readily be quite lost, but may be again and again further altered. Hence, the structure of each part of each species, for whatever purpose it may serve, is the sum of many inherited changes, through which the species has passed during successive adaptations to change habits and conditions of life. Finally, then, although in many cases it is most difficult even to conjecture by what transitions organs could have arrived at their present state, yet, considering how small the proportion of living known forms is to the extinct and unknown, I have been astonished how rarely an organ can be named towards which no transitional grade is known to lead. It is certainly true that new organs appearing as if created for some special purpose rarely or never appear in any being, as indeed is shown by that old, but somewhat exaggerated, canon in natural history of natura non facit saltum. We meet with this admission in the writings of almost every experienced naturalist, or, as Milne Edwards has well expressed it, nature is prodigal in variety, but niggard in innovation. Why, on the theory of creation, should there be so much variety and so little real novelty? Why should all the parts and organs of many independent beings, each supposed to have been separately created for its own proper place in nature, be so commonly linked together by graduated steps? Why should not nature take a sudden leap from structure to structure? On the theory of natural selection, we can clearly understand why she should not, for natural selection acts only by taking advantage of slight successive variations. She can never take a great and sudden leap, but must advance by the short and sure, through slow steps. Organs of little apparent importance, as affected by natural selection. As natural selection acts by life and death, by the survival of the fittest, and by the destruction of the less well-fitted individuals, I have sometimes felt great difficulty in understanding the origin or formation of parts of little importance, almost as great, though of a very different kind, as in the case of the most perfect and complex organs. In the first place, we are much too ignorant in regard to the whole economy of any one organic being to say what slight modifications would be of importance or not. In a former chapter, I have given instances of very trifling characters, such as the down on fruit and the color of its flesh, the color of the skin and hair of quadrupeds, which, from being correlated with constitutional differences, or from determining the attacks of insects, might assuredly be acted on by natural selection. The tail of the giraffe looks like an artificially constructed fly flapper, and it seems at first incredible that this could have been adapted for its present purpose by successive slight modifications, each better and better fitted for so trifling an object as to drive away flies. Yet we should pause before being too positive even in this case, for we know that the distribution and existence of cattle and other animals in South America absolutely depend on their power of resisting the attacks of insects, so that individuals which could by any means defend themselves from these small enemies would be able to range into new pastures and thus gain a great advantage. It is not that the larger quadrupeds are actually destroyed, except in some rare cases, by flies, but they are incessantly harassed and their strength reduced, so that they are more subject to disease, or not so well enabled in a coming dearth to search for food, or to escape from beasts of prey. Organs now of trifling importance have probably in some cases been of high importance to an early progenitor, and, after having been slowly perfected at a former period, have been transmitted to existing species in nearly the same state, although now of very slight use. But any actually injurious deviations in their structure would of course have been checked by natural selection. Seeing how important an organ of locomotion the tail is in most aquatic animals, its general presence and use for many purposes in so many land animals, which in their lungs or modified swim bladders betray their aquatic origin, may perhaps be thus accounted for. A well-developed tail having been formed in an aquatic animal, it might subsequently come to be worked in for all sorts of purposes, as a fly flapper, an organ of prehension, or as an aid in turning, as in the case of the dog, though the aid in this latter respect must be slight, for the hare, with hardly any tail, can double still more quickly. In the second place, we may easily err in attributing importance to characters, and in believing that they have been developed through natural selection. We must by no means overlook the effects of the definite action of changed conditions of life, of so-called spontaneous variations, which seem to depend in a quite subordinate degree on the nature of the conditions, of the tendency to reversion to long-lost characters, of the complex laws of growth, such as correlation, comprehension of the pressure of one part on another, etc., and finally of sexual selection, by which characters of use to one sex are often gained and then transmitted more or less perfectly to the other sex, though of no use to the sex. But structures thus indirectly gained, although at first no advantage to a species, may subsequently have been taken advantage of by its modified descendants, under new conditions of life and newly acquired habits. If green woodpeckers alone had existed, and we did not know that there were many black and pied kinds, I dare say that we should have thought that the green color was a beautiful adaptation to conceal this tree-frequenting bird from its enemies, and consequently that it was a character of importance and had been acquired through natural selection. As it is, the color is probably in chief part due to sexual selection. A trailing palm in the Malay arpeggio climbs the loftiest trees by aid of exquisitely constructed hooks clustered around the ends of the branches, and this contrivance, no doubt, is of the highest service to the plant. But as we see nearly similar hooks on many trees which are not climbers, and which, as there is reason to believe from the distribution of the thorn-bearing species in Africa and South America, serve as a defense against browsing quadrupeds, so the spikes on the palm may at first have been developed for this object, and subsequently have been improved and taken advantage of by the plant, as it underwent further modification and became a climber. The naked skin on the head of a vulture is generally considered as a direct adaptation for wallowing in putridity, and so it may be, or may possibly be due to the direct action of putrid matter. But we should be very cautious in drawing any such inference when we see that the skin on the head of the clean-feeding male turkey is likewise naked. The sutures in the skulls of mammals have been advanced as a beautiful adaptation for aiding parturition, and no doubt they facilitate or may be indispensable for this act. But as sutures occur in the skulls of young birds and reptiles, which have only to escape from a broken egg, we may infer that this structure has arisen from the laws of growth, and has been taken advantage of in the parturition of the higher animals. We are profoundly ignorant of the cause of each slight variation or individual difference, and we are immediately made conscious of this by reflecting on the differences between the breeds of our domesticated animals in different countries, more especially in the less civilized countries, where there has been but little methodical selection. Animals kept by savages in different countries often have to struggle for their own subsistence, and are exposed to a certain extent to natural selection, and individuals with slightly different constitutions would succeed best under different climates. With cattle, susceptibility to the attacks of flies is correlated with color, as is the liability to be poisoned by certain plants, so that even color would thus be subjected to the action of natural selection. Some observers are convinced that a damp climate affects the growth of the hair, and that with the hair the horns are correlated. Mountain breeds always differ from lowland breeds, and a mountainous country would probably affect the hind limbs from exercising them more, and possibly even the form of the pelvis. And then by the law of homologous variation, the front limbs and the head would probably be affected. The shape also of the pelvis might affect by pressure the shape of certain parts of the young in the womb. The laborious breathing necessary in high regions tends, as we have good reason to believe, to increase the size of the chest, and again correlation would come into play. The effects of lessened exercise, together with abundant food, on the whole organization is probably still more important, and this, as H. von Nathusis has lately shown in his excellent treatise, is apparently one chief cause of the great modification which the breeds of swine have undergone. But we are far too ignorant to speculate on the relative importance of the several known and unknown causes of variation, and I have made the remarks only to show that, if we are unable to account for the characteristic differences of our several domestic breeds, which nevertheless are generally admitted to have arisen through ordinary generation from one or a few parent stocks, we ought not to lay too much stress on our ignorance of the precise cause of the slight analogous differences between true species. Utilitarian doctrine, how far true? Beauty, how acquired? The foregoing remarks lead me to say a few words on the protest lately made by some naturalists against the utilitarian doctrine that every detail of structure has been produced for the good of its possessor. They believe that many structures have been created for the sake of beauty, to delight man or the Creator, but this latter point is beyond the scope of scientific discussion, or for the sake of mere variety, a few already discussed. Such doctrines, if true, would be absolutely fatal to my theory. I fully admit that many structures are now of no direct use to their possessors, and may never have been of any use to their progenitors, but this does not prove that they were formed solely for beauty or variety. No doubt the definite action of changed conditions and the various causes of modifications lately specified have all produced an effect, probably a great effect, independently of any advantage thus gained. But a still more important consideration is that the chief part of the organization of every living creature is due to inheritance, and consequently, though each being assuredly is well fitted for its place in nature, many structures have now no very close and direct relation to present habits of life. Thus, we can hardly believe that the webbed feet of the upland goose, or of the frigate bird, are of special use to these birds. We cannot believe that the similar bones in the arm of the monkey, in the foreleg of the horse, in the wing of the bat, and in the flipper of the seal, are of special use to these animals. We may safely attribute these structures to inheritance. But webbed feet, no doubt, were as useful to the progenitor of the upland goose and of the frigate bird as they now are to the most aquatic of living birds. So we may believe that the progenitor of the seal did not possess a flipper, but a foot with 5 toes fitted for walking or gasping, and we may further venture to believe that the several bones in the limbs of the monkey, horse, and bat were originally developed on the principle of utility, probably through the reduction of more numerous bones in the fin of some ancient fish-like progenitor of the whole class. It is scarcely possible to decide how much allowance ought to be made for such causes of change as the definite action of external conditions, so-called spontaneous variations, and the complex laws of growth. But with these important exceptions, we may conclude that the structure of every living creature either now is, or was formerly, of some direct or indirect use to its possessor. With respect to the belief that organic beings have been created beautiful for the delight of man, a belief which, it has been pronounced, is subversive of my whole theory, I must first remark that the sense of beauty obviously depends on the nature of the mind, irrespective of any real quality in the admired object, and that the idea of what is beautiful is not innate or unalterable. We see this, for an instance, in the men of different races admiring an entirely different standard of beauty in their women. If beautiful objects had been created solely for man's gratification, it ought to be shown that before man appeared there was less beauty on the face of the earth than since he came on the stage. Were the beautiful volute and cone shells of the Eocene epoch and the gracefully sculptured ammonite of the secondary period created that man might ages afterward admire them in his cabinet? Few objects are more beautiful than the minute siliceous cases of diamanticae. Were these created that they might be examined and admired under the higher powers of the microscope? The beauty in this latter case, and in many others, is apparently wholly due to the symmetry of growth. Flowers rank among the most beautiful productions of nature, but they have been rendered conspicuous in contrast with the green leaves, and in consequence at the same time beautiful, so that they may be easily observed by insects. I have come to this conclusion from finding it an invariable rule that when a flower is fertilized by the wind, it never has a gaily colored corolla. Several plants habitually produce 2 kinds of flowers, one kind open and colored so as to attract insects, the other closed, not colored, destitute of nectar, and never visited by insects. Hence we may conclude that, if insects had not been developed on the face of the earth, our plants would not have been decked with beautiful flowers, but it would have been produced only with such poor flowers as we see on our fir, oak, nut, and ash trees, on grasses, spinach, docks, and nettles, which are all fertilized through the agency of wind. A similar line of argument holds good with fruits, that a ripe strawberry or cherry is as pleasing to the eye as to the palate, that the gaily colored fruit of the spindlewood tree and the scarlet berries of the holly are beautiful objects, will be admitted by everyone. But this beauty serves merely as a guide to birds and beasts, in order that the fruit may be devoured and the matured seeds disseminated. I infer that this is the case from having as yet found no exception to the rule that seeds are always disseminated when embedded within a fruit of any kind, that is, within a fleshy or pulpy envelope, if it is to be colored of any brilliant tint, or rendered conspicuous by being white or black. On the other hand, I willingly admit that a great number of male animals, as are most gorgeous birds, some fishes, reptiles, and mammals, and a host of magnificently colored butterflies, have been rendered beautiful for beauty's sake. But this has been effected through sexual selection, that is, by the more beautiful males having been continually preferred by the females, and not for the delight of man. So it is with the music of birds. We may infer from all this that a nearly similar taste for beautiful colors and for musical sounds runs through a large part of the animal kingdom. When the female is as beautifully colored as the male, which is not rarely the case with birds and butterflies, the cause apparently lies in the colors acquired through sexual selection having been transmitted to both sexes instead of to the males alone. How the sense of beauty in its simplest form, that is, the reception of a peculiar kind of pleasure from certain colors, forms, and sounds, was first developed in the mind of man and of the lower animals, is a very obscure subject. The same sort of difficulty is presented if we inquire how it is that certain flavors and odors give pleasure and others displeasure. Habit in all these cases appears to have come to a certain extent into play, but there must be some fundamental cause in the constitution of the nervous system in each species. Natural selection cannot possibly produce any modification in a species exclusively for the good of another species, though throughout nature one species incessantly takes advantage of, and profits by, the structures of others. But natural selection can, and does, often produce structures for the direct injury of other animals, as we see in the fang of the adder, and in the ovipositor of the ichneumon, by which its eggs are deposited in the living bodies of other insects. If it could be proved that any part of the structure of any one species had been formed for the exclusive good of another species, it would annihilate my theory, for such could not have been produced through natural selection. Although many statements may be found in works on natural history to this effect, I cannot find even one which seems to me of any weight. It is admitted that the rattlesnake has a poison fang for its own defense and for the destruction of its prey, but some authors suppose that at the same time it is furnished with a rattle for its own injury, namely, to warn its prey. I would almost as soon believe that the cat curls the end of its tail when preparing to spring in order to warn the doomed mouse. It is a much more probable view that the rattlesnake uses its rattle, the cobra expands its frill, and the puff adder swells while hissing so loudly and harshly in order to alarm the many birds and beasts which are known to attack even the most venomous species. Snakes act on the same principle which makes the hen ruffle her feathers and expand her wings when a dog approaches her chickens. But I have not space here to enlarge on the many ways by which animals endeavor to frighten away their enemies. Natural selection will never produce in a being any structure more injurious than beneficial to that being, for natural selection acts solely by and for the good of each. No organ will be formed, as Paley has remarked, for the purpose of causing pain or for doing an injury to its possessor. If a fair balance be struck between the good and evil caused by each part, each will be found, on the whole, advantageous. After the lapse of time, under changing conditions of life, if If any part comes to be injurious, it will be modified, or, if it be not so, the being will become extinct, as myriads have become extinct. Natural selection tends only to make each organic being as perfect as, or slightly more perfect than the other inhabitants of the same country with which it comes into competition. And we see that this is the standard of perfection attained under nature. The endemic productions of New Zealand, for instance, are perfect, one compared with another, but they are now rapidly yielding before the advancing legions of plants and animals introduced from Europe. Natural selection will not produce absolute perfection, nor do we always meet, as far as we can judge, with this high standard under nature. The correction for the aberration of light is said by Müller not to be perfect even in the most perfect organ, the human eye. Helmholtz, whose judgment no one will dispute, after describing in the strongest terms the wonderful powers of the human eye, adds these remarkable words: "That which we have discovered in the way of inexactness and imperfection in the optical machine and in the image on the retina is as nothing in comparison with the incongruities which we have just come across in the domain of the sensations. One might say that nature has taken delight in accumulating contradictions in order to remove all foundation from the theory of a pre-existing harmony between the external and internal worlds." If our reason leads us to admire with enthusiasm a multitude of inimitable contrivances in nature, this same reason tells us, though we may easily err on both sides, that some other contrivances are less perfect. Can we consider the sting of the bee as perfect, which, when used against many kinds of enemies, cannot be withdrawn, owing to the backward serratures, and thus invariably causes the death of the insect by tearing out its viscera? If we look at the sting of the bee as having existed in a remote progenitor, as a boring and serrated instrument, like that in so many members of the same great order, and that it has since been modified but not perfected for its present purpose, with the position originally adapted for some other object, such as produce galls, since intensified, we can perhaps understand how it is that the use of the sting should so often cause the insect's own death. For if, on the whole, the power of stinging be useful to the social community, it will fulfill all the requirements of natural selection, though it may cause the death of some few members. If we admire the truly wonderful power of scent by which the males of many insects find their females, we can admire the production for the single purpose of thousands of drones, which are utterly useless to the community for any other purpose, and which are ultimately slaughtered by their industrious and sterile sisters? It may be difficult, but we ought to admire the savage instinctive hatred of the queen bee, which urges her to destroy the young queens, her daughters, as soon as they are born, or to perish herself in the combat, for undoubtedly this is for the good of the community, and maternal love or maternal hatred, though the latter, fortunately, is most rare, is all the same to the inexorable principles of natural selection. If we admire the several ingenious contrivances by which orchids and many other plants are fertilized through insect agency, can we consider as equally perfect the elaboration of dense clouds of pollen by our fir trees, so that a few granules may be wafted by chance on to the ovules? Summary. The law of unity of type and of the conditions of existence embraced by the theory of natural selection. We have, in this chapter, discussed some of the difficulties and objections which may be urged against the theory. Many of them are serious, but I think that in the discussion light has been thrown on several facts, which on the belief of independent acts of creation are utterly obscure. We have seen that species at any one period are not indefinitely variable, and are not linked together by a multitude of intermediate gradations, partly because the process of natural selection is always very slow, and at any one time acts only on a few forms, and partly because the very process of natural selection implies the continual supplanting and extinction of preceding and intermediate gradations. Closely allied species, now living on a continuous area, must often have been formed when the area was not continuous, and when the conditions of life did not insensibly graduate away from one part to another. When two varieties are formed in two districts of a continuous era, an intermediate variety will often be formed, fitted for an intermediate zone, but from reasons assigned, the intermediate variety will usually exist in lesser numbers than the two forms which it connects. Consequently, the two latter, during the course of further modification, from existing in greater numbers, will have a great advantage over the less numerous intermediate variety, and will thus generally succeed in supplanting and exterminating it. We have seen in this chapter how cautious we should be in concluding that the most different habits of life could not graduate into each other, that a bat, for instance, could not have been formed by natural selection from an animal which at first only glided through air. We have seen that a species under new conditions of life may change its habits, or it may have diversified habits, with some very unlike those of its nearest congeners. Hence we can understand, bearing in mind that each organic being is trying to live wherever it can live, how it has arisen that there are upland geese with webbed feet, ground woodpeckers, diving thrushes, and petrels with the habits of auks. Although the belief that an organ so perfect as the eye could have been formed by natural selection is enough to stagger anyone, yet in the case of any organ, if we know of a long series of gradations in complexity, each good for its possessor, then under changing conditions of life, there is no logical impossibility in the acquirement of any conceivable degree of perfection through natural selection. In the cases in which we know of no intermediate or transitional states, we should be extremely cautious in concluding that none can have existed, for the metamorphosis of many organs show what wonderful changes in function are at least possible. For instance, a swim bladder has apparently been converted into an air-breathing lung, the same organ having performed simultaneously very different functions, and then having been in part or in whole specialized for one function, and two distinct organs having performed at the same time the same function, the one having been perfected whilst aided by the other, must often have largely facilitated transition. We have seen that in two beings widely remote from each other in the natural scale, organs serving for the same purpose and in external appearance closely similar may have been separately and independently formed. But when such organs are closely examined, essential differences in their structure can almost always be detected, and this naturally follows from the principle of natural selection. On the other hand, the common rule throughout nature is infinite diversity of structure for gaining the same end, and this again naturally follows from the same great principle. In many cases we are far too ignorant to be enabled to assert that a part or organ is so unimportant for the welfare of a species, that modifications in its structure could not have been slowly accumulated by means of natural selection. In many other cases, modifications are probably the direct result of the laws of variation or of growth, independently of any good having been thus gained. But even such structures have often, as we may feel assured, been subsequently taken advantage of, and still further modified for the good of species under new conditions of life. We may also believe that a part formerly of high importance has frequently been retained, as the tail of an aquatic animal by its terrestrial descendants, though it has become of such small importance that it could not, in its present state, have been acquired by means of natural selection. Natural selection can produce nothing in one species for the exclusive good or injury of another, though it may well produce parts, organs, and excretions highly useful or even indispensable, or highly injurious to another species, but in all cases at the same time useful to the possessor. In each well-stocked country, natural selection acts through the competition of the inhabitants, and consequently leads to success in the battle for life, only in accordance with the standard of that particular country. Hence the inhabitants of one country, generally the smaller one, often yield to the inhabitants of another and generally larger country. For in the larger country there will have existed more individuals and more diversified forms, and the competition will have been severer, and thus the standard of perfection will have been rendered higher. Natural selection will not necessarily lead to absolute perfection, nor, as far as we can judge by our limited faculties, can absolute perfection be everywhere predicated. On the theory of natural selection, we can clearly understand the full meaning of that old canon in natural history, natura non facit saltum. This canon, if we look to the present inhabitants alone of the world, is not strictly correct, but if we include all of those of past times, whether known or unknown, it must, on this theory, be strictly true. It is generally acknowledged that all organic beings have been formed on two great laws, unity of type and the conditions of existence. By unity of type is meant the fundamental agreement in structure which we see in organic beings of the same class, and which is quite independent of their habits of life. On my theory, unity of type is explained by unity of descent. The expression of conditions of existence, so often insisted on by the illustrious Cuvier, is fully embraced by the principle of natural selection. For natural selection acts by either now adapting the varying parts of each being to its organic and inorganic conditions of life, or by having adapted them during past periods of time, the adaptations being aided, in many cases, by the increased use or disuse of parts, being affected by the direct action of external conditions of life, and subjected in all cases to the several laws of growth and variation. Hence, in fact, the law of the conditions of existence is the higher law, as it includes, through the inheritance of former variations and adaptations, that of the unity of type. End of Chapter 6.
Part 2.
The Origin of Species by means of Natural Selection, or the Preservation of Favoured Races in the Struggle for Life. 6th London edition by Charles Darwin. Chapter 7. Miscellaneous Objections to the Theory of Natural Selection. Longevity. Modifications not necessarily simultaneous. Modifications apparently of no direct service. Progressive development. Characters of small functional importance, the most constant. Supposed incompetence of natural selection to account for the incipient stages of useful structures. Causes which interfere with the acquisition through natural selection of useful structures. Gradations of structure with changed functions. Widely different organs in members of the same class, developed from one and the same source. Reasons for disbelieving in great and abrupt modifications. I will devote this chapter to the consideration of various miscellaneous objections which have been advanced against my own views, as some of the previous discussions may thus be made clearer. But it would be useless to discuss all of them, as many have been made by writers who have not taken the trouble to understand the subject. Thus a distinguished German naturalist has asserted that the weakest part of my theory is that I consider all organic beings as imperfect. What I have really said is that all are not as perfect as they might have been in relation to their conditions, and this is shown to be the case by so many native forms in many quarters of the world having yielded their places to intruding foreigners. Nor can organic beings, even if they were at any one time perfectly adapted to their conditions of life, have remained so when their conditions changed, unless they themselves likewise changed. And no one will dispute that the physical conditions of each country, as well as the number and kinds of its inhabitants, have undergone many mutations. A critic has lately insisted, with some parade of mathematical accuracy, that longevity is a great advantage to all species, so that he who believes in natural selection must arrange his genealogical tree in such a manner that all the descendants have longer lives than their progenitors. Cannot our critics conceive that a biennial plant or one of the lower animals might range into a cold climate and perish there every winter, and yet, owing to advantages gained through natural selection, survive from year to year by means of its seeds or ova? Mr. E. Ray Lancaster has recently discussed this subject, and he concludes, as far as its extreme complexity allows him to form a judgment, that longevity is generally related to the standard of each species in the scale of organization, as well as to the amount of expenditure in reproduction and in general activity. And these conditions have, it is probable, been largely determined through natural selection. It has been argued that, as none of the animals and plants of Egypt, of which we know anything, have changed during the last 3,000 or 4,000 years, so probably have none in any part of the world. But, as Mr. G. H. Lewis has remarked, this line of argument proves too much, for the ancient domestic races figured on the Egyptian monuments or embalmed are closely similar or even identical with those now living. Yet all naturalists admit that such races have been produced through the modification of their original types. The many animals which have remained unchanged since the commencement of the glacial period would have been an incomparably stronger case, for these have been exposed to great changes of climate and have migrated over great distances, whereas in Egypt, during the last several thousand years, the conditions of life, as far as we know, have remained absolutely uniform. The fact of little or no modification having been effected since the glacial period would have been of some avail against those who believe in an innate and necessary law of development, but it is powerless against the doctrine of natural selection, or the survival of the fittest, which implies that when variations or individual differences of a beneficial nature happen to arise, these will be preserved, but this will be effected only under certain favourable circumstances. The celebrated paleontologist Braun, at the close of his German translation of this work, asks how, on the principle of natural selection, can a variety live side by side with the parent species? If both have become fitted for slightly different habitats of life or conditions, they might live together, and if we lay on one side polymorphic species, in which the variability seems to be of a peculiar nature, and all mere temporary variations, such as size, albinism, etc., the more permanent varieties are generally found, as far as I can discover, inhabiting distinct stations, such as highland or lowland, dry or moist districts. Moreover, in the case of animals which wander much about and cross freely, their varieties seem to be generally confined to distinct regions. Braun also insists that the distinct species never differ from each other in single characters, but in many parts, and he asks how it always comes that many parts of the organization should have been modified at the same time through variation and natural selection. But there is no necessity for supposing that all the parts of any being have been simultaneously modified. The most striking modifications, excellently adapted for some purpose, might, as was formerly remarked, be acquired by successive variations, if slight, first in one part and then in another, and as they would be transmitted all together, they would appear to us as if they had been simultaneously developed. The best answer, however, to the above objection is afforded by those domestic races which have been modified, chiefly through man's power of selection, for some natural purpose. Look at the race and dray horse, or at the greyhound and mastiff. Their whole frames and even their mental characteristics have been modified. But if we could trace each step in the history of their transformation, and the latter steps can be traced, we should not see great and simultaneous changes, but first one part and then another, slightly modified and improved. Even when selection has been applied by man to some one character alone, of which our cultivated plants offer the best instances, it will invariably be found that although this one part, whether it be flower, fruit, or leaves, has been greatly changed, almost all the other parts have been slightly modified. This may be attributed partly to the principle of correlated growth, and partly to so-called spontaneous variation. A much more serious objection has been urged by Braun, and recently by Broca, namely that many characters appear to be of no service whatsoever to their possessors, and therefore cannot have been influenced through natural selection. Braun adduces the length of the ears and tails of the different species of hares and mice, the complex folds of enamel in the teeth of many animals, and a multitude of analogous cases. With respect to plants, this subject has been discussed by Nägeli in an admirable essay. He admits that natural selection has effected much, but he insists that the families of plants differ chiefly from each other in morphological characters, which appear to be quite unimportant for the welfare of the species. He consequently believes in an innate tendency towards progressive and more perfect development. He specifies the arrangement of the cells in the tissues, and of the leaves on the axis, as cases in which natural selection could not have acted. To these may be added the numerical divisions in the parts of the flower, the position of the ovules, the shape of the seed, when not of any use for dissemination, etc. There is much force in the above objection. Nevertheless, we ought in the first place to be extremely cautious in pretending to decide what structures now are, or have formerly been, of use to each species. In the second place, it should always be borne in mind that when one part is modified, so will be other parts, though certainly dimly seen causes, such as increased or diminished flow of nutriment to a part, mutual pressure, an early developed part affecting one subsequently developed, and so forth, as well as through other causes which lead to the many mysterious cases of correlation, which we do not in the least understand. These agencies may be all grouped together, for the sake of brevity, under the expression of the laws of growth. In the third place, we have to allow for the direct and definite action of changed conditions of life, and for so-called spontaneous variations, in which the nature of the conditions apparently plays quite a subordinate part. Bud variations, such as the appearance of a moss rose on a common rose, or of a nectarine on a peach tree, offer good instances of spontaneous variations. But even in these cases, if we bear in mind the power of a minute drop of poison in producing complex galls, we ought not to feel too sure that the above variations are not the effect of some local change in the nature of the sap, due to some change in the conditions. There must be some efficient cause for each slight individual difference, as well as for the more strongly marked variations which occasionally arise. And if the unknown cause were to act persistently, it is almost certain that all the individuals of the species would be similarly modified. In the earlier editions of this work I underrated, as it now seems probable, the frequency and importance of modifications due to spontaneous variability. But it is impossible to attribute to this cause the innumerable structures which are so well adapted to the habits of life of each species. I can no more believe in this than that the well-adapted form of a racehorse or greyhound, which before the principle of selection by man was well understood, excited so much surprise in the minds of older naturalists, can thus be explained. It may be worth while to illustrate some of the foregoing remarks. With respect to the assumed inutility of various plants and organs, it is hardly necessary to observe that even in the higher and best known animals many structures exist which are so highly developed that no one doubts that they are of importance, yet their use has not been, or has only recently been, ascertained. As Braun gives the length of the ears and tail in the several species of mice as instances, though trifling ones, of differences in structure which can be of no special use, I may mention that, according to Dr. Schobel, the external ears of the common mouse are supplied in an extraordinary manner with nerves, so that they no doubt serve as tactile organs. Hence the length of the ears can hardly be quite unimportant. We shall also presently see that the tail is a highly useful prehensile organ to some of the species, and its use would be much influenced by its length. With respect to plants, to which, on account of Nägeli's essay, I shall confine myself in the following remarks, it will be admitted that the flowers of the orchids present a multitude of curious structures, which a few years ago would have been considered as mere morphological differences without any special function, but are now known to be of the highest importance for the fertilization of the species through the aid of insects, and would probably have been gained through natural selection. No one until lately could have imagined that in dimorphic and trimorphic plants the different lengths of the stamens and pistils and their arrangement could have been of any service, but now we know this to be the case. In certain whole groups of plants the ovules stand erect, and in others they are suspended, and within the same ovarium of some few plants one ovule holds the former, and a second ovule the latter position. These positions seem at first purely morphological, or of no physiological signification, but Dr. Hooker informs me that within the same ovarium the upper ovules alone in some cases, and in others the lower ones alone, are fertilized, and he suggests that this probably depends on the direction in which pollen tubes enter the ovarium. If so, the position of the ovules, even when one is erect and the other suspended within the same ovarium, would follow the selection of any slight deviations in position which favoured their fertilization and the production of seed. Several plants belonging to distinct orders habitually produce flowers of two kinds, the one open, of the ordinary structure, the other closed and imperfect. These two kinds of flowers sometimes differ wonderfully in structure, yet may be seen to graduate into each other on the same plant. The ordinary and open flowers can be intercrossed, and the benefits which certainly are derived from this process are thus secured. The closed and imperfect flowers are, however, manifestly of high importance, as they yield with the utmost safety a large stock of seed, with the expenditure of wonderfully little pollen. The two kinds of flowers often differ much, as just stated, in structure. The petals in the imperfect flowers almost always consist of mere rudiments. The pollen grains are reduced in diameter. In Ononis columnae, 5 of the alternative stamens are rudimentary, and in some species of viola 3 stamens are in this state, 2 retaining their proper function, but being of very small size. In 6 out of 30 of the closed flowers in an Indian violet, name unknown, for the plants have never produced with me perfect flowers, the sepals are reduced from the normal number of 5 to 3. In one section of the Malpighiaceae, the closed flowers, according to A. de Jussieu, are still further modified, for the 5 stamens which stand opposite to the sepals are all aborted, a 6th stamen standing opposite to a petal being alone developed, and this stamen is not present in the ordinary flowers of this species. The style is aborted, and the ovaria are reduced from 3 to 2. Now, although natural selection may well have the power to prevent some of the flowers from expanding, and to reduce the amount of pollen when rendered by the closure of the flowers superfluous, yet hardly any of the above special modifications can have been thus determined, but must have followed from the laws of growth, according to the functional inactivity of parts, during the progress of the reduction of the pollen and the closure of the flowers. It is so necessary to appreciate the important effects of the laws of growth that I will give some additional cases of another kind, namely of differences in the same part or organ due to differences in relative position on the same plant. In the Spanish chestnut and in certain fir trees, the angles of divergence of the leaves differ according to Schott in the nearly horizontal and the upright branches. In the common rue and some other plants, one flower, usually the central or terminal one, opens first, and has 5 sepals and petals, and 5 divisions to the ovarium, while all the other flowers on the plant are tetramerous. In the British adoxa, the uppermost flower generally has 2 calyx lobes, with the other organs tetramerous, while the surrounding flowers generally have 3 calyx lobes, and the other organs pentamerous. In many Compositae and Umbelliferae, and some other plants, the circumferential flowers have their corollas much more developed than those of the centre, and this seems often connected with the abortion of the reproductive organs. It is a mere curious fact, previously referred to, that the echines, or seeds of the circumference and centre, sometimes differ greatly in form, colour, and other characters. In Carthamus and in some other Compositae, in the central echines alone are furnished with a pappus, and in the Hierosus the same head yields echines of 3 different forms. In certain Umbelliferae the exterior seeds, according to Tausch, are orthospermous, and the central one coleospermous, and this is a character which was considered by de Candolle to be in other species of the highest systematic importance. Professor Braun mentions a fumariaceous genus, in which the flowers in the lower part of their spike bear oval, ribbed, or one-seeded nutlets, and in the upper part of the spike, lanceolate, 2-valved and 2-seeded silex. In these several cases, with the exception of the well-developed ray florets, which are of service in making the flowers conspicuous to insects, natural selection cannot, as far as we can judge, have come into play, or only in a quite subordinate manner. All these modifications follow from the relative position and interaction of the parts, and it can hardly be doubted that if all the flowers and leaves on the same plant had been subjected to the same external and internal condition as are the flowers and leaves in certain positions, all would have been modified in the same manner. In numerous other cases we find modifications of structure which are considered by botanists to be generally of a highly important nature, affecting only some of the flowers of the same plant, or occurring on distinct plants which grow together under the same conditions. As these variations seem of no special use to the plants, they cannot have been influenced by natural selection. Of their cause we are quite ignorant, we cannot even attribute them, as in the last class of cases, to any proximate agency, such as relative position. I will give only a few instances. It is so common to observe on the same plant flowers indifferently tetramerous, pentamerous, etc., that I need not give examples. But as numerical variations are comparatively rare when the parts are few, I may mention that, according to de Candolle, the flowers of Papaver bracteatum offer either 2 sepals with 4 petals, which is the common type with poppies, or 3 sepals with 6 petals. The manner in which the petals are folded on the bud is in most groups of very constant morphological character, but Professor Asa Gray states that with some species of Mimulus the estivation is almost as frequently that of the Rhinanthidae as of the Antirrhinidae, to which the latter tribe the genus belongs. Auguste Saint-Hilaire gives the following cases. The genus Xanthaxylon belongs to a division of the Rutaceae with a single ovary, but in some species flowers may be found on the same plant, and even in the same panicle, with either one or two ovaries. In Helianthemum, the capsule has been described as unilocular or trilocular, and in H. mutabile, une lame plus ou moins large s'étend entre le pericarpe et la placenta. In the flowers of Soparnia officinalis, Dr. Masters has observed instances of both marginal and free central placentation. Lastly, St. Hilaire found toward the southern extreme of the range of Gomphia oleiformis two forms which he did not at first doubt were distinct species, but he subsequently saw them growing on the same bush, and adds, Voilà donc dans un même individu, des loges et un style qui se rapprochent tantôt à son axe ventriculaire et tantôt à un gynovis. We thus see that with most plants many morphological changes may be attributed to the laws of growth and the interaction of parts, independently of natural selection. But with respect to Nageli's doctrine of an innate tendency toward perfection or progressive development, can it be said in the case of these strongly pronounced variations that the plants have been caught in the act of progressing toward a higher state of development? On the contrary, I should infer from the mere fact of the parts in question differing or varying greatly on the same plant, that such modifications were of extremely small importance to the plants themselves, of whatever importance they may generally be to us for our classifications. The acquisition of a useless part can hardly be said to raise an organism in the natural scale, and in the case of the imperfect closed flowers above described, if any new principle has to be invoked, it must be one of retrogression rather than of progression, and so it must be with many parasitic and degraded animals. We are ignorant of the exciting cause of the above specified modifications, but if the unknown were to act almost uniformly for a length of time, we may infer that the result would be almost uniform, and in this case all the individuals of the species would be modified in the same manner. From the fact of the above characters being unimportant for the welfare of the species, any slight variations which occurred in them would not have been accumulated and augmented through natural selection. A structure which has been developed through long-continued selection, when it ceases to be of service to a species, generally becomes variable, as we see with rudimentary organs, for it will no longer be regulated by this same power of selection. But when, from the nature of the organism and of the condition, modifications have been induced which are unimportant for the welfare of the species, they may be, and apparently often have been, transmitted in nearly the same state to numerous, otherwise modified descendants. It cannot have been of much importance to the greater number of mammals, birds, or reptiles, whether they were clothed with hair, feathers, or scales. Yet hair has been transmitted to almost all mammals, feathers to all birds, and scales to all true reptiles. A structure, whatever it may be, which is common to many allied forms, is ranked by us as of high systematic importance, and consequently is often assumed to be of high vital importance to the species. Thus, as I am inclined to believe, morphological differences which we consider as important, such as the arrangement of the leaves, the divisions of the flower, or of the ovarium, the positions of the ovules, etc., first appeared in many cases as fluctuating variations, which sooner or later became constant through the nature of the organism and of the surrounding conditions, as well as through the intercrossing of distinct individuals, but not through natural selection. For as these morphological characters do not affect the welfare of the species, any slight deviations in them would not have been governed or accumulated through this latter agency. It is a strange result which we thus arrive at, namely, that characters of slight vital importance to the species are the most important to the systematist. But, as we shall hereinafter see when we treat of the genetic principle of classification, this is by no means so paradoxical as it may at first appear. Although we have no good evidence of the existence in organic beings of an innate tendency towards progressive development, yet this necessarily follows, as I have attempted to show in the 4th chapter, through the continued action of natural selection. For the best definition which has ever been given of a high standard of organisation is the degree to which the parts have been specialised or differentiated, and natural selection tends towards this end, inasmuch as the parts are thus enabled to perform their functions more efficiently. A distinguished zoologist, Mr. St. George Mivart, has recently collected all the objections which have ever been advanced by myself and others against the theory of natural selection as propounded by Mr. Wallace and myself, and has illustrated them with admirable art and force. When thus marshalled, they make a formidable array, and it forms no part of Mr. Mivart's plan to give the various facets and considerations opposed to its conclusions. No slight effort of reason and memory is left to the reader, who may wish to weigh the evidence on both sides. When discussing special cases, Mr. Mivart passes over the effects of the increased use and disuse of parts, which I have always maintained to be highly important, and have treated my variation under domestication at greater length than, as I believe, any other writer. He likewise often assumes that I attribute nothing to variation, independently of natural selection, whereas in the work just referred to I have collected a greater number of well-established cases than can be found in any other work known to me. My judgment may not be trustworthy, but after reading with care Mr. Mivart's book, and after comparing each section with what I have said on the same head, I never before felt so strongly convinced of the general truth of the conclusions here arrived at, subject, of course, in so intricate a subject, to much partial error. All Mr. Mivart's objections will be, or have been, considered in the present volume. The one new point which appears to have struck many readers is that natural selection is incompetent to account for the incipient stages of useful structures. This subject is intimately connected with that of the gradation of the characters, often accompanied by a change of function, for instance, the conversion of a swim bladder into lungs, points of which were discussed in the last chapter under 2 headings. Nevertheless, I will here consider in some detail several of the causes advanced by Mr. Mivart, selecting those which are the most illustrative, as want of space prevents me from considering all. The giraffe, by its lofty structure, much elongated neck, forelegs, head, and tongue, has its whole frame beautifully adapted for browsing on the higher branches of trees. It can thus obtain food beyond the reach of the other ungulata or hoofed animals inhabiting the same country, and this must be a great advantage to it during dearths. The Niata cattle in South America show us how a small difference in structure may make, during such periods, a great difference in preserving an animal's life. These cattle can browse as well as others on grass, but from the projection of the lower jaw they cannot, during the often recurrent droughts, browse on the twigs of trees, reeds, etc., to which food the common cattle and horses are often driven, so that at these times the Niatas perish, if not well fed by their owners. Before coming to Mr. Mivart's objections, it may be well to explain once again how natural selection will act in all ordinary cases. Man has modified some of his animals without necessarily having attended to special points of structure, but simply preserving and breeding from the fleetest animals, as with the racehorse and the greyhound, or as with the gamecock by breeding from the victorious birds. So under nature, with the nascent giraffe, the individuals which were the highest browsers and were able during dearths to reach even an inch or two above the others will often have been preserved, for they will have roamed over the whole country in search of food. That the individuals of the same species often differ slightly in the relative lengths of all their parts may be seen in many works of natural history, in which careful measurements are given. These slight proportional differences, due to the laws of growth and variation, are not of the slightest use or importance to most species, but it will have been otherwise with the nascent giraffe, considering its probable habits of life, for those individuals which had some one part or several parts of their bodies rather more elongated than usual would generally have survived. These will have intercrossed and left offspring, either inheriting the same bodily peculiarities, or with a tendency to vary again in the same manner, while the individuals less favoured in the same respects will have been the most liable to perish. We see here that there is no need to separate single pairs, as man does when he methodically improves a breed. Natural selection will preserve and thus separate all the superior individuals, allowing them freely to intercross, and will destroy all the inferior individuals. By this process, long continued, which exactly corresponds to what I have called unconscious selection by man, combined no doubt in a more important manner with the inherited effects of the increased use of parts, it seems to me almost certain that an ordinary hoofed quadruped might be converted into a giraffe. To this conclusion Mr. Mivart brings forward two objections. One is that the increased size of the body would obviously require an increased supply of food, and he considers it as very problematical whether the disadvantages thence arising would not, in times of scarcity, more than counterbalance the advantages. But as the giraffe actually does exist in large numbers in Africa, and as some of the largest antelopes in the world, taller than an ox, abound there, why should we doubt that, as far as size is concerned, intermediate gradations could formerly have existed there, subjected as now to severe dearths? Assuredly, the being able to reach, at each stage of increased size, to a supply of food left untouched by other hoofed quadrupeds of the country would have been of some advantage to the nascent giraffe. Nor must we overlook the fact that increasing bulk would act as little protection against almost all beasts of prey, excepting the lion, and against this animal. Its tall neck, and the taller the better, would, as Mr. Chauncey Wright has remarked, serve as a watchtower. It is from this cause, as Sir S. Baker remarks, that no animal is more difficult to stalk than the giraffe. This animal also uses its long neck as a means of offence or defence, by violently swinging its head around with stump-like horns. The preservation of each species can rarely be determined by any one advantage, but by the union of all, great and small. Mr. Mivart then asks, and this is his second objection, if natural selection be so potent, and if high browsing be so great an advantage, why has not any other hoofed quadruped acquired a long neck and a lofty stature, besides the giraffe, and, to a lesser degree, the camel, guanaco, and macrauchenia? Or, again, why has not any member of the group acquired a long proboscis? With respect to South Africa, which was formerly inhabited by numerous herds of the giraffe, the answer is not difficult, and can be best given by an illustration. In every meadow in England in which trees grow, we see the lower branches trimmed or planed to an exact level by the browsing of the horses or cattle. And what advantage would it be, for instance, to sheep, if kept there, to acquire slightly longer necks? In every district some kind of animal will almost certainly be able to browse higher than the others, and it is almost equally certain that this one kind alone could have had its neck elongated for this purpose, through natural selection and the effects of increased use. In South America, the competition for browsing on the higher branches of the acacias and other trees must be between giraffe and giraffe, and not with the other ungulate animals. Why, in other quarters of the world, various animals belonging to this same order have not acquired either an elongated neck or a proboscis cannot be distinctly answered, but it is as unreasonable to expect a distinct answer to such a question as why some event in the history of mankind did not occur in one country while it did in another. We are ignorant with respect to the conditions which determine the numbers and range of each species, and we cannot even conjecture what changes of structure would be favourable to its increase in some new country. We can, however, see in a general manner that various causes might have interfered with the development of a long neck or proboscis. To reach the foliage at a considerable height without climbing, for which hoofed animals are singularly ill constructed, implies greatly increased bulk of body, and we know that some areas support singularly few large quadrupeds, for instance South America, though it is so luxuriant, while South Africa abounds with them to an unparalleled degree. Why this should be, so we do not know, nor why the later tertiary periods should have been so much more favourable for their existence than the present time. Whatever the causes may have been, we can see that certain districts and times would have been much more favourable than others for the development of so large a quadruped as the giraffe. In order that an animal should acquire some structures specially and largely developed, it is almost indispensable that several other parts should be modified and co-adapted. Although every part of the body varies slightly, it does not follow that the necessary parts should always vary in the right direction and to the right degree. With the different species of our domesticated animals, we know that the parts vary in a different manner and degree, and that some species are more variable than others. Even if the fitting variations did arise, it does not follow that natural selection would be able to act on them and produce a structure which apparently would be beneficial to the species. For instance, if the number of individuals existing in a country is determined chiefly through destruction by beasts of prey, by external or internal parasites, etc., as seems often to be the case, then natural selection will be able to do little, or it will be greatly retarded in modifying any particular structure for obtaining food. Lastly, natural selection is a slow process, and the same favourable conditions must long endure in order that any marked effect should thus be produced. Except by assigning such general and vague reasons, we cannot explain why, in many quarters of the world, hoofed quadrupeds have not acquired much elongated necks or other means for browsing on higher branches of trees. Objections of the same nature as the foregoing have been advanced by many writers. In each case, various causes, besides the general ones just indicated, have probably interfered with the acquisition through natural selection of structures, which it is thought would be beneficial to certain species. One writer asks, why has not the ostrich acquired the power of flight? But a moment's reflection will show that an enormous supply of food would be necessary to give this bird of the desert force to move its huge body through the air. Oceanic islands are inhabited by bats and seals, but by no terrestrial mammals. Yet as some of these bats are peculiar species, they must have long inhabited their present homes. Therefore, Sir C. Lyell asks, and assigns through certain reasons in answer, why have not seals and bats given birth on such islands to forms fitted to live on the land? But seals would necessarily be first converted into terrestrial carnivorous animals of considerable size, and bats into terrestrial insectivorous animals. For the former there would be no prey. For the bats, ground insects would serve as food, but these would already be largely preyed upon by the reptiles or birds, which first colonize and abound on most oceanic islands. Gradations of structure, with each stage beneficial to a changing species, will be favoured only under certain peculiar conditions. A strictly terrestrial animal, by occasionally hunting for food in shallow water, then in streams or lakes, might at last be converted into an animal so thoroughly aquatic as to brave the open ocean. But seals would not find on oceanic islands the conditions favourable to their gradual reconversion into a terrestrial form. Bats, as formerly shown, probably acquired their wings by at first gliding through the air from tree to tree, like the so-called flying squirrels, for the sake of escaping from their enemies, or for avoiding falls. But when the power of true flight had once been acquired, it would never be reconverted back, at least for the above purposes, into the less efficient power of gliding through the air. Bats might indeed, like many birds, have had their wings greatly reduced in size or completely lost through disuse, but in this case it would be necessary that they should first have acquired the power of running quickly on the ground, by the aid of their hind legs alone, so as to compete with the birds and other ground animals, and for such a change a bat seems singularly ill-fitted. These conjectural remarks have been made merely to show that a transition of structure, with each step beneficial, is a highly complex affair, and there is nothing strange in a transition not having occurred in any particular case. Lately, more than one writer has asked why have some animals had their mental powers more highly developed than others, as such development would be advantageous to all. Why have not apes acquired the intellectual powers of man? Various causes could be assigned, but as they are conjectural, and their relative probability cannot be weighed, it would be useless to give them. A definite answer to the latter question ought not to be expected, seeing that one can solve the simpler problem, why of two races of savages has one risen higher in the scale of civilization than the other, and this apparently implies increased brain power. We will return to Mr. Mivart's other objections. Insects often resemble, for the sake of protection, various objects, such as green or decayed leaves, dead twigs, bits of lichen, flowers, spines, excrement of birds, and living insects. But to this latter point I shall hereafter recur. The resemblance is often wonderfully close, and is not confined to colour, but extends to form and even to the manner in which the insects hold themselves. The caterpillars, which project motionless like dead twigs from the bushes on which they feed, offer an excellent instance of a resemblance of this kind. The cases of this imitation of such objects as the excrement of birds are rare and exceptional. On this head Mr. Mivart remarks, as according to Mr. Darwin's theory, there is a constant tendency to indefinite variation, and as the minute incipient variations will be in all directions, they must tend to neutralize each other, and, at first, to form such unstable modifications that it is difficult, if not impossible, to see how such indefinite oscillations of infinitesimal beginnings can ever build up a sufficiently appreciable resemblance to a leaf, bamboo, or other object, for natural selection to seize upon and perpetuate. But in all the foregoing cases, the insects in their original state no doubt presented some rude and accidental resemblance to an object commonly found in the stations frequented by them. Nor is this at all improbable, considering the almost infinite number of surrounding objects, and the diversity in form and colour of the hosts of insects which exist. As some rude resemblance is necessary for the first start, we can understand how it is that the larger and higher animals do not, with the exception, as far as I know, of one fish, resemble, for the sake of protection, special objects, but only the surface which commonly surrounds them, and this chiefly in colour. Assuming that an insect originally happened to resemble in some degree a dead twig or decayed leaf, and that it varied slightly in many ways, then all the variations which rendered the insect at all more like any such object, and thus favoured its escape, would be preserved, while other variations would be neglected and ultimately lost, or, if they rendered the insect at all less like the imitated object, they would be eliminated. There would indeed be force in Mr. Mivart's objection if we were to attempt to account for the above resemblances, independently of natural selection, through mere fluctuating variability, but as the case stands, there is none. Nor can I see any force in Mr. Mivart's difficulty with respect to the last touches of perfection in the mimicry, as is the case given by Mr. Wallace of a walking-stick insect, Ceroxylus lacerus, which resembles a stick grown over by a creeping moss, or Jungermannia. So close was this resemblance that a native Dyak maintained that the foliaceous excrescences were really moss. Insects are preyed upon by birds and other enemies whose sight is probably sharper than ours, and every grade in resemblance which aided an insect to escape notice or detection would tend toward its preservation, and the more perfect the resemblance, so much the better for the insect. Considering the nature of the differences between the species in the group which includes the above Ceroxylus, there is nothing improbable in this insect having varied in the irregularities on its surface, and in these having become more or less green-coloured. For in every group the characters which differ in the several species are the most apt to vary, while the genetic characters, or those common to all the species, are the most constant. The Greenland whale is one of the most wonderful animals in the world, and the baleen, or whalebone, one of its greatest peculiarities. The baleen consists of a row on each side of the upper jaw of about 300 plates, or laminae, which would stand close together transversely to the longer axis of the mouth. Within the main row there are some subsidiary rows. The extremities and inner margins of all the plates are frayed into stiff bristles, which clothe the whole gigantic palate, and serve to strain or sift the water, and thus to secure the minute prey on which these great animals subsist. The middle and longest lamina in the Greenland whale is 10, 12, or even 15 feet in length, but in the different species of cetaceans there are gradations in length, the middle lamina being in one species, according to Scoresby, 4 feet, in another 3, in another 18 inches, and in the Balænoptera rostara only about 9 inches in length. The quality of the whalebone also differs in the different species. With respect to the baleen, Mr. Mivart remarks that if it had once attained such a size and development as to be at all useful, then its preservation and augmentation within serviceable limits would be promoted by natural selection alone. But how to obtain the beginning of such a useful development? In answer, it may be asked, why should not the early progenitors of the whales with baleen have possessed a mouth constructed something like the lamellated beak of a duck? Ducks, like whales, subsist by sifting the mud and water, and the family has sometimes been called criblators, or sifters. I hope that I may not be misconstrued into saying that the progenitors of whales did actually possess mouths lamellated like the beak of a duck. I wish only to show that this is not incredible, and that the immense plates of baleen in the Greenland whale might have been developed from such lamellae by finely graduated steps, each of service to its possessor. The beak of a shoveler duck, Spatula clypeata, is a more beautiful and complex structure than the mouth of a whale. The upper mandible is furnished on one side, in the specimen examined by me, with a row or comb formed of 188 thin elastic lamellae, obliquely beveled so as to be pointed and placed transversely to the longer axis of the mouth. They arise from the palate, and are attached by a flexible membrane to the sides of the mandible. Those standing toward the middle are the longest, being about 1/3 of an inch in length, and they project 14/100ths of an inch beneath the edge. At their bases there is a short subsidiary row of obliquely transverse lamellae. In these several respects they resemble the plates of baleen in the mouth of a whale, but towards the extremity of the beak they differ much, as they project inward instead of straight downward. The entire head of the shoveler, though incomparably less bulky, is about 1/18th the length of the head of a moderately large Balænoptera rostrata, in which species the baleen is only 9 inches long, so that if we were to make the head of the shoveler as long as that of the Balænoptera, the laminae would be 6 inches in length, that is, 2/3 the length of the baleen in this species of whale. The lower mandible of the shoveler duck is furnished with lamellae of equal length with those above, but finer, and in being thus furnished it differs conspicuously from the lower jaw of a whale, which is destitute of baleen. On the other hand, the extremities of these lower lamellae are frayed into fine bristly points, so that they thus curiously resemble the plates of baleen. In the genus Prion, a member of the distinct family of the petrels, the upper mandible alone is furnished with lamellae, which are well developed and project beneath the margin, so that the beak of this bird resembles in this respect the mouth of a whale. From the highly developed structure of the shoveler's beak we may proceed, as I have learned from information and specimens sent to me by Mr. Salvin, without any great break as far as fitness for sifting is concerned, through the beak of Meriganta armata, and in some respects through that of the Aix sponsa, to the beak of the common duck. In this latter species the lamellae are much coarser than in the shoveler, and are firmly attached to the sides of the mandible. They are only about 50 in number on each side, and do not project at all beneath the margin. They are square-tipped, and are edged with translucent, hardish tissue, as if for crushing food. The edges of the lower mandible are crossed by numerous fine ridges, which project very little. Although the beak is thus very inferior as a sifter to that of the shoveler, yet this bird, as every one knows, constantly uses it for that purpose. There are other species, as I heard from Mr. Salvin, in which the lamellae are considerably less developed than in the common duck, but I do not know whether they use their beaks for sifting the water. Turning to another group in the same family, in the Egyptian goose, Chinolopex, the beak closely resembles that of the modern duck, but the lamellae are not so numerous, nor so distinct from each other, nor do they project so much inward. Yet this goose, as I am informed by Mr. E. Bartlett, uses its bill like a duck by throwing the water out at the corners. Its chief food, however, is grass, which it crops like the common goose. In this latter bird the lamellae of the upper mandible are much coarser than in the common duck, almost confluent, about 27 in number on each side, and terminating upward in teeth-like knobs. The palate is also covered with hard rounded knobs. The edges of the lower mandible are serrated with teeth much more prominent, coarser and sharper than in the duck. The common goose does not sift the water, but uses its beak exclusively for tearing or cutting herbage, for which purpose it is so well fitted that it can crop grass closer than almost any other animal. There are other species of geese, as I hear from Mr. Bartlett, in which the lamellae are less developed than in the common goose. We thus see that a member of the duck family, with a beak constructed like that of a common goose and adapted solely for grazing, or even a member with a beak having less well-developed lamellae, might be converted by small changes into a species like the Egyptian goose, this into one like the common duck, and lastly into one like the shoveler, provided with a beak almost exclusively adapted for sifting the water, for this bird would hardly use any part of its beak except the hooked tip for seizing or tearing solid food. The beak of a goose, as I may add, might also be converted by small changes into one provided with prominent recurved teeth, like those of the merganser, a member of the same family, serving for the widely different purpose of securing live fish. Returning to the whales, Hyperodon bidens is destitute of true teeth in an efficient condition, but its palate is roughened, according to Laccipidae, with small, unequal, hard points of horn. There is therefore nothing improbable in supposing that some early cetacean form was provided with similar points of horn on the palate, but rather more regularly placed, and which, like the knobs on the beak of the goose, aided it in seizing or tearing its food. If so, it will hardly be denied that the points might have been converted, through variation and natural selection, into lamellae, as well developed as that of the Egyptian goose, in which case they would have been used both for seizing objects and for sifting the water. Then into lamellae like those of the domestic duck, and so onward until they became as well constructed as those of the shoveler, in which case they would have served exclusively as a sifting apparatus. From this stage, in which the lamellae would be 2/3 the length of the plates of baleen in the Balænoptera rostrata, gradations, which may be observed in still existing cetaceans, lead us onward to the enormous plates of baleen in the Greenland whale. Nor is there the least reason to doubt that each step in this scale might have been as serviceable to certain ancient cetaceans, with the functions of the parts slowly changing during the progress of development, as are the gradations in the beaks of the differing existing members of the duck family. We should bear in mind that each species of duck is subjected to a severe struggle for existence, and that the structure of every part of its frame must be well adapted to its conditions of life. The Pleuronectidae, or flatfish, are remarkable for their asymmetrical bodies. They rest on one side, in the greater number of species on the left, but in some on the right side, and occasionally reversed adult specimens occur. The lower or resting surface resembles at first sight the ventral surface of an ordinary fish. It is of white colour, less developed in many ways than on the upper side, with the lateral fins often of smaller size. But the eyes offer the most remarkable peculiarity, for they are both placed on the upper side of the head. During early youth, however, they stand opposite to each other, and the whole body is then symmetrical, with both sides equally coloured. Soon the eye proper to the lower side begins to glide slowly round the head to the upper side, but does not pass right through the skull, as was formerly thought to be the case. It is obvious that unless the lower eye did this travel round, it could not be used by the fish while lying in its habitual position on one side. The lower eye would also have been liable to be abraded by the sandy bottom. That the Pleuronectidae are remarkably adapted by their flattened and asymmetrical structure for their habits of life is manifest from several species, such as soles, flounder, etc., being excessively common. The chief advantages thus gained seem to be protection from their enemies, and facility for feeding on the ground. The different members, however, of the family present, as Schiödte remarks, a long series of forms exhibiting a gradual transition from Hippoglossus pinguis, which does not in any considerable degree alter the shape in which it leaves the ovum, to the soles, which are entirely thrown off to one side. Mr. Mivart has taken up this case, and remarks that a sudden spontaneous transformation in the position of the eyes is hardly conceivable, in which I quite agree with him. He then adds, if the transit were gradual, then how such transit of one eye of a minute fraction of the journey toward the other side of the head could benefit the individual is indeed far from clear. It seems even that such an incipient transformation must rather have been injurious. But he might have found an answer to his objection in the excellent observations published in 1867 by Malm. The Pleuronectidae, while very young and still symmetrical, with their eyes standing on opposite sides of the head, cannot long retain a vertical position, owing to the excessive depth of their bodies, the small size of their lateral fins, and to their being destitute of a swim bladder. Hence, soon growing tired, they fall to the bottom on one side. While thus at rest, they often twist, as Malm observed, the lower eye upward, to see above them, and they do so vigorously that the eye is pressed hard against the upper part of the orbit. The forehead between the eyes consequently becomes, as could plainly be seen, temporarily contracted in breadth. On one occasion Malm saw a young fish raise and depress the lower eye through an angular distance of about 70 degrees. We should remember that the skull at this early age is cartilaginous and flexible, and so it readily yields to muscular action. It is also known with the higher animals, even after early youth, that the skull yields and is altered in shape if the skin or muscles be permanently contracted through diseases or some accident. With long-eared rabbits, if one ear flops forward and downward, its weight drags forward all the bones of the skull on the same side, of which I have given a figure. Malm states that the newly hatched young of perches, salmon, and several other symmetrical fishes have the habit of occasionally resting on one side at the bottom, and he has observed that they often then strain their lower eyes so as to look upward, and their skulls are thus rendered rather crooked. These fishes, however, are soon able to hold themselves in a vertical position, and no permanent effect is thus produced. With the Pleuronectidae, on the other hand, the older they grow, the more habitually they rest on one side, owing to the increasing flatness of their bodies, and a permanent effect is thus produced at the form of the head, and on the position of the eyes. Judging from analogy, the tendency to distortion would no doubt be increased through the principle of inheritance. Schiödte believes, in opposition to some other naturalists, that the Pleuronectidae are not quite symmetrical even in the embryo, and if this be so, we could understand how it is that certain species, while young, habitually fall over and rest on the left side, and other species on the right side. Malm adds, in confirmation of the above view, that the adult Trachypterus arcticus, which is not a member of the Pleuronectidae, rests on the left side at the bottom, and swims diagonally through the water, and this fish, of the two sides of its head, are said to be somewhat dissimilar. Our great authority on fishes, Dr. Gunther, concludes his abstract of Malm's paper by remarking that the author gives a very simple explanation of the abnormal condition of the pleuronectinoids. We thus see that the first stages of the transit of the eye from one side of the head to the other, which Mr. Mivart considers would be injurious, may be attributed to the habit, no doubt beneficial to the individual and to the species, of endeavouring to look upward with both eyes, while resting on one side at the bottom. We may also attribute to the inherited effects of use the fact of the mouth in several kinds of flatfish being bent toward the lower surface, with the jawbones stronger and more effective on this, the eyeless side of the head, than on the other, for the sake, as Dr. Tronquoyar supposes, of feeding with ease on the ground. Disuse, on the other hand, will account for less developed conditions of the whole inferior half of the body, including the lateral fins, though Yarrell thinks that the reduced size of these fins is advantageous to the fish, as there is so much less room for the action than with the larger fins above. Perhaps the lesser number of teeth, in the proportion of 4 to 7 in the upper halves of the two jaws of the Pliaceae, to 25 to 30 in the lower halves, may likewise be accounted for by disuse. From the colourless state of the ventral surface of many fishes, and from many other animals, we may reasonably suppose that the absence of colour in flatfish on the side, whether it be right or left, which is undermost, is due to the exclusion of light, but it cannot be supposed that the peculiar speckled appearance of the upper side of the sole is so like the sandy bed of the sea, or the power in some species, as recently shown by Pouchet, of changing their colour in accordance with the surrounding surface, or the presence of bony tubercles in the upper side of the turbot, are due to the action of the light. Here natural selection has probably come into play, as well as in adapting the general shape of the body of these fishes and many other peculiarities to their habits of life. We should keep in mind, as I have before insisted, that the inherited effects of the increased use of parts, and perhaps of their disuse, will be strengthened by natural selection. For all spontaneous variations in the right direction will be thus preserved, as will those individuals which inherit in the highest degree the effects of the increased beneficial use of any part. How much to attribute in each particular case to the effects of use, and how much to natural selection, it seems impossible to decide. I may give another instance of a structure which apparently owes its origin exclusively to use or habit. The extremity of the tail in some American monkeys has been converted into a wonderfully perfect prehensile organ, and serves as a fifth hand. A reviewer, who agrees with Mr. Mivart in every detail, remarks on this structure. It is impossible to believe that in any number of ages the first slight incipient tendency to grasp could preserve the lives of the individuals possessing it, or favour their chance of having and of rearing offspring. But there is no necessity for any such belief. Habit, and this almost implies that some benefit of great or small is thus derived, would in all probability suffice for the work. Brehm saw the young of an African monkey, Cercopithecus, clinging to the under surface of their mother by their hands, and at the same time they hooked their little tails round that of their mother. Professor Henslow kept in confinement some harvest mice, Mus mesorius, which do not possess a structurally prehensive tail, but he frequently observed that they curled their tails round the branches of a bush placed in the cage, and thus aided themselves in climbing. I have received an analogous account from Dr. Gunther, who has seen a mouse thus suspend itself. If the harvest mouse had been more strictly arboreal, it would perhaps have had its tail rendered structurally prehensile, as is the case with some members of the same order. Why Cercopithecus, considering its habits while young, has not become thus provided, it would be difficult to say. It is, however, possible that the long tail of this monkey may be more of service to it as a balancing organ in making its prodigious leaps than as a prehensile organ. The mammary glands are common to the whole class of mammals, and are indispensable for their existence. They must, therefore, have been developed at an extremely remote period, and we can know nothing positively about their manner of development. Mr. Mivart asks, is it conceivable that the young of any animal was ever saved from destruction by accidentally sucking a drop of scarcely nutritious fluid from an accidentally hypertrophied cutaneous gland of its mother? And even if one were so, what chance was there of the perpetuation of such a variation? But the case is not here put fairly. It is admitted by most evolutionists that mammals are descended from a marsupial form, and if so, the mammary glands will have at first developed within the marsupial sac. In the case of fish, Hippocampus, the eggs are hatched, and the young are reared for a time within a sac of this nature, and an American naturalist, Mr. Lockwood, believes from what he has seen of the development of the young that they are nourished by a secretion from the cutaneous glands of the sac. Now, with the early progenitors of mammals, almost before they deserve to be thus designated, is it not at least possible that the young might have been similarly nourished? and in this case the individuals which secreted a fluid in some degree or manner the most nutritious, so as to partake of the nature of milk, would in the long run have reared a larger number of well-nourished offspring than would the individuals which secreted a poorer fluid, and thus the cutaneous glands, which are the homologues of the mammary glands, would have been improved or rendered more effective. It accords with the widely extended principle of specialization that the glands over a certain space of the sac should have become more highly developed than the remainder, and that they would then have formed a breast, but at first without a nipple, as we see in the Ornithorhynchus at the base of the mammalian series. Through what agency the glands over a certain space become more highly specialized than the others, I will not pretend to decide. Whether in part through compensation of growth, the effects of youth, or natural selection. The development of the mammary glands would have been of no service, and could not have been effected through natural selection, unless the young at the same time were able to partake of the secretion. There is no greater difficulty in understanding how young mammals have instinctively learned to suck the breast, than in understanding how unhatched chickens have learned to break the egg-shell by tapping against it with their specially adapted beaks, or how a few hours after leaving the shell they have learned to pick up grains of food. In such cases the most probable solution seems to be that the habit was at first acquired by practice at a more advanced age, and afterwards transmitted to the offspring at an earlier age. But the young kangaroo is said not to suck, only to cling to the nipple of its mother, who has the power of injecting milk into the mouth of her helpless, half-formed offspring. On this head Mr. Mivart remarks, did no special provision exist? The young one must infallibly be choked up by the intrusion of the milk into the windpipe? But there is a special provision. The larynx is so elongated that it arises up into the posterior end of the nasal passage, and is thus enabled to give free entrance to the air for the lungs, while the milk passes harmlessly on each side of this elongated larynx, and so safely attains the gullet behind it. Mr. Mivart then asks, how did natural selection remove in the adult kangaroo, and in most other mammals, on the assumption that they are descended from a marsupial form, this at least perfectly innocent and harmless structure? It may be suggested in answer that the voice, which is certainly of high importance to many mammals, could hardly have been used with full force as long as the larynx entered the nasal passage, and Professor Flower has suggested to me that this structure would have greatly interfered with an animal swallowing solid food. We will now turn for a short space to the lower divisions of the animal kingdom. The echinodermata, starfishes, sea urchins, etc., are furnished with remarkable organs called pedicellary, which consist, when well developed, of a tridactyl forceps, that is, of one formed of 3 serrated arms, neatly fitting together and placed on the summit of a flexible stem moved by muscles. These forceps can seize and firmly hold of any object, and Alexander Agassiz has seen an echinus or sea urchin rapidly passing particles of excrement from forceps to forceps down certain lines of its body, in order that its shell should not be fouled. But there is no doubt that, besides removing dirt of all kinds, they subserve other functions, and one of these, apparently, is defence. With respect to these organs, Mr. Mivart, as on so many previous occasions, asks, what would be the utility of the first rudimentary beginnings of such structures, and how could such incipient buddings ever have preserved the life of a single echinus? He adds, not even the sudden development of the snapping action would have been beneficial without the freely movable stalk, nor could the latter have been efficient without the snapping jaws. Yet no minute, nearly indefinite variations could have simultaneously evolved these complex coordinations of structure. To deny this seems to do no less than to affirm a startling paradox. Paradoxical as this may appear to Mr. Mivart, tridactyl forcepses, immovably fixed at the base but capable of a snapping action, certainly do exist on some starfishes, and this is intelligible if they serve, at least in part, as a means of defence. Mr. Agassiz, to whose great kindness I am indebted for much information on the subject, informs me that there are other starfishes in which one of the 3 arms of the forceps is reduced to a support for the other 2, and again other genera in which the 3rd arm is completely lost. In Echinosis, the shell is described by M. Perrier as bearing 2 kinds of pedicellariae, one resembling that of Echinus, and the other those of Spatangus, and in such cases are always interesting as affording the means of apparently sudden transitions through the abortion of one of the 2 states of an organ. With respect to the steps by which these curious organs have evolved, Mr. Agassiz infers from his own researches, and those of Mr. Müller, that both in starfishes and sea urchins the pedicellariae have undoubtedly been looked at as modified spines. This must be inferred from their manner of development in the individual, as well as from a long and perfect series of gradations in different species and genera, from simple granules to ordinary spines to perfect tridactyl pedicellariae. This gradation extends even to the manner in which ordinary spines and the pedicellariae, with their supporting calcareous rods, are articulated to the shell. In certain genera of starfishes, the very combinations needed to show that the pedicellariae are only modified branching spines may be found. Thus we have fixed spines with 3 equidistant, serrated, movable branches articulated to near their bases, and higher up on the same spine 3 other movable branches. Now when the latter arise from the summit of a spine, they form in fact a rude tridactyl pedicellariae, and as such may be seen on the same spine together with the 3 lower branches. In this case, the identity in nature between the arms of the pedicellariae and the movable branches of a spine is unmistakable. It is generally admitted that the ordinary spines serve as a protection, and if so, there can be no reason to doubt that those furnished with serrated and movable branches likewise serve for the same purpose, and they would thus serve still more effectively as soon as by meeting together they acted as a prehensile or snapping apparatus. Thus every gradation from an ordinary fixed spine to a fixed pedicellariae would be of service. In certain genera of starfishes, these organs, instead of being fixed or borne on an immovable support, are placed at the summit of a flexible and muscular, though short, stem, and in this case they probably subserve some additional function besides defence. In the sea urchins, the steps can be followed by which a fixed spine becomes articulated to the shell, and is thus rendered movable. I wish I had space here to give a fuller abstract of Mr. Agassiz's interesting observations on the development of the pedicellariae. All possible gradations, as he adds, may likewise be found between the pedicellariae of the starfishes and the hooks of the ophiurians, another group of the echinodermata, and again between the pedicellariae of sea urchins and the anchors of the holothuriae, also belonging to the same great class. Certain compound animals, or zoophytes as they have been termed, namely the polyzoa, are provided with curious organs called avicularia. These differ much in structure in the different species. In their most perfect condition they curiously resemble the head and beak of a vulture in miniature, seated on the neck and capable of movement, as is likewise the lower jaw or mandible. In one species observed by me, all the avicularia on the same branch often moved simultaneously backwards and forwards, with the lower jaw widely open, through an angle of about 90 degrees in the course of 5 seconds, and their movement caused the whole polyzoary to tremble. When the jaws are touched with a needle, they seize it so firmly that the branch can thus be shaken. Mr. Mivart adduces this case chiefly on account of the supposed difficulty of organs, namely the avicularia of the polyzoa and the pedicellariae of the echinodermata, which he considers as essentially similar, having been developed through natural selection in widely distinct divisions of the animal kingdom. But as far as the structure is concerned, I can see no similarity between tridactyle pedicellariae and avicularia. The latter resembles somewhat more closely the chelae or pincers of crustaceans, and Mr. Mivart might have adduced with equal appropriateness this resemblance as a special difficulty, or even their resemblance to the head and beak of a bird. The avicularia are believed by Mr. Busk, Dr. Smith, and Dr. Nietzsche, naturalists who have carefully studied this group, to be homologous with the zooids and their cells which composite the zoophyte. The movable lip or lid of the cell corresponding with the lower and movable mandible of the avicularium. Mr. Busk, however, does not know of any gradations now existing between a zooid and an avicularium. It is therefore impossible to conjecture by what serviceable gradations the one could have been converted into the other, but it by no means follows from this that such gradations have not existed. As the chelae of crustaceans resemble in some degree the avicularia of polyzoa, both serving as pincers, it may be worth while to show that with the former a long series of serviceable gradations still exists. In the first and simplest stage, the terminal segment of the limb shuts down either on the square summit of the broad penultimate segment, or against the whole side, and is thus enabled to catch hold of an object. But the limb still serves as an organ of locomotion. We next find one corner of the broad penultimate segment slightly prominent, sometimes furnished with irregular teeth, and against these the terminal segment shuts down. But an increase in the size of this projection, with its shape as well as that of the terminal segment slightly modified and improved, the pincers are rendered more and more perfect, until at last we have an instrument as efficient as the chelae of a lobster. And all these gradations can actually be traced. Besides the avicularia, the polyzoa possess curious organs called vibracula. These generally consist of long bristles, capable of movement and easily excited. In one species examined by me, the vibracula were slightly curved and serrated along the outer margin, and all of them on the same polyzoary often moved simultaneously, so that, acting like long oars, they swept a branch rapidly across the object glass of my microscope. When a branch was placed on the face, the vibracula became entangled, and they made violent efforts to free themselves. They are supposed to serve as a defence, and may be seen, as Mr. Busk remarks, to sweep slowly and carefully over the surface of the polyzoary, removing what might be noxious to the delicate inhabitants of the cells when their tentacula are protruded. The avicularia, like the vibracula, probably serve for defence, but they also catch and kill small living animals, which it is believed are afterwards swept by the currents within the reach of the tentacula of the zooids. Some species are provided with avicularia and vibracula, some with avicularia alone, and a few with vibracula alone. It is not easy to imagine two objects more widely different in appearance than a bristle or vibraculum and an avicularium like the head of a bird, yet they are almost certainly homologous, and have been developed from the same common source, namely a zooid with its cell. Hence we can understand how it is that these organs gradate in some cases, as I am informed by Mr. Busk, into each other. Thus, with the avicularia of some species of Lepralia, the movable mandible is so much produced, and is so like that of a bristle, that the presence of the upper or fixed beak alone serves to determine its avicularian nature. The vibracula may have been directly developed from the lips of the cells, without having passed through the avicularian stage, but it seems more probable that they have passed through this stage, as during the early stages of the transformation the other parts of the cell, with the included zooid, could hardly have disappeared at once. In many cases the vibracula have a grooved support at the base, which seems to represent the fixed beak, though this support in some species is quite absent. This view of the development of the vibracula, if trustworthy, is interesting, for supposing that all the species provided with avicularia had become extinct, no one with the most vivid imagination would ever have thought that the vibracula had originally existed as a part of an organ resembling a bird's head, or an irregular box or hood. It is interesting to see two such widely different organs developed from a common origin, and as the movable lip of the cell serves as a protection of the zooid, there is no difficulty in believing that all the gradations, by which the lip became converted first into the lower mandible of an avicularium, and then into an elongated bristle, likewise served as a protection in different ways and under different circumstances. In the vegetable kingdom, Mr. Mivart only alludes to two cases, namely, the structure of the flowers of orchids and the movements of climbing plants. With respect to the former, he says, the explanation of their origin is deemed thoroughly unsatisfactory, utterly insufficient to explain the incipient, infinitesimal beginnings of structures which are of utility only when they are considerably developed. As I have fully treated this subject in another work, I will here give only a few details, on one alone of the most striking peculiarities of the flowers of orchids, namely their pollinia. A pollinum, when highly developed, consists of a mass of pollen grains affixed to an elastic footstalk or caudicle, and this to a little mass of extremely viscid matter. The pollinia are by this means transported by insects from one flower to the stigma of another. In some orchids there is no caudicle to the pollen masses, and the grains are merely tied together by fine threads. But as these are not confined to orchids, they need not here be considered. Yet I may mention that at the base of the Orchidus series, in Cyberspadium, we can see how the threads were probably first developed. In other orchids the threads cohere at one end of the pollen masses, and this forms the first or nascent trace of a claudicle. This is the origin of the claudicle. Even when of considerable length and highly developed, we have good evidence in the aborted pollen grains, which can sometimes be detected embedded within the central and solid parts. With respect to the second chief peculiarity, namely the little mass of viscid matter attached to the end of the claudicle, a long series of gradations can be specified, each of plain service to the plant. In most flowers belonging to other orders, the stigma secretes a little viscid matter. Now, in certain orchids, similar viscid matter is secreted, but in much larger quantities by one alone of the three stigmas, and this stigma, perhaps in consequence of the copious secretion, is rendered sterile. When an insect visits a flower of this kind, it rubs off some of the viscid matter, and thus at the same time drags away some of the pollen grains. From this simple condition, which differs but little from that of a multitude of common flowers, there are endless gradations, to species in which the pollen mass terminates in a very short free claudicle, to others in which the claudicle becomes firmly attached to the viscid matter, which the sterile stigmata itself much modified. In this latter case we have a pollinium in its most highly developed and perfect condition. He who will carefully examine the flowers of orchids for himself will not deny the existence of the above series of gradations, from a mass of pollen grains merely tied together by threads, with the stigmata differing but little from that of the ordinary flowers, to a highly complex pollinium, admirably adapted for transportal by insects. Nor will he deny that all the gradations in the several species are admirably adapted in relation to the general structure of each flower for its fertilization by different insects. In this and almost every other case, the inquiry must be pushed further backwards, and it must be asked, how did the stigma of an ordinary flower become viscid? But as we do not know the full history of any one group of beings, it is as useless to ask as it is hopeless to attempt answering such questions. We will now turn to climbing plants. These can be arranged in a long series, from those which simply twine round a support, to those which I have called leaf climbers, and to those provided with tendrils. In these two latter cases the stems have generally, but not always, lost the power of twining, though they retain the power of revolving, which the tendrils likewise possess. The gradations from leaf climbers to tendril bearers are wonderfully close, and certain plants may be differently placed in either class. But in ascending the series from simple twiners to leaf climbers, an important quality is added, namely sensitiveness to a touch, by means of the footstalks of the leaves of the flowers, or these modified and converted into tendrils are excited to bend round and clasp the touching object. He who will read my memoir on these plants will, I think, admit that all the gradations in function and structure between simple twiners and tendril bearers are in each case beneficial in a high degree to the species. For instance, it is clearly a great advantage to a twining plant to become a leaf climber, and it is probable that every twiner which possessed leaves with long footstalks would have been developed into a leaf climber, if the footstalks had possessed in any slight degree the requisite sensitiveness to a touch. As twining is the simplest means of ascending a support, and forms the basis of our series, it may naturally be asked, how did plants acquire this power in an incipient degree, afterwards to be improved and increased through natural selection? The power of twining depends, firstly, on the stems while young being extremely flexible, but this is a character common to many plants which are not climbers, and secondly, on their continually bending to all points of the compass, one after another in succession in the same order. By this movement the stems are inclined to all sides, and are made to move round and round. As soon as the lower part of a stem strikes against any object and is stopped, the upper part still goes on bending and revolving, and thus necessarily twines round and up the support. The revolving movement ceases after the early growth of each shoot. As in many widely separated families of plants, single species and single genera possess the power of revolving, and have thus become twiners. They must have independently acquired it, and cannot have inherited it from a common progenitor. Hence I was led to predict that some slight tendency to a movement of this kind would be found to be far from uncommon with plants which did not climb, and that this had afforded the basis for natural selection to work on and improve. When I made this prediction, I knew of only one imperfect case, namely of the young flower peduncles of a Moreanda, which revolved slightly and irregularly, like the stems of twining plants, but without making any use of this habit. Soon afterwards Fritz Müller discovered that the young stems of Alissima and of a Linum, plants which do not climb and are widely separated in the natural system, revolved plainly, though irregularly, and he states that he has reason to suspect that this occurs with some other plants. These slight movements appear to be of no service to the plants in question, Anyhow, they are not of the least use in the way of climbing, which is the point that concerns us. Nevertheless, we can see that if the stems of these plants had been flexible, and if under the conditions to which they are exposed it had profited them to ascend to a height, then the habit of unsightly and irregularly revolving might have been increased and utilized through natural selection, until they had become converted into well-developed twining species. With respect to the sensitiveness of the footstalks of the leaves and flowers and of the tendrils, nearly the same remarks are applicable as in the case of the revolving movements of twining plants. As a vast number of species belonging to widely distinct groups are endowed with this kind of sensitiveness, it ought to be found in a nascent condition in many plants which have not become climbers. This is the case. I observed that the young flower peduncles of the above Morondia curved themselves a little towards the side which was touched. Morin found in several species of oxalis that the leaves and their footstalks moved, especially after exposure to a hot sun, when they were gently and repeatedly touched, or when the plant was shaken. I repeated these observations on some other species of oxalis with the same result. In some of them the movement was distinct, but was best seen in the young leaves. In others it was extremely slight. But it is a more important fact that, according to the high authority of Hofmeister, the young shoots and leaves of all plants move after being shaken, and with climbing plants it is, as we know, only during the early stages of growth that the footstalks and tendrils are sensitive. It is scarcely possible that the above slight movements, due to a touch or shake in the young and growing organs of plants, can be of any functional importance to them. But plants possess, in obedience to various stimuli, powers of movement which are of manifest importance to them. For instance, towards, and more rarely from the light, in opposition to, and more rarely in the direction of, the attraction of gravity, when the nerves and muscles of an animal are excited by galvanism, or by the absorption of strychnine, the consequent movements may be called an incidental result, for the nerves and muscles have not been rendered specially sensitive to these stimuli. So with plants it appears that, from having the power of movement in obedience to certain stimuli, they are excited in an incidental manner by a touch or by being shaken. Hence there is no great difficulty in admitting that, in the case of leaf climbers and tendril bearers, it is this tendency which has been taken advantage of and increased through natural selection. It is, however, probable, from reasons which I have assigned in my memoir, that this will have occurred only with plants which had already acquired the power of revolving, and had thus become twiners. I have already endeavoured to explain how plants become twiners, namely by the increase of a tendency to slight and irregular revolving movements, which were at first of no use to them. This movement, as well as that due to a touch or a shake being the incidental result of the power of moving, gained for other and beneficial purposes. Whether, during the gradual development of climbing plants, natural selection has been aided by the inherent effects of use, I will not pretend to decide. But we know that certain periodical movements, for instance the so-called sleep of plants, are governed by habit. I have now considered enough, perhaps more than enough, of the cases selected with care by a skilful naturalist to prove that natural selection is incompetent to account for the incipient changes of useful structures, and I have shown, as I hope, that there is no great difficulty on this head. A good opportunity has thus been afforded for enlarging a little on gradations of structure, often associated with strange functions, an important subject which was not treated at sufficient length in former editions of this work. I will now briefly recapitulate the foregoing cases. With the giraffe, the continued preservation of the individuals of some extinct high-reaching ruminant, which had the longest necks, legs, etc., and could browse a little above the average height, and the continued destruction of those who could not browse so high, would have sufficed for the production of this remarkable quadruped. But the prolonged use of all the parts, together with inheritance, will have aided in an important manner in their coordination. With the many insects which imitate various objects, there is no improbability in the belief that an accidental resemblance to some common object was in each case the foundation for the preservation of slight variations which made the resemblance at all closer, and this will have been carried on as long as the insect continued to vary, and as long as a more and more perfect resemblance led to its escape from sharp-sighted enemies. In certain species of whales there is a tendency to the formation of irregular little points of horn on the palate, and it seems to be quite within the scope of natural selection to preserve all favourable variations, until the points were converted first into lamellated knobs or teeth, like those on the beak of a goose, then into short lamellae, like those of the domestic ducks, and then into lamellae as perfect as those of the shoveler duck, and finally into the gigantic plates of baleen, as in the mouth of the Greenland whale. In the family of these ducks, the lamellae are first used as teeth, then partly as teeth, and partly as a sifting apparatus, and at last almost exclusively for this latter purpose. With such structures as the above lamellae of horn or whalebone, habit or use can have done little or nothing, as far as we can judge, toward their development. On the other hand, the transportal of the lower eye of a flatfish to the upper side of the head, and the formation of a prehensile tail, may be attributed almost wholly to continued use, together with inheritance. With respect to the mammae of the higher animals, the most probable conjecture is that primordially the cutaneous glands over the whole surface of a marsupial sac secreted a nutritious fluid, and that these glands were improved in function through natural selection, and concentrated into a confined area, in which case they would have formed a mamma. There is no more difficulty in understanding how the branched spines of some ancient echinoderm, which served as a defence, became developed through natural selection into tridactyl pediculae, than in understanding the development of the pincers of crustaceans, through slight serviceable modifications in the ultimate and penultimate segments of a limb, which was at first used solely for locomotion. In the avicularia and vibracula of the polyzoa, we have organs widely different in appearance, developed from the same source, and with the vibracula we can understand how the successive gradations might have been of service. With the pollinia of orchids, the threads which originally served to tie together the pollen grains can be traced cohering into cauticles, and these steps can likewise be followed by which viscid matter, such as that secreted by the stigmas of ordinary flowers, and still subserving nearly but not quite the same purpose, became attached to the free ends of the cauticles, all these gradations being of manifest benefit to the plants in question. With respect to climbing plants, I need not repeat what has been so lately said. It has often been asked, if natural selection be so potent, why has not this or that structure been gained by certain species, to which it would apparently have been advantageous? But it is unreasonable to expect a precise answer to such questions, considering our ignorance of the past history of each species, and of the conditions which at the present day determine its numbers and range. In most cases only general reasons, but in some few cases special reasons can be assigned. Thus, to adapt a species to new habits of life, many coordinated modifications are almost indispensable, and it may often have happened that the requisite parts did not vary in the right manner or to the right degree. Many species must have been prevented from increasing in numbers through destructive agencies which stood in no relation to certain structures, which we imagine would have been gained through natural selection from appearing to us advantageous to the species. In this case, as the struggle for life did not depend on such structures, they could not have been acquired through natural selection. In many cases, complex and long-enduring conditions, often of a peculiar nature, are necessary for the development of a structure, and the requisite conditions may seldom have concurred. The belief that any given structure, which we think, often erroneously, would have been beneficial to a species, would have been gained under all circumstances through natural selection. It is opposed to what we can understand of its manner of action. Mr. Mivart does not deny that natural selection has effected something, but he considers it as demonstrably insufficient to account for the phenomenon which I explain by its agency. His chief arguments have now been considered, and the others will hereafter be considered. They seem to me to partake little of the character of demonstration, and to have little weight in comparison with those in favour of the power of natural selection, aided by the other agencies often specified. I am bound to add that some of the facts and arguments here used by me have been advanced for the same purpose in an able article lately published in the Medical Chirurgical Review. At the present day, almost all naturalists admit evolution under some form. Mr. Mivart believes that species change through an internal force or tendency about which it is not pretended that anything is known. That species have a capacity for change will be admitted by all evolutionists, but there is no need, as it seems to me, to invoke any internal force beyond the tendency to ordinary variability, which through the aid of selection by man has given rise to many well-adapted domestic races, and which through the aid of natural selection would equally well give rise by graduated steps to natural races or species. The final result will generally have been, as already explained, an advance, but in some few cases a retrogression, an organization. Mr. Mivart is further inclined to believe, and some naturalists agree with him, that new species manifest themselves with suddenness and by modifications appearing at once. For instance, he supposes that the differences between the extinct three-toed hipparion and the horse arose suddenly. He thinks it difficult to believe that the wing of a bird was developed in any other way than by a completely sudden modification of a marked and important kind, and apparently he would extend the same view to the wings of bats and pterodactyls. This conclusion, which implies great breaks of discontinuity in the series, appears to me improbable in the highest degree. Everyone who believes in slow and gradual evolution will, of course, admit that specific changes may have been as abrupt and as great as any single variation which we meet with under nature or even under domestication. But as species are more variable when domesticated or cultivated than under their natural conditions, it is not probable that such great and abrupt variations have often occurred under nature, as are known occasionally to arise under domestication. Of these latter variations, several may be attributed to reversion, and the characters which thus reappear were, it is probable, in many cases at first gained in a gradual manner. A still greater number must be called monstrosities, such as six-fingered men, porcupine men, Ancon sheep, Niata cattle, etc., and as they are widely different in character from natural species, they throw very little light on our subject. Excluding such cases of abrupt variations, the few which remain would at best constitute, if found in a state of nature, doubtful species, closely related to their parental types. My reasons for doubting whether natural species have changed as abruptly as have occasionally domestic races, and for entirely disbelieving that they have changed in the wonderful manner indicated by Mr. Mivart, are as follows. According to our experience, abrupt and strongly marked variations occur in our domesticated productions, singly and at rather long intervals of time. If such occurred under nature, they would be liable, as formerly explained, to be lost by accidental causes of destruction and by subsequent intercrossing. And so it is known to be under domestication, unless abrupt variations of this kind are specially preserved and separated by the care of man. Hence, in order that a new species should suddenly appear in the manner supposed by Mr. Mivart, it is almost necessary to believe, in opposition to all analogy, that several wonderfully changed individuals appeared simultaneously within the same district. This difficulty, as in the case of unconscious selection by man, is avoided on the theory of gradual evolution, through the preservation of a large number of individuals which varied more or less in any favourable direction, and of the destruction of a large number which varied in the opposite manner. That many species have been evolved in an extremely gradual manner, there can hardly be a doubt. The species, and even the genera of many large natural families, are so closely allied together that it is difficult to distinguish not a few of them. On every continent, in proceeding from north to south, from lowland to upland, etc., we meet with a host of closely related or representative species, as we are likely to do on certain distinct continents, which we have reason to believe were formerly connected. But in making these and the following remarks, I am compelled to allude to subjects hereinafter to be discussed. Look at the many outlying islands round a continent, and see how many of their inhabitants can be raised only to the rank of doubtful species. So it is that if we look to past times and compare the species which have just passed away with those still living within the same areas, or if we compare the fossil species embedded in the substages of the same geological formation, it is indeed manifest that multitudes of species are related in the closest manner to other species that still exist or have lately existed, and it will hardly be maintained that such species have been developed in an abrupt or sudden manner. Nor should it be forgotten, when we look to the special parts of allied species instead of to distinct species, that numerous and wonderfully fine gradations can be traced, connecting together widely different structures. Many large groups of facts are intelligible only on the principle that species have been evolved by very small steps. For instance, the fact that the species included in the larger genera are more closely related to each other and present a greater number of varieties than do the species in the smaller genera. The former are also grouped in little clusters, like varieties around species, and they present other analogies with varieties, as was shown in our second chapter. On this same principle we can understand how it is that specific characters are more variable than generic characters, and how the parts which are developed in an extraordinary degree or manner are more variable than other parts of the same species. Many analogous facts, all pointing in the same direction, could be added. Although many species have almost certainly been produced by steps not greater than those separating fine varieties, yet it may be maintained that some have been developed in a different and abrupt manner. Such an admission, however, ought not to be made without strong evidence being assigned. The vague and in some respects false analogies, as they have been shown to be by Mr. Chauncey Wright, which have been advanced in favour of this view, such as the sudden crystallization of inorganic substances, or the falling of a faceted spheroid from one facet to another, hardly deserve consideration. One class of facts, however, namely the sudden appearance of new and distinct forms of life in our geological formations, supports at first sight the belief in abrupt development. But the value of this evidence depends almost entirely on the perfection of the geological record in relation to periods remote in the history of the world. If the record is as fragmentary as many geologists strenuously assert, there is nothing strange in new forms appearing as if suddenly developed. Unless we admit transformations as prodigious as those advocated by Mr. Mivart, such as the sudden development of the wings of birds or bats, or the sudden conversion of a Hyperion into a horse, hardly any light is thrown by the belief in abrupt modifications on the deficiency of connecting links in our geological formations. But against the belief in such abrupt changes, embryology enters a strong protest. It is notorious that the wings of bats and birds, and the legs of horses or other quadrupeds, are indistinguishable at an early embryonic period, and they become differentiated by insensibly fine steps. Embryological resemblances of all kinds can be accounted for, as we shall hereafter see, by the progenitors of our existing species having varied after early youth, and having transmitted their newly acquired characters to their offspring at a corresponding age. The embryo is thus left almost unaffected, and serves as a record of the past condition of the species. Hence it is that existing species, during the early stages of their development, so often resemble ancient and extinct forms belonging to the same class. On this view of the meaning of embryological resemblances, and indeed on any view, it is incredible that an animal should have undergone such momentous and abrupt transformations as those above indicated, and yet should not bear even a trace in its embryonic condition of any sudden modification, every detail in its structure being developed by insensibly fine steps. He who believes that some ancient form was transformed suddenly through an internal force or tendency into, for instance, one furnished with wings, will be almost compelled to assume, in opposition to all analogy, that many individuals varied simultaneously. It cannot be denied that such abrupt and great changes of structure are widely different from those which most species apparently have undergone. He will further be compelled to believe that many structures beautifully adapted to all the other parts of the same creature and to the surrounding conditions have been suddenly produced, and of such complex and wonderful co-adaptations he will not be able to assign a shadow of an explanation. He will be forced to admit that these great and sudden transformations have left no trace of their action on the embryo. To admit all this is, as it seems to me, to enter into the realms of miracle, and to leave those of science. So ends Chapter 7, Miscellaneous Objections to the Theory of Natural Selection.
The Origin of Species by means of Natural Selection, or the Preservation of Favoured Races in the Struggle for Life. 6th London edition, by Charles Darwin. Chapter 8, Part 1. Instinct. Contents of this chapter include instincts comparable with habits but different in their origin, instincts graduated, aphides and ants, instincts variable, domestic instincts, their origin, natural instincts of the cuckoo, molothrus, ostrich and parasitic bees, slave-making ants, hive bee, its cell-making instinct, changes of instinct and structure not necessarily simultaneous, difficulties of the theory of natural selection of instincts, neuter or sterile insects. Summary. Many instincts are so wonderful that their development will probably appear to the reader a difficulty sufficient to overthrow my whole theory. I may here premise that I have nothing to do with the origin of the mental powers, any more than I have with that of life itself. We are concerned only with the diversities of instinct and of the other mental faculties in animals of the same class. I will not attempt any definition of instinct. It would be easy to show that several distinct mental actions are commonly embraced by this term, but everyone understands what is meant when it is said that instinct impels the cuckoo to migrate and to lay her eggs in other birds' nests. An action which we ourselves require experience to enable us to perform, when performed by an animal, more especially by a very young one, without experience, and when performed by many individuals in the same way, without their knowing for what purpose it is performed, is usually said to be instinctive. But I could show that none of these characters are universal. A little dose of judgment or reason, as Pierre Huber expresses it, often comes into play, even with animals low in the scale of nature. Frederick Cuvier and several of the older metaphysicians have compared instinct with habit. This comparison gives, I think, an accurate notion of the frame of mind under which an instinctive action is performed, but not necessarily of its origin. How unconsciously many habitual actions are performed, indeed not rarely in direct opposition of our conscious will! Yet they may be modified by the will or reason. Habits easily become associated with other habits, with certain periods of time and states of the body. When once acquired, they often remain constant throughout life. Several other points of resemblance between instinct and habits could be pointed out. As in repeating a well-known song, so in instincts, one action follows another by a sort of rhythm. If a person be interrupted in a song, or in repeating anything by rote, he is generally forced to go back to recover the habitual train of thought. So P. Huber found it was with the caterpillar, which makes a very complicated hammock. For if he took a caterpillar which had completed its hammock up to, say, the 6th stage of construction, and put it into a hammock completed only to the 3rd stage, the caterpillar simply re-performed the 4th, 5th, and 6th stages of construction. If, however, a caterpillar were taken out of a hammock made up, for instance, to the 3rd stage, and were put into one finished up to the 6th stage, so that much of its work was already done for it, far from deriving any benefit from this, it was much embarrassed and, in order to complete its hammock, seemed forced to start from the 3rd stage, where it had left off, and thus tried to complete the already finished work. If we suppose any habitual action to become inherited, and it can be shown that this does sometimes happen, then the resemblance between what originally was a habit and an instinct becomes so close as not to be distinguished. If Mozart, instead of playing the pianoforte at 3 years old with wonderfully little practice, had played a tune with no practice at all, he might truly be said to have done so instinctively. But it would be a serious error to suppose that the greater number of instincts have been acquired by habit in one generation, and then transmitted by inheritance to succeeding generations. It can be clearly shown that the most wonderful instincts with which we are acquainted, namely those of the hive bee and of many ants, could not possibly have been acquired by habit. It will be universally admitted that instincts are as important as corporeal structures for the welfare of each species, under its present conditions of life. Under changed conditions of life, it is at least possible that slight modifications of instinct may be profitable to a species. And if it can be shown that instincts do vary ever so little, then I can see no difficulty in natural selection preserving and continually accumulating variations of instinct to any extent that was profitable. It is thus, as I believe, that all the most complex and wonderful instincts have originated. As modifications of corporeal structure arise from, and are increased by, use or habit, and are diminished or lost by disuse, so I do not doubt it has been with instincts. But I believe that the effects of habit are in many cases of subordinate importance to the effects of the natural selection of what may be called spontaneous variations of instincts, that is, of variations produced by the same unknown causes, which produce slight deviations of bodily structure. No complex instinct can possibly be produced through natural selection, except by the slow and gradual accumulation of numerous, slight yet profitable variations. Hence, as in the case of corporeal structures, we ought to find in nature not the actual transitional gradations by which each complex instinct has been acquired, for these could be found only in the lineal ancestors of each species, but we ought to find in the collateral lines of descent some evidence of such gradations, or we ought at least to be able to show that gradations of some kind are possible, and this we certainly can do. I have been surprised to find, making allowance for the instincts of animals having been but little observed, except in Europe and North America, and for no instinct being known among extinct species, how very generally gradations, leading to the most complex instincts, can be discovered. Changes of instinct may sometimes be facilitated by the same species having different instincts at different periods of life, or at different seasons of the year, or when placed under different circumstances, etc., in which case either the one or the other instinct might be preserved by natural selection. And such instances of diversity of instinct in the same species can be shown to occur in nature. Again, as in the case of corporeal structure, and conformably to my theory, the instinct of each species is good for itself, but has never, as far as we can judge, been produced for the exclusive good of others. One of the strongest instances of an animal apparently performing an action for the sole good of another, with which I am acquainted, is that of aphides voluntarily yielding, as was first observed by Huber, their sweet excretion to ants. They do so voluntarily, the following facts show. I removed all the ants from a group of about a dozen aphides on a dock plant, and prevented their attendance during several hours. After this interval, I felt sure that the aphides would want to excrete. I watched them for some time through a lens, but not one excreted. I then tickled and stroked them with the hair in the same manner, as well as I could, as the ants do with their antennae, but not one excreted. Afterwards I allowed an ant to visit them, and it immediately seemed, by its eager way of running about, to be well aware what a rich flock it had discovered. It then began to play with its antennae on the abdomen first of one aphis and then of another, and each, as soon as it felt the antennae, immediately lifted up its abdomen and excreted a limpid drop of sweet juice, which was eagerly devoured by the ant. Even the quite young aphides behaved in this manner, showing that the action was instinctive, and not the result of experience. It is certain, from the observations of Huber, that the aphides show no dislike to the ants. If the latter be not present, they are at last compelled to eject their excretion. But as the excretion is extremely viscid, it is no doubt a convenience to the aphides to have it removed. Therefore probably they do not excrete solely for the good of the ants. Although there is no evidence that any animal performs an action for the exclusive good of another species, yet each tries to take advantage of the instincts of others, as each takes advantage of the weaker bodily structure of another species. So again certain instincts cannot be considered as absolutely perfect, but as details on this and other such points are not indispensable, they may be here passed over. As some degree of variation in instincts under a state of nature, and the inheritance of such variations, are indispensable for the action of natural selection, as many instances as possible ought to be given, but want of space prevents me. I can only assert that instincts certainly do vary. For instance, the migratory instinct, both in extent and direction, and in its total loss. So it is with the nests of birds, which vary partly in dependence to the situations chosen, and on the nature and temperature of the country inhabited, but often from causes wholly unknown to us. Audubon has given several remarkable cases of differences in the nests of the same species in the northern and southern United States. Why, it has been asked, if instinct be variable, has it not granted to the bee the ability to use some other material when wax was deficient? But what other natural material could bees use? They will work, as I have seen, with wax hardened with vermilion or softened with lard. Andrew Knight observed that his bees, instead of laboriously collecting propolis, used a cement of wax and turpentine with which he had covered decorticated trees. It has lately been shown that bees, instead of searching for pollen, will gladly use a very different substance, namely oatmeal. Fear of any particular enemy is certainly an instinctive quality, as may be seen in nestling birds, though it is strengthened by experience and by the sight of fear of the same enemy in other animals. The fear of man is slowly acquired, as I have elsewhere shown, by the various animals which inhabit desert islands, and we see an instance of this even in England, in the greater wildness of all our large birds in comparison with our small birds, for the large birds have been most persecuted by man. We may safely attribute the greater wildness of our large birds to this cause. For in uninhabited islands large birds are not more fearful than small, and the magpie, so wary in England, is tame in Norway, as is the hooded crow in Egypt. That the mental qualities of animals of the same kind, born in a state of nature, vary much, could be shown by many facts. Several cases could also be adduced of occasional and strange habits in wild animals, which, if advantageous to the species, might have given rise, through natural selection, to new instincts. But I am well aware that these general statements, without the facts in detail, can produce but a feeble effort on the reader's mind. I can only repeat my assurance that I do not speak without good evidence. Inherited changes of habit or instinct in domesticated animals. The possibility, or even probability, of inherited variations of instinct in a state of nature will be strengthened by briefly considering a few cases under domestication. We shall thus be enabled to see the part which habit and the selection of so-called spontaneous variations have played in modifying the mental qualities of our domestic animals. It is notorious how much domestic animals vary in their mental qualities. With cats, for instance, one naturally takes to catching rats, and another mice, and these tendencies are known to be inherited. One cat, according to Mr. St. John, always brought home game birds, another hares or rabbits, and another hunted on marshy ground and almost nightly caught woodcocks or snipes. A number of curious and authentic instances could be given of various shades of disposition and taste, and likewise of the oddest tricks associated with certain frames of mind or periods of time. But let us look to the familiar case of the breeds of dogs. It cannot be doubted that young pointers, I have myself seen striking instances, will sometimes point and even back other dogs the very first time that they are taken out. Retrieving is certainly in some degree inherited by retrievers, and the tendency to run round, instead of at, a flock of sheep, by shepherd dogs. I cannot see that these actions, performed without experience by the young, and in nearly the same manner by each individual, performed with eager delight by each breed and without the end being known. For the young pointer can no more know that he points to aid his master than the white butterfly knows why she lays her eggs on the leaf of the cabbage. I cannot see that these actions differ essentially from true instincts. If we were to behold one kind of wolf, when young and without any training, as soon as it scented its prey, stand motionless like a statue, and then slowly crawl forward with a peculiar gait, and another kind of wolf rushing round instead of at a herd of deer, and driving them to a distant point, we should assuredly call these actions instinctive. Domestic instincts, as they may be called, are certainly far less fixed than natural instincts, but they have been acted on by far less vigorous selection, and have been transmitted for an incomparably shorter period under less fixed conditions of life. How strong these domestic instincts, habits, and dispositions are inherited, and how curiously they become mingled, is well shown when different breeds of dogs are crossed. Thus it is known that a cross with a bulldog has affected for many generations the courage and obstinacy of greyhounds, and a cross with a greyhound has given to the whole family of shepherd dogs a tendency to hunt hares. These domestic instincts, when thus tested by crossing, resemble natural instincts, which in a like manner become curiously blended together, and for a long period exhibit traces of the instincts of either parent. For example, Leroy describes a dog whose great-grandfather was a wolf, and this dog showed a trace of its wild parentage only in one way, by not coming in a straight line to his master when called. Domestic instincts are sometimes spoken of as actions which have become inherited solely from long-continued and compulsory habit, but this is not true. No one would ever have thought of teaching, or probably could have taught, the tumbler pigeon to tumble, an action which, as I have witnessed, is performed by young birds that have never seen a pigeon tumble. We may believe that some one pigeon showed a slight tendency to this strange habit, and that the long-continued selection of the best individuals in successive generations made tumblers what they are now. And near Glasgow there are house tumblers, as I hear from Mr. Brent, which cannot fly 18 inches high without going head over heels. It may be doubted whether anyone would have thought of training a dog to point, had not some one dog naturally shown a tendency in this line, and this is known occasionally to happen, as I once saw in a pure terrier. The act of pointing is probably, as many have thought, only the exaggerated pause of an animal preparing to spring on its prey. When the first tendency to point was once displayed, methodical selection and the inherited effects of compulsory training in each successive generation would soon complete the work. And unconscious selection is still in progress, as each man tries to procure, without intending to improve the breed, dogs which stand and hunt best. On the other hand, habit alone in some cases has sufficed. Hardly any animal is more difficult to tame than the young of the wild rabbit. Scarcely any animal is tamer than the young of the tame rabbit. But I can hardly suppose that domestic rabbits have often been selected for tameness alone, so that we must attribute at least the greater part of the inherited change from extreme wildness to extreme tameness to habit and long-continued close confinement. Natural instincts are lost under domestication, A remarkable instance of this is seen in those breeds of fowls which very rarely or ever become broody, that is, never wish to sit on their eggs. Familiarity alone prevents our seeing how largely and how permanently the minds of our domestic animals have been modified. It is scarcely possible to doubt that the love of man has become instinctive in the dog. All wolves, foxes, jackals, and species of the cat genus, when kept tame, are most eager to attack poultry, sheep, and pigs, and this tendency has been found incurable in dogs which have been brought home as puppies from countries such as Tierra del Fuego and Australia, where the savages do not keep these domestic animals. How rarely, on the other hand, do our civilized dogs, even when quite young, require to be taught not to attack poultry, sheep, and pigs? No doubt they occasionally make an attack, and are then beaten, and if not cured, they are destroyed, so that habit and some degree of selection have probably concurred in civilizing, by inheritance, our dogs. On the other hand, young chickens have lost wholly by habit that fear of the dog and cat which no doubt was originally instinctive in them, for I am informed by Captain Hutton that the young chickens of the parent stock, the Gallus bankiva, when reared in India under a hen, are at first excessively wild. So it is with young pheasants reared in England under a hen. It is not that chickens have lost all fear, but fear only of dogs and cats, for if the hen gives the danger chuckle, they will run, more especially young turkeys, from under her and conceal themselves in the surrounding grass or thickets, and this is evidently done for the instinctive purpose of allowing, as we see in wild ground birds, their mother to fly away. But this instinct retained by our chickens has become useless under domestication, for the mother hen has almost lost by disuse the power of flight. Hence we may conclude that under domestication instincts have been acquired, and natural instincts have been lost, partly by habit and partly by man selecting and accumulating, during successive generations, peculiar mental habits and actions, which at first appeared from what we must, in our ignorance, call an accident. In some cases compulsory habit alone has sufficed to produce inherited mental changes. In other cases compulsory habit has done nothing, and all has been the result of selection, pursued both methodically and unconsciously, but in most cases habit and selection have probably concurred. Special instincts. We shall, perhaps, best understand how instincts in a state of nature have become modified by selection by considering a few cases. I will select only three, namely, the instinct which leads the cuckoo to lay her eggs in other birds' nests, the slave-making instinct of certain ants, and the cell-making power of the hive bee. These two latter instincts have generally and justly been ranked by naturalists as the most wonderful of all known instincts. Instincts of the cuckoo. It is supposed by some naturalists that the more immediate cause of the instinct of the cuckoo is that she lays her eggs not daily, but at intervals of 2 or 3 days, so that if she were to make her own nest and sit on her own eggs, those first laid would have to be left for some time unincubated, or there would be eggs and young birds of different ages in the same nest. If this were the case, the process of laying and hatching might be inconveniently long, more especially as she migrates at a very early period, and the first hatched young would probably have to be fed by the male alone. But the American cuckoo is in this predicament, for she makes her own nest and has eggs and young successively hatched all at the same time. It has been both asserted and denied that the American cuckoo occasionally lays her eggs in other birds' nests, but I have lately heard from Dr. Merrill of Iowa that he once found in Illinois a young cuckoo together with a young jay in the nest of a blue jay, Garrulus cristatus, and as both were nearly full-feathered, there could be no mistake in their identification. I could also give several instances of various birds which have been known occasionally to lay their eggs in other birds' nests. Now let us suppose that the ancient progenitor of our European cuckoo had the habits of the American cuckoo, and that she occasionally laid an egg in another bird's nest. If the old bird profited by this occasional habit, through being enabled to emigrate earlier, or through any other cause, or if the young were made more vigorous by advantage being taken of the mistaken instinct of another species than when reared by their own mother, encumbered as she could hardly fail to be by having eggs and young of different ages at the same time, then the old birds or the fostered young would gain an advantage. And analogy would lead us to believe that the young thus reared would be apt to follow by inheritance the occasional and aberrant habit of their mother, and in their turn would be apt to lay their eggs in other birds' nests, and thus be more successful in rearing their young. By a continued process of this nature, I believe that the strange instinct of our cuckoo has been generated. It has also recently been ascertained on sufficient evidence by Adolf Müller that the cuckoo occasionally lays her eggs on the bare ground, sits on them, and feeds her young. This rare event is probably a case of reversion to the long-lost aboriginal instinct of nidification. It has been objected that I have not noticed other related instincts and adaptations of structure in the cuckoo, which are spoken of as necessarily coordinated. But in all cases, speculation of an instinct, known to us only in a single species, is useless, for we have hitherto had no facts to guide us. Until recently, the instincts of the European and of the non-parasitic American cuckoo alone were known. Now, owing to Mr. Ramsay's observations, we have learned something about 3 Australian species which lay their eggs in other birds' nests. The chief points to be referred to are 3. First, that the common cuckoo, with rare exceptions, lays only 1 egg in a nest, so that the large and voracious young bird receives ample food. Secondly, that the eggs are remarkably small, not exceeding those of a skylark, a bird about 1/4 as large as the cuckoo. That the small size of the egg is a real case of adaptation we may infer from the fact of the non-parasitic American cuckoo laying full-sized eggs. Thirdly, that the young cuckoo, soon after birth, has the instinct, the strength, and a properly shaped back for ejecting its foster brothers, which then perish from cold and hunger. This has been boldly called a beneficent arrangement, in order that the young cuckoo may get sufficient food, and that its foster brothers may perish before they had acquired much feeling. Turning now to the Australian species. Though these birds generally lay only 1 egg in a nest, it is not rare to find 2 and even 3 eggs in the same nest. In the bronze cuckoo, the eggs vary greatly in size, from 8 to 10 lines in length. Now, if it had been an advantage to this species to have laid eggs even smaller than those now laid, so as to have deceived certain foster parents, or, as is more probable, to have been hatched within a shorter period, for it is asserted that there is a relation between the size of eggs and the period of their incubation, then there is no difficulty in believing that a race or species might have been formed which would have laid smaller and smaller eggs, for these would have been more safely hatched and reared. Mr. Ramsay remarks that 2 of the Australian cuckoos, when they lay their eggs in an open nest, manifest a decided preference for nests containing eggs similar in colour to their own. The European species apparently manifests some tendency towards a similar instinct, but not rarely departs from it, as is shown by her laying her dull and pale-coloured eggs in the nest of the hedge warbler with bright greenish-blue eggs. Had our cuckoo invariably displayed the above instinct, it would assuredly have been added to those which it is assumed must all have been acquired together. The eggs of the Australian bronze cuckoo vary, according to Mr. Ramsay, to an extraordinary degree in colour, so that in this respect, as well as in size, natural selection might have secured and fixed any advantageous variation. In the case of the European cuckoo, the offspring of the foster parents are commonly ejected from the nest within 3 days after the cuckoo is hatched, and as the latter at this age is in a most helpless condition, Mr. Gould was formerly inclined to believe that the act of ejection was performed by the foster parents themselves. But he has now received a trustworthy account of a young cuckoo which was actually seen while still blind and not able even to hold up its own head, in the act of ejecting its foster brothers. One of these was replaced in the nest by the observer and was again thrown out. With respect to the means by which this strange and odious instinct was acquired, if it were of great importance for the young cuckoo, as is probably the case, to receive as much food as possible soon after birth, I can see no special difficulty in its having gradually acquired, during successive generations, the blind desire, the strength, and the structure necessary for the work of ejection, for those cuckoos which had such habits and structure best developed would be the most securely reared. The first step towards the acquisition of the proper instinct might have been more unintentional restlessness on the part of the young bird, when somewhat advanced in age and strength, the habit having been afterwards improved and transmitted to an earlier age. I can see no more difficulty in this than in the unhatched young of other birds acquiring the instinct to break through their own shells, or than in young snakes acquiring in the upper jaws, as Owen has remarked, a transitory sharp tooth for cutting through the tough egg-shell. For if each part is liable to individual variations at all ages, and the variations tend to be inherited at a corresponding or earlier age, propositions which cannot be disputed, then the instincts and structure of the young could be slowly modified as surely as those of the adult, and both cases must stand or fall together with the whole theory of natural selection. Some species of the Molothrus, a widely distinct genus of American birds, allied to our starlings, have parasitic habits like those of the cuckoo, and the species present an interesting gradation in the perfection of their instincts. The sexes of Molothrus badius are stated by an excellent observer, Mr. Hudson, sometimes to live promiscuously together in flocks, and sometimes to pair. They either build a nest of their own, or seize on one belonging to some other bird, occasionally throwing out the nestlings of the stranger. They either lay their eggs in the nest thus appropriated, or oddly enough build one for themselves on the top of it. They usually sit on their own eggs and rear their own young, but Mr. Hudson says it is probable that they are occasionally parasitic, for he has seen the young of this species following old birds of a distinct kind and clamouring to be fed by them. The parasitic habits of another species of Molothrus, the M. bonariensis, are much more highly developed than those of the last, but are still far from perfect. This bird, as far as it is known, invariably lays its eggs in the nests of strangers, but it is remarkable that several together sometimes commence to build an irregular untidy nest of their own, placed in singular ill-adapted situations, as on the leaves of a large thistle. They never, however, as far as Mr. Hudson has ascertained, complete a nest for themselves. They often lay so many eggs, from 15 to 20, in the same foster nest that few or none can possibly be hatched. They have, moreover, the extraordinary habit of pecking holes in the eggs, whether of their own species or of their foster parents, which they find in the appropriated nests. They drop also many eggs on the bare ground, which are thus wasted. A third species, the M. pecoris of North America, has acquired instincts as perfect as those of the cuckoo, for it never lays more than one egg in a foster nest, so that the young bird is securely reared. Mr. Hudson is a strong disbeliever in evolution, but he appears to have been so much struck by the imperfect instincts of the Molothrus bonariensis that he quotes my words and asks, must we consider these habits not as especially endowed or created instincts, but as small consequences of one general law, namely transition? Various birds, as has already been remarked, occasionally lay their eggs in the nests of other birds. This habit is not very uncommon with the Gallinaceae, and throws some light on the singular instinct of the ostrich. In this family several hen birds unite, and lay first a few eggs in one nest, and then in another, and these are hatched by the males. This instinct may probably be accounted for by the fact of the hens laying a large number of eggs, but, as with the cuckoo, at intervals of 2 or 3 days. The instinct, however, of the American ostrich, as in the case of the Molothrus bonariensis, has not as yet been perfected, for a surprising number of eggs lay strewed over the plains, so that in one day's hunting I picked up no less than 20 lost and wasted eggs. Many bees are parasitic, and regularly lay their eggs in the nests of other kinds of bees. This case is more remarkable than that of the cuckoo, for these bees have not only had their instincts, but their structure modified in accordance with their parasitic habits, for they do not possess the pollen-collecting apparatus which would have been indispensable if they had stored up food for their own young. Some species of Sphagidae, wasp-like insects, are likewise parasitic, and M. Faber has lately shown good reason for believing that, although the Tachytes nigra generally makes its own burrow, and stores it with paralyzed prey for its own larvae, yet that when this insect finds a burrow already made and stored by another sphex, it takes advantage of the prize, and becomes for the occasion parasitic. In this case, as with that of the Molothrus or cuckoo, I can see no difficulty in natural selection making an occasional habit permanent, if of advantage to the species, and if the instinct whose nest and stored food are feloniously appropriated be not thus exterminated. End of chapter 8, part 1.
The Origin of Species by Means of Natural Selection, or The Preservation of Favoured Races in the Struggle for Life, 6th London edition, by Charles Darwin. Chapter number 8, Instinct, Part 2. Slave-making instinct. This remarkable instinct was first discovered in the Formica polyergus rufescens by Pierre Huber, a better observer even than his celebrated father. This ant is absolutely dependent on its slaves. Without their aid, the species would certainly become extinct in a single year. The males and fertile females do no work of any kind, and the workers or sterile females, though most energetic and courageous in capturing slaves, do no other work. They are incapable of making their own nests, or of feeding their own larvae. When the old nest is found inconvenient and they have to migrate, it is the slaves which determine the migration, and actually carry their masters in their jaws. So utterly helpless are the masters, that when Hubert shut up 30 of them without a slave, but with plenty of the food which they like best, and with their larvae and pupae to stimulate them to work, they did nothing. They could not even feed themselves, and many perished of hunger. Hubert then introduced a single slave, F. fusca, and she instantly set to work, fed and saved the survivors, made some cells and tended the larvae, and put all to rights. What can be more extraordinary than these well-ascertained facts? If we had not known of any other slave-making ant, it would have been hopeless to speculate how so wonderful an instinct could have been perfected. Another species, Formica sanguinea, was likewise first discovered by P. Hubert to be a slave-making ant. This species is found in the southern parts of England, and its habits have been attended to by Mr. F. Smith of the British Museum, to whom I am much indebted for information on this and other subjects. Although fully trusting to the statements of Hubert and Mr. Smith, I tried to approach the subject in a skeptical frame of mind, as any one may well be excused for doubting the existence of so extraordinary an instinct as that of making slaves. Hence, I will give the observations which I made in some little detail. I opened 14 nests of F. sanguinea, and found a few slaves in all. Males and fertile females of the slave species F. fusca are found only in their own proper communities, and have never been observed in the nest of sanguinea. The slaves are black, and not above half the size of their red masters, so that the contrast in their appearance is great. When the nest is slightly disturbed, the slaves occasionally come out, and like their masters are much agitated and defend the nest. When the nest is much disturbed, and the larvae and pupae are exposed, the slaves work energetically together with their masters in carrying them away to a place of safety. Hence it is clear that the slaves feel quite at home. During the months of June and July, on 3 successive years, I watched for many hours several nests in Surrey and Sussex, and never saw a slave either leave or enter a nest. As, during these months, the slaves are very few in number, I thought that they might behave differently when more numerous, but Mr. Smith informs me that he has watched the nest at various hours during May, June, and August, both in Surrey and Hampshire, and has never seen the slaves, though present in large numbers in August, either leave or enter the nest. Hence, he considers them as strictly household slaves. The masters, on the other hand, may be constantly seen bringing in materials for the nest and food of all kinds. During the year 1860, however, in the month of July, I came across a community with an unusually large stock of slaves, and I observed a few slaves mingled with their masters leaving the nest, and marching along the same road to a tall Scotch fir tree, 25 yards distant, which they had ascended together, probably in search of aphids or cocci. According to Hubert, who had ample opportunities for observation, the slaves in Switzerland habitually work with their masters in making the nest, and they alone open and close the doors in the morning and evening. And, as Hubert expressly states, their principal office is to search for aphids. This difference in the usual habits of the masters and slaves in the two countries probably depends merely on the slaves being captured in greater numbers in Switzerland than in England. One day I fortunately witnessed a migration of F. sanguinea from one nest to another, and it was a most interesting spectacle to behold the masters carefully carrying their slaves in their jaws, instead of being carried by them, as in the case of F. rufescens. Another day my attention was struck by about a score of the slave-makers haunting the same spot, and evidently not in search of food. They approached, and were vigorously repulsed by an independent community of the slave species F. fusca, sometimes as many as 3 of these ants clinging to the legs of the slave-making F. sanguinea. The latter ruthlessly killed their small opponents, and carried their dead bodies as food to their nest, 29 yards distant. But they were prevented from getting any pupae to rear as slaves. I then dug up a small parcel of the pupae of F. fusca from another nest, and put them down on a bare spot near the place of combat. They were eagerly seized and carried off by the tyrants, who perhaps fancied that, after all, they had been victorious in their late combat. At the same time, I laid on the same place a small parcel of the pupae of another species, F. flava, with a few of these little yellow ants still clinging to the fragments of their nest. This species is sometimes, though rarely, made into slaves, and has been described by Mr. Smith. Although so small a species, it is very courageous, and I have seen it ferociously attack other ants. In one instance I found to my surprise an independent community of F. flava under a stone beneath a nest of the slave-making F. sanguinea, and when I had accidentally disturbed both nests, the little ants attacked their big neighbors with surprising courage. Now I was curious to ascertain whether F. sanguinea could distinguish the pupae of F. fusca, which they habitually make into slaves, from those of the little and furious F. flava, which they rarely capture. And it was evident that they did at once distinguish them, for we have seen that they eagerly and instantly seized the pupae of F. fusca, whereas they were much terrified when they came across the pupae, or even the earth from the nest of F. flava, and quickly ran away. But in about a quarter of an hour, shortly after all the little yellow ants had crawled away, they took heart and carried off the pupae. One evening I visited another community of F. sanguinea, and found a number of these ants returning home and entering their nests, carrying the dead bodies of F. fusca, showing that it was not a migration, and numerous pupae. I traced a long file of ants burdened with booty for about 40 yards back, to a very thick clump of heath, whence I saw the last individual of F. sanguinea emerge, carrying a pupa. But I was not able to find the desolated nest in the thick heath. The nest, however, must have been close at hand, for 2 or 3 individuals of F. fusca were rushing about in the greatest agitation, and one was perched motionless with his own pupa in its mouth on the top of a spray of heath, an image of despair over its ravaged home. Such are the facts, though they did not need confirmation by me in regard to the wonderful instinct of making slaves. Let it be observed what a contrast the instinctive habits of F. sanguinea present with those of the continental F. rufescens. The latter does not build its own nest, does not determine its own migrations, does not collect food for itself or its young, and cannot even feed itself. It is absolutely dependent on its numerous slaves. Formica sanguinea, on the other hand, possesses much fewer slaves, and in the early part of the summer extremely few. The masters determine when and where new nests shall be formed, and when they migrate, the masters carry the slaves. Both in Switzerland and England the slaves seem to have the exclusive care of the larvae, and the masters alone go on slave-making expeditions. In Switzerland, the slaves and masters work together, making and bringing materials for the nest. Both, but chiefly the slaves, tend and milk, as it may be called, their aphids, and thus both collect food for the community. In England, the masters alone usually leave the nest to collect building materials and food for themselves, their slaves, and larvae, so that the masters in this country receive much less service from their slaves than they do in Switzerland. By what steps the instinct of F. sanguinea originated, I will not pretend to conjecture. But as ants which are not slave-makers will, as I have seen, carry off pupae of other species if scattered near their nests, it is possible that such pupae originally stored as food might become developed, and the foreign ants thus unintentionally reared would then follow their proper instincts and do what work they could. If their presence proved useful to the species which had seized them, if it were more advantageous to this species to capture workers than to procreate them, the habit of collecting pupae, originally for food, might by natural selection be strengthened and rendered permanent for the very different purpose of raising slaves. When the instinct was once acquired, if carried out to a much less extent even than our British F. sanguinea, which as we have seen is less aided by its slaves than the same species in Switzerland, natural selection might increase and modify the instinct, always supposing each modification to be of use to the species, until an ant was formed as abjectly dependent on its slaves as is the Formica rufescens. Cell-making instinct of the hive bee. I will not here enter on minute details on this subject, but will merely give an outline of the conclusions at which I have arrived. He must be a dull man who can examine the exquisite structure of a comb, so beautifully adapted to its end, without enthusiastic admiration. We hear from mathematicians that bees have practically solved a recondite problem, and have made their cells of the proper shape to hold the greatest possible amount of honey with the least possible consumption of precious wax in their construction. It has been remarked that a skillful workman, with fitting tools and measures, would find it very difficult to make cells of wax of the true form, though this is effected by a crowd of bees working in a dark hive. Granting whatever instincts you please, it seems at first quite inconceivable how they can make all the necessary angles and planes, or even perceive when they are correctly made. But the difficulty is not nearly so great as it first appears. All this beautiful work can be shown, I think, to follow from a few simple instincts. I was led to investigate this subject by Mr. Waterhouse, who has shown that the form of the cells stands in close relation to the presence of adjoining cells, and the following view may, perhaps, be considered only as a modification of his theory. Let us look to the great principle of gradation, and see whether nature does not reveal to us her method of work. At one end of a short series we have humblebees, which use their old cocoons to hold honey, sometimes adding to them short tubes of wax, and likewise making separate and very irregular rounded cells of wax. At the other end of the series we have the cells of the hive bee, placed in a double layer. Each cell, as is well known, is an hexagonal prism, with the basal edges of its 6 sides beveled so as to join an inverted pyramid of 3 rhombs. These rhombs have certain angles, and the 3 which form the pyramidal base of a single cell on one side of the comb enter into the composition of the bases of 3 adjoining cells on the opposite side. In the series between the extreme perfection of the cells of the hive bee and the simplicity of those of the humble bee, we have the cells of the Mexican Melipona domestica, carefully described and figured by Pierre Hubert. The Melipona itself is intermediate in structure between the hive and humble-bee, but more nearly related to the latter. It forms a nearly regular waxen comb of cylindrical cells, in which the young are hatched, and, in addition, some large cells of wax for holding honey. These latter cells are nearly spherical, and of nearly equal sizes, and are aggregated into an irregular mass. But the important point to notice is, that these cells are always made at that degree of nearness to each other, that they would have intersected or broken into each other if the spheres had been completed. But this is never permitted, the bees building perfectly flat walls of wax between the spheres which thus tend to intersect. Hence, each cell consists of an outer spherical portion, and of 2, 3, or more flat surfaces, according as the cell adjoins 2, 3, or more other cells. When one cell rests in 3 other cells, which, from the spheres, being nearly of the same size, is very frequently and necessarily the case, the 3 flat surfaces are united into a pyramid, and this pyramid, as Hubert has remarked, is manifestly a gross imitation of the 3-sided pyramidal base of the cell of the hive bee. As in the cells of the hive bee, so here the 3 plane surfaces in any one cell necessarily enter into the construction of 3 adjoining cells. It is obvious that the Melipona saves wax, and what is more important, labor, by this manner of building. For the flat walls between the adjoining cells are not double, but are of the same thickness as the outer spherical portions, and yet each flat portion forms a part of 2 cells. Reflecting on this case, it occurred to me that if the Melipona had made its spheres at some given distance from each other, and had made them of equal sizes, and had arranged them symmetrically in a double layer, the resulting structure would have been as perfect as the comb of the hive bee. Accordingly, I wrote to Professor Miller of Cambridge, and this geometer has kindly read over the following statement drawn up from his information, and tells me that it is strictly correct. If a number of equal spheres be described with their centers placed in 2 parallel layers, with the center of each sphere at the distance of radius times square root 2, or radius times 1.41421, or at some lesser distance, from the centers of the 6 surrounding spheres in the same layer, and at the same distance from the centers of the adjoining spheres in the other and parallel layer, then, if planes of intersection between the several spheres in both layers be formed, there will result a double layer of hexagonal prisms united together by pyramidal bases formed of 3 rhombs, and the rhombs and the sides of the hexagonal prisms will have every angle identically the same with the best measurements which have been made of the cells of the hive bee. But I hear from Professor Wyman, who has made numerous careful measurements, that the accuracy of the workmanship of the bee has been greatly exaggerated, so much so that whatever the typical form of the cells may be, it is rarely if ever realized. Hence, we may safely conclude that, if we could slightly modify the instincts already possessed by the Melipona, and in themselves not very wonderful, this bee would make a structure as wonderfully perfect as that of the hive bee. We must suppose the Melipona to have the power of forming her cells truly spherical, and of equal sizes, and this would not be very surprising, seeing that she already does so to a certain extent, and seeing what perfectly cylindrical burrows many insects make in wood, apparently by turning around on a fixed point. We must suppose the Melipona to arrange her cells in level layers, as she already does her cylindrical cells, and we must further suppose, and this is the greatest difficulty, that she can somehow judge accurately at what distance to stand from her fellow laborers when several are making their spheres. But she is already so far enabled to judge of a distance, that she always describes her spheres so as to intersect to a certain extent, and then she unites the points of intersection by perfectly flat surfaces. By such modifications of instincts which in themselves are not very wonderful, hardly more wonderful than those which guide a bird to make its nest, I believe that the hive bee has acquired through natural selection her inimitable architectural powers. But this theory can be tested by experiment. Following the example of Mr. Tegetmeier, I separated 2 combs and put between them a long, thick, rectangular strip of wax. The bees instantly began to excavate minute circular pits in it, and as they deepened these little pits, they made them wider and wider until they were converted into shallow basins, appearing to the eye perfectly true or parts of a sphere, and of about the diameter of a cell. It was most interesting to observe that, wherever several bees had begun to excavate their basins near together, they had begun their work at such a distance from each other that by the time the basins had acquired the above stated width, i.e. about the width of an ordinary cell, and were in depth about 1/6 of the diameter of the sphere of which they formed a part, the rims of the basins intersected or broke into each other. As soon as this occurred, the bees ceased to excavate, and began to build up flat walls of wax on the lines of intersection between the basins, so that each hexagonal prism was built upon the scalloped edge of a smooth basin, instead on the straight edges of a 3-sided pyramid as in the case of ordinary cells. I then put into the hive, instead of a thick rectangular piece of wax, a thin and narrow knife-edged ridge, colored with vermilion. The bees instantly began on both sides to excavate little basins near to each other, in the same way as before, but the ridge of wax was so thin that the bottoms of the basins, if they had been excavated to the same depth as the former experiment, would have broken into each other from the opposite sides. The bees, however, did not suffer this to happen, and they stopped their excavations in due time, so that the basins, as soon as they had been a little deepened, came to have flat bases, and these flat bases, formed by thin little plates of the vermilion wax left ungnawed, were situated, as far as the eye could judge, exactly along the planes of imaginary intersection between the basins on the opposite side of the ridge of wax. In some parts only small portions, in other parts large portions of a rhombing plate were thus left between the opposed basins, but the work from the unnatural state of things had not been neatly performed. The bees must have worked at very nearly the same rate in circularly gnawing away and deepening the basins on both sides of the ridge of vermilion wax, in order to have thus succeeded in leaving flat plates between the basins, by stopping work at the planes of intersection. Considering how flexible thin wax is, I do not see that there is any difficulty in the bees, whilst at work on the 2 sides of a strip of wax, perceiving when they have gnawed the wax away to the proper thinness, and then stopping their work. In ordinary combs, it has appeared to me that the bees do not always succeed in working at exactly the same rate from the opposite sides, for I have noticed half-completed rhombs at the base of a just-commenced cell, which were slightly concave on one side, where I suppose that the bees had excavated too quickly, and convex on the opposed side where the bees had worked less quickly. In one well-marked instance, I put the comb back into the hive and allowed the bees to go on working for a short time, and again examined the cell, and I found that the rhombic plate had been completed and had become perfectly flat. It was absolutely impossible, from the extreme thinness of the little plate, that they could have effected this by gnawing away the convex side, and I suspect that the bees in such cases stand in the opposed cells and push and bend the ductile and warm wax, which as I have tried is easily done, into its proper intermediate plane, and thus flatten it. From the experiment of the ridge of vermilion wax we can see that, if the bees were to build for themselves a thin wall of wax, they could make their cells of the proper shape by standing at the proper distance from each other, by excavating at the same rate, and by endeavouring to make equal spherical hollows, but never allowing the spheres to break into each other. Now bees, as may be clearly seen by examining the edge of a growing comb, do make a rough circumferential wall or rim all around the comb, and they gnaw this away from the opposite sides, always working circularly as they deepen each cell. They do not make the whole three-sided pyramidal base of any one cell at the same time, but only that of one rhombic plate which stands on the extreme growing margin, or the two plates as the case may be. And they never complete the upper edges of the rhombic plates until the hexagonal walls are commenced. Some of these statements differ from those made by the justly celebrated elder Huber, but I am convinced of their accuracy, and if I had space I could show that they are conformable with my theory. Huber's statement, that the very first cell is excavated out of a little parallel-sided wall of wax, is not, as far as I have seen, strictly correct, the first commencement having always been a little hood of wax, but I will not here enter on details. We see how important a part excavation plays in the construction of the cells, but it would be a great error to suppose that the bees cannot build up a rough wall of wax in the proper position, that is, along the plane of intersection between two adjoining spheres. I have several specimens showing clearly that they can do this. Even in the rude circumferential rim or wall of wax around a growing comb, flexures may sometimes be observed, corresponding in position to the planes of the rhombic basal plates of future cells. But the rough wall of wax has in every case to be finished off by being largely gnawed away on both sides. The manner in which the bees build is curious. They always make the first rough wall from 10 to 20 times thicker than the excessively thin finished wall of the cell, which will ultimately be left. We shall understand how they work by supposing masons first to pile up a broad ridge of cement, and then to begin cutting it away equally on both sides near the ground till a smooth, very thin wall is left in the middle. The masons always piling up the cut-away cement and adding fresh cement on the summit of the ridge. We shall thus have a thin wall steadily growing upward, but always crowned by a gigantic coping. From all the cells, both those just commenced and those completed, being thus crowned by a strong coping of wax, the bees can cluster and crawl over the comb without injuring the delicate hexagonal walls. These walls, as Professor Miller has kindly ascertained for me, vary greatly in thickness, being on an average of 12 measurements made near the border of the comb, 1/352 of an inch in thickness, whereas the basal rhomboidal plates are thicker, nearly in the proportion of 3 to 2, having a mean thickness from 21 measurements of 1/229 of an inch. By the above singular manner of building, strength is continually given to the comb, with the utmost ultimate economy of wax. It seems at first to add to the difficulty of understanding how the cells are made, that a multitude of bees all work together. One bee, after working a short time at one cell, going to another, so that, as Huber has stated, a score of individuals work even at the commencement of the first cell. I was able practically to show this fact by covering the edges of the hexagonal walls of a single cell, or the extreme margin of the circumferential rim of a growing comb, with an extremely thin layer of melted vermilion wax. And I invariably found that the color was most delicately diffused by the bees, as delicately as a painter could have done it with his brush, by atoms of the colored wax having been taken from the spot on which it had been placed, and worked in the growing edges of the cells all round. The work of construction seems to be a sort of balance struck between many bees, all instinctively standing at the same relative distance from each other, all trying to sweep equal spheres, and then building up or leaving ungnawed the planes of intersection between these spheres. It was really curious to note in cases of difficulty, as when two pieces of comb met at an angle, how often these bees would pull down and rebuild in different ways the same cell, sometimes recurring to a shape which they had at first rejected. When bees have a place on which they can stand in their proper positions for working, for instance on a slip of wood, placed directly under the middle of a comb growing downwards, so that the comb has to be built over one face of the slip. In this case, the bees can lay the foundations of one wall of a new hexagon, in its strictly proper place, projecting beyond the other completed cells. It suffices that the bees should be enabled to stand at their proper relative distances from each other and from the walls of the last completed cell, and then, by striking imaginary spheres, they can build up a wall intermediate between two adjoining spheres. But, as far as I have seen, they never gnaw away and finish off the angles of a cell till a large part both of that cell and of the adjoining cells has been built. This capacity in bees of laying down under certain circumstances a rough wall in its proper place between two just commenced cells is important, as it bears on a fact which seems at first subversive of the foregoing theory, namely that the cells on the extreme margin of wasp combs are sometimes strictly hexagonal, but I have not space here to enter on this subject, nor does there seem to me any great difficulty in a single insect, as in the case of a queen wasp, making hexagonal cells, if she were to work alternately on the inside and outside of 2 or 3 cells commenced at the same time, always standing at the proper relative distance from the parts of the cells just begun, sweeping spheres or cylinders, and building up intermediate planes. As natural selection acts only by the accumulation of slight modifications of structure or instinct, each profitable to the individual under its conditions of life, it may reasonably be asked how a long and graduated succession of modified architectural instincts, all tending towards the present perfect plan of construction, could have profited the progenitors of the hive bee. I think the answer is not difficult. Cells constructed like those of the bee or of the wasp gain in strength, and save much in labor and space, and in the materials of which they are constructed. With respect to the formation of wax, it is known that the bees are often hard-pressed to get sufficient nectar, and I am informed by Mr. Tegetmeier that it has been experimentally proved that from 12 to 15 pounds of a dry sugar are consumed by a hive of bees for the secretion of a pound of wax, so that a prodigious quantity of fluid nectar must be collected and consumed by the bees in a hive for the secretion of the wax necessary for the construction of their combs. Moreover, many bees have to remain idle for many days during the process of secretion. A large store of honey is indispensable to support a large stock of bees during the winter, and the security of the hive is known mainly to depend on a large number of bees being supported. Hence the saving of wax by largely saving honey, and the time consumed in collecting the honey, must be an important element of success in any family of bees. Of course, the success of the species may be dependent on the number of its enemies, or parasites, or on quite distinct causes, and so be altogether independent of the quantity of honey which the bees can collect. But let us suppose that this latter circumstance determined, as it probably often has determined, whether a bee allied to our humble bees could exist in large numbers in any country, and let us further suppose that the community lived through the winter, and consequently required a store of honey. There can in this case be no doubt that it would be an advantage to our imaginary humble bee if a slight modification of her instincts led her to make her waxen cells near together so as to intersect a little. For a wall in common even to 2 adjoining cells would save some little labor and wax. Hence, it would continually be more and more advantageous to our humble bees if they were to make the cells more and more regular, nearer together, and aggregated into a mass like the cells of the Melipona. For in this case a large part of the bounding surface of each cell would serve to bound the adjoining cells, and much labor and wax would be saved. Again, from the same cause, it would be advantageous to the Melipona if she were to make her cells closer together, and more regular in every way than at present. For then, as we have seen, the spherical surfaces would wholly disappear, and be replaced by plane surfaces, and the Melipona would make a comb as perfect as that of the hive bee. Beyond this stage of perfection in architecture, natural selection could not lead, for the comb of the hive bee, as far as we can see, is absolutely perfect in economizing labor and wax. Thus, as I believe, the most wonderful of all known instincts, that of the hive bee, can be explained by natural selection having taken advantage of numerous, successive, slight modifications of simpler instincts, natural selection having, by slow degrees, more and more perfectly led the bees to sweep equal spheres at a given distance from each other in a double layer, and to build up and excavate the wax along the planes of intersection. The bees, of course, no more knowing that they swept their spheres at one particular distance from each other than they know what are the several angles of the hexagonal prisms and of the basal-rhombic plates, the motive power of the process of natural selection having been the construction of cells of due strength and of the proper size and shape for the larvae, thus being effected with the greatest possible economy of labor and wax. That individual swarm which thus made the best cells with least labor and least waste of honey in the secretion of wax, having succeeded best, and having transmitted their newly acquired economical instincts to new swarms, which, in their turn, will have had the best chance of succeeding in the struggle for existence. End of Chapter 8, Part 2.
The Origin of Species by Means of Natural Selection, or the Preservation of Favoured Races in the Struggle for Life, 6th London edition, by Charles Darwin, Chapter number 8. Instinct. Part 3. Objections to the Theory of Natural Selection as applied to instincts, neuter and sterile insects. It has been objected to the foregoing view of the origin of instincts that, quote, the variations of structure and of instinct must have been simultaneous and accurately adjusted to each other, as a modification in the one without an immediate corresponding change in the other would have been fatal. End quote. The force of this objection rests entirely on the assumption that the changes in the instincts and structure are abrupt. To take as an illustration the case of the larger titmouse, Parus major, alluded to in a previous chapter. This bird often holds the seeds of the ewe between its feet on a branch, and hammers with its beak till it gets at the kernel. Now what special difficulty would there be in natural selection, preserving all the slight individual variations in the shape of the beak, which were better and better adapted to break open the seeds, until a beak was formed as well constructed for this purpose as that of the nuthatch, at the same time that habit or compulsion or spontaneous variations of taste led the bird to become more and more of a seed-eater. In this case, the beak is supposed to be slowly modified by natural selection, subsequently to, but in accordance with, slowly changing habits or taste. But let the feet of the titmouse vary and grow larger from correlation with the beak, or from any other unknown cause, and it is not improbable that such larger feet would lead the bird to climb more and more until it acquired the remarkable climbing instinct and power of the nuthatch. In this case, a gradual change of structure is supposed to lead to changed instinctive habits. To take one more case, few instincts are more remarkable than that which leads the swift of the eastern islands to make its nest wholly of inspissated saliva. Some birds build their nests of mud, believed to be moistened with saliva, and one of the swifts of North America makes its nest, as I have seen, of sticks agglutinated with saliva, and even with flakes of this substance. Is it then very improbable that the natural selection of individual swifts, which secreted more and more saliva, should at last produce a species with instincts, leading it to neglect other materials, and to make its nest exclusively of inspissated saliva? And so in other cases. It must, however, be admitted that in many instances we cannot conjecture whether it was instinct or structure which first varied. No doubt many instincts of very difficult explanation could be opposed to the theory of natural selection, cases in which we cannot see how an instinct could have originated, cases in which no intermediate gradations are known to exist, cases of instincts of such trifling importance that they could hardly have been acted on by natural selection, cases of instincts almost identically the same in animals so remote in the scale of nature that we cannot account for their similarity by inheritance from a common progenitor, and consequently must believe that they were independently acquired through natural selection. I will not here enter on these several cases, but will confine myself to one special difficulty, which at first appeared to me insuperable and actually fatal to the whole theory. I allude to the neuters or sterile females in insect communities, for these neuters often differ widely in instinct and in structure from both the males and fertile females, and yet, from being sterile, they cannot propagate their kind. The subject well deserves to be discussed at great length, but I will here take only a single case, that of working or sterile ants. How the workers have been rendered sterile is a difficulty, but not much greater than that of any other striking modification of structure, for it can be shown that some insects and other articulate animals in a state of nature occasionally become sterile, and if such insects had been social, and it had been profitable to the community that a number should have been annually born capable of work, but incapable of procreation, I can see no especial difficulty in this having been effected through natural selection. But I must pass over this preliminary difficulty. The great difficulty lies in the working ants differing widely from both the males and the fertile females in structure, as in the shapes of the thorax, and in being destitute of wings and sometimes of eyes, and in instinct. As far as instinct alone is concerned, the wonderful difference in this respect between the workers and the perfect females would have been better exemplified by the hive bee. If a working ant or other neuter insect had been an ordinary animal, I should have unhesitatingly assumed that all its characters had been slowly acquired through natural selection, namely by individuals having been born with slight, profitable modifications which were inherited by the offspring, and that these again varied and again were selected, and so onwards. But with the working ant we have an insect differing greatly from its parents, yet absolutely sterile, so that it could never have transmitted successively acquired modifications of structure or instinct to its progeny. It may well be asked how it is possible to reconcile this case with the theory of natural selection. First, let it be remembered that we have innumerable instances both in our domestic productions and in those in a state of nature of all sorts of differences of inherited structure which are correlated with certain ages and with either sex. We have differences correlated not only with one sex, but with that short period when the reproductive system is active, as in the nuptial plumage of many birds, and in the hooked jaws of the male salmon. We have even slight differences in the horns of different breeds of cattle in relation to an artificially imperfect state of the male sex, for oxen of certain breeds have longer horns than the oxen of other breeds, relatively to the length of the horns in both the bulls and cows of these same breeds. Hence I can see no great difficulty in any character becoming correlated with the sterile condition of certain members of insect communities. The difficulty lies in understanding how such correlated modifications of structure could have been slowly accumulated by natural selection. This difficulty, though appearing insuperable, is lessened, or, as I believe, disappears, when it is remembered that selection may be applied to the family as well as to the individual, and may thus gain the desired end. Breeders of cattle wish the flesh and fat to be well marbled together. An animal thus characterized has been slaughtered, but the breeder has gone with confidence to the same stock and has succeeded. Such faith may be placed in the power of selection that a breed of cattle, always yielding oxen with extraordinarily long horns, could, it is probable, be formed by carefully watching which individual bulls and cows, when matched, produce oxen with the longest horns, and yet no one ox would ever have propagated its kind. Here is a better and real illustration. According to M. Verlot, some varieties of the double annual stock, from having been long and carefully selected to the right degree, always produce a large proportion of seedlings bearing double and quite sterile flowers, but they likewise yield some single and fertile plants. These latter, by which alone the variety can be propagated, may be compared with the fertile male and female ants, and the double sterile plants with the neuters of the same community. As with the varieties of the stock, so with social insects, selection has been applied to the family and not to the individual, for the sake of gaining a serviceable end. Hence we may conclude that slight modifications of structure or of instinct, correlated with the sterile condition of certain members of the community, have proved advantageous. Consequently, the fertile males and females have flourished and transmitted to their fertile offspring a tendency to produce sterile members with the same modifications. This process must have been repeated many times until that prodigious amount of difference between the fertile and sterile females of the same species has been produced which we see in many social insects. But we have not as yet touched on the acme of the difficulty, namely the fact that the neuters of several ants differ not only from the fertile females and males, but from each other, sometimes to an almost incredible degree, and are thus divided into 2 or even 3 castes. The castes, moreover, do not generally graduate into each other, but are perfectly well defined, being as distinct from each other as are any 2 species of the same genus, or rather as any 2 genera of the same family. Thus, in Eciton there are working and soldier neuters with jaws and instincts extraordinarily different. In Cryptoceras, the workers of one caste alone carry a wonderful sort of shield on their heads, the use of which is quite unknown. In the Mexican Myrmecocystus, the workers of one caste never leave the nest. They are fed by the workers of another caste, and they have an enormously developed abdomen which secretes a sort of honey, supplying the place of that excreted by the aphides, or the domestic cattle as they may be called, which our European ants guard and imprison. It will indeed be thought that I have an overweening confidence in the principle of natural selection, when I do not admit that such wonderful and well-established facts at once annihilate the theory. In the simpler case of neuter insects all of one caste, which, as I believe, have been rendered different from the fertile males and females through natural selection, we may conclude from the analogy of ordinary variations that the successive slight, profitable modifications did not first arise in all the neuters in the same nest, but in some few alone, and that by the survival of the communities with females which produced most neuters having the advantageous modification, all the neuters ultimately came to be thus characterized. According to this view, we ought occasionally to find in the same nest neuter insects presenting gradations of structure, and this we do find, even not rarely, considering how few neuter insects out of Europe have been carefully examined. Mr. F. Smith has shown that the neuters of several British ants differ surprisingly from each other in size and sometimes in color, and that the extreme forms can be linked together by individuals taken out of the same nest. I have myself compared perfect gradations of this kind. It sometimes happens that the larger or the smaller-sized workers are the most numerous, or that both large and small are numerous, while those of an intermediate size are scanty in numbers. Formica flava has larger and smaller workers with some few of intermediate size, and in this species, as Mr. F. Smith has observed, the larger workers have simple eyes, ocelli, which, though small, can be plainly distinguished, whereas the smaller workers have their ocelli rudimentary. Having carefully dissected several specimens of these workers, I can affirm that the eyes are far more rudimentary in the smaller workers than can be accounted for merely by their proportionately lesser size, and I fully believe, though I dare not assert so positively, that the workers of intermediate size have their ocelli in an exactly intermediate condition. So that here we have 2 bodies of sterile workers in the same nest, differing not only in size, but in their organs of vision, yet connected by some few members in an intermediate condition. I may digress by adding that if the smaller workers had been the most useful to the community, and those males and females had been continually selected, which produced more and more of the smaller workers, until all the workers were in this condition, we should then have had a species of ant with neuters in nearly the same condition as those of Myrmica. For the workers of Myrmica have not even rudiments of ocelli, though the male and female ants of this genus have well-developed ocelli. I may give one other case. So confidently did I expect occasionally to find gradations of important structures between the different castes of neuters in the same species, that I gladly availed myself of Mr. F. Smith's offer of numerous specimens from the same nest of the driver ant, Anoma, of West Africa. The reader will perhaps best appreciate the amount of difference in these workers by my giving not the actual measurements, but a strictly accurate illustration. The difference was the same as if we were to see a set of workmen building a house, of whom many were 5 feet 4 inches high, and many 16 feet high. and we must in addition suppose that the larger workmen had heads 4 instead of 3 times as big as those of the smaller men, and jaws nearly 5 times as big. The jaws, moreover, of the working ants of the several sizes differed wonderfully in shape and in the form and number of the teeth. But the important fact for us is that though the workers can be grouped into castes of different sizes, yet they graduate insensibly into each other, as does the widely different structure of their jaws. I speak confidently on this latter point, as Sir J. Lubbock made drawings for me with the camera lucida of the jaws which I dissected from the workers of the several sizes. Mr. Bates, in his interesting Naturalist on the Amazons, has described analogous cases. With these facts before me, I believe that natural selection, by acting on the fertile ants or parents, could form a species which should regularly produce neuters, all of large size with one form of jaw, or all of small size with widely different jaws. Or lastly, and this is the greatest difficulty, one set of workers of one size and structure, and simultaneously another set of workers of a different size and structure, a graduated series having first been formed, as in the case of the driver ant, and then the extreme forms having been produced in greater and greater numbers through the survival of the parents which generated them, until none of the intermediate structure were produced. An analogous explanation has been given by Mr. Wallace of the equally complex case of certain Malayan butterflies regularly appearing under 2 or even 3 distinct female forms, and by Fritz Müller of certain Brazilian crustaceans likewise appearing under 2 widely distinct male forms. But this subject need not here be discussed. I have now explained how, I believe, the wonderful fact of 2 distinctly defined castes of sterile workers existing in the same nest, both widely different from each other and from their parents, has originated. We can see how useful their production may have been to a social community of ants, on the same principle that the division of labor is useful to civilized man. Ants, however, work by inherited instincts and by inherited organs or tools, while man works by acquired knowledge and manufactured instruments. But I must confess that with all my faith in natural selection, I should never have anticipated that this principle could have been efficient in so high a degree, had not the case of these neuter insects led me to this conclusion. I have therefore discussed this case, at some little but wholly insufficient length, in order to show the power of natural selection, and likewise because this is by far the most serious special difficulty which my theory has encountered. The case also is very interesting as it proves that with animals, as with plants, any amount of modification may be effected by the accumulation of numerous, slight, spontaneous variations, which are in any way profitable, without exercise or habit having been brought into play. For peculiar habits confined to the workers of sterile females, however long they might be followed, could not possibly affect the males and fertile females, which alone leave descendants. I am surprised that no one has advanced this demonstrative case of neuter insects against the well-known doctrine of inherited habit as advanced by Lamarck. Summary. I have endeavored in this chapter briefly to show that the mental qualities of our domestic animals vary, and that the variations are inherited. Still more briefly, I have attempted to show that instincts vary slightly in a state of nature. No one will dispute that instincts are of the highest importance to each animal. Therefore, there is no real difficulty, under changing conditions of life, in natural selection accumulating to any extent slight modifications of instinct which are in any way useful. In many cases, habit or use and disuse have probably come into play. I do not pretend that the facts given in this chapter strengthen in any great degree my theory, but none of the cases of difficulty, to the best of my judgment, annihilate it. On the other hand, the fact that instincts are not always absolutely perfect and are liable to mistakes, that no instinct can be shown to have been produced for the good of other animals, though animals take advantage of the instincts of others, that the canon in natural history of natura non facit saltum is applicable to instincts as well as to corporeal structure, and is plainly explicable on the foregoing views, but is otherwise inexplicable, all tend to corroborate the theory of natural selection. This theory is also strengthened by some few other facts in regard to instincts. As by that common case of closely allied but distinct species, when inhabiting distant parts of the world and living under considerably different conditions of life, yet often retaining nearly the same instincts. For instance, we can understand, on the principle of inheritance, how it is that the thrush of tropical South America lines its nest with mud in the same peculiar manner as does our British thrush. How it is that the hornbills of Africa and India have the same extraordinary instinct of plastering up and imprisoning the females in a hole in a tree, with only a small hole left in the plaster through which the males feed them and their young when hatched. How it is that the male wrens, troglodytes, of North America build cock nests to roost in like the males of our kitty wrens, a habit wholly unlike that of any other known bird. Finally, it may not be a logical deduction, but to my imagination it is far more satisfactory to look at such instincts as the young cuckoo ejecting its foster brothers, ants making slaves, the larvae of Ichneumonidae feeding within the live bodies of caterpillars, not as specially endowed or created instincts, but as small consequences of one general law leading to the advancement of all organic beings, namely, multiply, vary, let the strongest live, and the weakest die. End of chapter 8.